Good morning. Good morning, everybody. My name is Louis Merlin. I'm a professor at Florida Atlantic University. I'll be a moderator for today's session, along with Dr. Islam of, it says Dhaka University. I'm not sure if that's accurate. Today's session, this is track 3 of the Bridging Transportation Researchers Conference. This is the first session, a 9 a.m. Central Time session, Shared Economy and Micromobility. We have 4 presentations today and 2 hours. And so each presentation should take 30 minutes. We've slotted 20 minutes for presentation and then 10 minutes for questions. If there are a lot of questions, I will moderate the questions. I will select the questions from the chat window and ask them to the presenter. But if there's just a few questions, we may just unmute people. And right now we have about 17 participants, so we may just unmute people and allow them to ask their questions directly. I think it depends on the number of questions and the number of participants. I see that everyone's muted now, which is helpful, of course, so that we don't have distracting sound during the presentation. So for each presenter, I'm going to give them a 3-minute warning through chat, and then I'll give a verbal warning at 1 minute. So our first presenter today is Dr. Sina Shokoohyar, who's an assistant professor in decision and system sciences at St. Joseph's University. Sina earned his doctoral degree in operations management from the Jindal School of Management at the University of Texas at Dallas and completed his master's in systems engineering at Sharif University of Technology. Dr. Shokoohyar, his research focuses on developing decision analytic tools that can be implemented in ride sourcing platforms such as Uber and Lyft, the tourist industry, new product development projects, and supplier evaluation systems. His research papers have been presented at conferences such as the Institute of Operations Research and Management Sciences, INFORMS, Management Service and Operations Management, MSOM, and Production and Operations Management Society, POMS, and Decision Sciences Institute. So with that, I will yield the floor to Dr. Shokoohyar, who can tell me how to say his name correctly.
Thank you very much, Luis, for the nice introduction. So let me see if I can share my screen and then, perfect. Do you guys see my screen?
Yes, we do.
Yes, we do.
Perfect. So first I want to thank you guys. Thank you, Luis, for the organizing this session, and thank you very much for the nice introduction. So today my talk is about the impact of trip characteristic and weather condition on ride sourcing network. And we have some, the data sample that we use is from Uber and Lyft. And this is a joint work with Ahmad and Anae. Ahmad is an assistant professor at Kockelman University, and Anae is an assistant professor at Utrecht University. So today, first, I will go over the motivation and the research questions, and then I will go over literature review, data collection methodology, and then I'm going to close my talk by concluding the result for this research paper. So first, I'm sure that most of you have used Uber at least once in your life, and then here in this slide, I'm just going to give you an overview of basically how Uber works, and then after that, I'm going to continue with motivating the research question that we considered and we addressed in this research paper. So basically, Uber and Lyft, they are just platforms that they are matching passengers with the drivers. So at the beginning, for each ride, the passenger basically requests a ride, and after that, then if there is a driver available, Uber is going to match the rider with the driver. And after that, the driver provides service, provides ride to the rider, and after that, basically, the rider pays the driver, and at the end, they can rate each other based on the quality of service that they have received. So basically, when by this example, we see that okay, Uber and Lyft, they don't own any car, and the only thing that they are doing here is just basically matching the potential riders, potential passengers with the drivers, and they don't own any, basically, they don't own any car or vehicle. So the reason that Uber and Lyft, they are growing very fast compared to yellow taxi. Basically, Uber and Lyft, they are more convenient, they are more affordable, and then they are also faster compared to yellow taxis. And then this figure here shows that basically how Uber and Lyft are growing over the time compared to yellow taxis and also rental cars. So it's really popular, and a lot of people are using Uber and Lyft instead of using yellow taxis nowadays. But for us as a researcher, when people are using basically Uber and Lyft, these platforms, they're generating massive amounts of data, which you can use in order to understand companies' performance and also customers' behavior. So these the huge data that these companies are basically generating can be used in order to understand the basically passengers' behavior and also companies' performances. So, as we discussed earlier today, this ride-sharing platform, they are trying to basically equilibrate demand with supply. So the demand in the ride-sharing platform fluctuates a lot and depends on a lot of different things, like, for instance, the rush hours or, for instance, weather conditions. On the other side, the supply side also depends on a lot of different things. For instance, drivers can decide whether, when, and where to provide services. So there's a lot of flexibility in the supply side as well. So these Uber and Lyft, these ride-sharing platforms, in order to basically equilibrate demand and supply, they're trying basically to promote drivers to be available at certain times and at a certain location in order to basically equilibrate demand and supply. The only tools that they have in order to equilibrate supply and demand is just how they are pricing the services that they are providing to their customers, to riders. And this is what is called surge pricing in this context. So Uber and Lyft, they are basically trying to dynamically price their services in order to make it more suitable for their customers. So, but then let me give you an example of how surge pricing works. So this example, this screenshot, I was at a DSI conference in Washington a couple of years ago, and actually this led to this research question and to this paper. So this is the screenshot that basically helped us to start this project, this research paper. So I was at Washington, D.C., and I wanted to attend a conference, and then when I wanted to get a ride using Uber and basically go to my room in the hotel, I saw this basically note here that I wanted to request a ride, and I saw that it's busy and prices may be lower in a few minutes. And I said, okay, let's wait for a couple of minutes and see what can happen. So I waited for a couple of minutes, and I checked outside, and I noticed that it's raining. And then after a couple of minutes, I saw everything change basically in the Lyft app. So you see that how price is changing. Initially, the price was 9.81, and then after less than a minute, the price went down to 6.28. And then if you look at also the number of drivers, number of cars available at the origin, you see also that the number of drivers or number of cars are also increasing. So this the Lyft has increased the price just because it was raining outside, and then the demand was basically greater than supply. So they try to equilibrate demand and supply by increasing the price. So when they increase the price, then some basic drivers that they are already there, I think, they basically open their app, their Lyft app, and then basically now it was working for Lyft compared to Uber or, for instance, yellow taxis. So, and also please feel free to type your question in the chat box if you have any question, or basically if you have any question, feel free to stop and basically unmute yourself and ask your question. So here in this example, here shows that when Uber basically increasing the price, number of drivers increase because it makes it more interesting for those drivers to provide ride, and also basically it can equilibrate demand and supply, right? For instance, when I saw this price 9.81, I said, okay, this is too much. Then I waited for a couple of minutes, and then the price went down. So there are several different ways that Uber and Lyft are trying to basically equilibrate demand and supply. For instance, one of the things that they do, they are just trying to provide guaranteed earnings, different guaranteed earnings for different time of the week. For instance, Friday and Saturday, in this figure, in this picture on the left-hand side, Friday and Saturday from 5 to 3 p.m. they are paying $23 per hour, and then all other hours they're only paying $18. That shows that, for instance, demand during this time is higher, so they are paying more compared to other time of the day. So they are trying basically to manage and control the supply side by just providing different promotions and also dynamically pricing the services that they are providing. So then the research question that we wanted to discuss here basically is we want to see how weather condition, ride origin, destination, location, and type of ride sharing, solo and pool impact the financial and non-financial performance of these ride sharing platforms. So the data that so first let me go over the briefly discuss the literature review and the papers that they have discussed the impact of weather condition and dynamic pricing on ride-sharing platforms. So there are a couple of papers that they have discussed dynamic pricing, but most of them they're analytical, and then they basically our paper is very different from what they have discussed. The only paper that they have discussed the impact of weather condition on ride-sharing platform is this paper titled as "Has Uber Made It Easier to Get a Ride in the Rain?" So they showed that the number of rides during basically rainy hours goes up by 25% for Uber, and it only goes up by 4% for the yellow taxi. So they conclude that Uber is making it easier to get a ride in rainy days. But this is not necessarily correct, because the number of rides are increasing, because that might be just because the demand is going up, or the number of rides increasing, that does not mean it's easier to get ride. The price is going up, the ride fare is going up. So this cannot necessarily be correct. So what that leads to, this is the gap in our research that we want to fill here. So we collected data about using Uber, Lyft, and Yahoo API from June 7 to June 20th in summer 2018 in Philadelphia city, and then overall we collected 700,000 data, around 700,000 data points. And these are the attributes and variables that we have collected through June 7 to June 20th. So basically what we did, we created this grid, 5x5 grid in city of Philadelphia. And from each of these black points to the other point, we tried to create a fake ride request at Uber and Lyft API. And at the same time, we were also collecting the data regarding the regarding the weather from Yahoo Weather API. So in our data set from June 7 to June basically 20th, we have data from each point of this grid to other points regarding the ride, the services that the Uber and Lyft they were providing, the fare, and also the waiting time, pickup waiting time, and also the travel time. So basically this Uber and Lyft API, they are basically they work in the background of every basically the apps that we are using in our cell phone. So basically using the Uber API and Lyft API, we can access everything that basically we can request ride, we can check the history of the rides that we have and everything. So basically using the Uber and Lyft API, we were able to write a program, and that program was were able to automatically basically get the information about rides and also information about the weather. So in that grid, we use the Haversine distance to calculate the distance and generate the distance between each 2 points of that grid. But I think we should have used the shortest path. In another paper, we used the shortest path. I think that's the better way to basically generate the distance between 2 points. But in this paper, we only used Haversine distance for all the points in that in the origin and destination in that grid. So we also use Yahoo weather condition to collect information about the weather condition, and we created a binary variable, the extreme weather condition. The extreme weather condition is 1, basically when it's a scattered showers, rain, or heavy rain, and it's 0 otherwise when it's sunny or mostly sunny. We used a time fixed effect to basically analyze the impact of basically weather on pickup waiting time. Pickup waiting time, the other term that we are using for this pickup waiting time is OVT, or out of vehicle time. And this pickup waiting time basically shows that whether Uber is accessible somewhere or not. When the pickup waiting time is high, then that means that okay, Uber or Lyft is not accessible in that location. So in the next slide, I'm going to, is Haversine distance much different from the consistency proxy for the shortest path, perhaps for the grid equality? It's basically, they are almost the same thing. I think shortest path is better to use here because when we are using the shortest path, then basically that is going to be much closer to the distance that those drivers, they are basically driving throughout the city, right? So I think it's that we should have used shortest path rather than the Haversine distance. So the pickup waiting time, the out of vehicle time, basically here. So the first variable that we included in our basically in our regression was origin to city center distance, and this shows that basically this waiting time when we are getting away from the city center, the waiting time is higher. That means that Uber and Lyft are less accessible in the suburb area, basically around the city compared to the city center. And this is an interesting point about the extreme weather condition for the both weekdays and weekends regression. So basically, if you look at this, the coefficient for the extreme weather condition for weekdays, this is positive, but for the weekends, this is negative. And this shows that basically during the weekdays, the extreme weather condition basically goes up, and basically the waiting time goes up during extreme weather condition and goes down during the weekends, because that's this is basically because of the differences between basically the nature of the travel behavior during the weekdays and weekends. During the weekdays, most of the trips are work related, so people have to basically get Uber or Lyft if it's rainy outside. But during the weekends, it's mostly leisure related. And that's why during the weekends, then they may need to cancel the event, the demand goes down, and that's why the waiting time goes down, because the traffic goes down during the weekend, because during the extreme weather condition, people may cancel their trip just because it's raining outside. So just for the interest of time, since I only have 3 minutes, I'm going to go over the basically final conclusion here. So here in this basically research paper, we had 3 basically regression model: riding fare, average pickup waiting time, and also trip duration. And basically, one of the main results that we got here is that the extreme weather condition impacts these 3 variables: ride faring, average pickup waiting time, and trip duration differently during weekdays and weekends. So during basically weekdays, most of the trips are work related, so people cannot necessarily basically cancel their trip just because it's rainy outside. They have to get to work, and therefore, if it's rainy, then they may need to basically request Uber or Lyft ride. And that is going to impact the fare. So for instance, during the weekdays, if during the extreme weather condition, the fare goes up, and also the pickup waiting time is going up during the extreme weather condition during the weekdays, and also it's going to increase the trip duration during the weekdays. On the other hand, during the weekends, it goes down because most of the rides during the weekdays, during the weekends are leisure related. So people are going to cancel their plan if it's rainy outside. So the extreme weather condition is negatively impacting the waiting time, the trip duration, and also the riding rate. So what we observed here in this research paper basically is that Uber and Lyft, these two ride-sharing platforms, are not balanced throughout the city. So this observation, it's very important, can help the city planners to basically plan to come up with some regulation in order to basically make transportation more accessible to all the people that are living in Philadelphia. I think I'm running out of time, so thank you all for basically attending this conference and attending my talk today. And I'm available if you have any question.
So we do have a couple of minutes for questions, Dr. Shokoohyar. If I could ask the first question,
Sure.
If you could go back to your results on average time to pick up. So my question is, it's very interesting that you have different results for weekdays and weekends, but my question is on the magnitude of the effect. I don't know if to me this looks like a small magnitude variable.
So here, here these are basically normalized between 0 and 1. All the variables and all the basic data points are normalized between 0 and 1. That's why it doesn't show much difference, but they are different. In fact, we did a statistical test, and then these two are definitely different.
So is it fair to compare the size of the effects across coefficients if they've all been normalized? In other words, it's
here it's when we are observing this normalized, the difference is small, but if we are basically testing them, they are not. Basically, the actual data points, they are not.
Okay, let's take some other questions. I see one question in the chat box.
Mm-hmm.
Is the Haversine distance much different from the Euclidean? For
yeah. I tried to answer this question actually when I basically read this question. I was presenting. So these two are almost the same thing, but the shortest path is basically different. The shortest path is, you can easily get the shortest path between the origin and destination, basically using Google API or other basically application programming interface that we have. So shortest path is basically, I think, instead of just using Haversine or Euclidean distance, we should have used shortest path. In another paper, we have used shortest path, and that's a better, I guess, approach, because the shortest path is basically the same thing as it will give us the same distance almost as when the ride happened, the actual distance almost.
I don't see, are there any other questions that someone wants to type in or unmute themselves and ask?
I was actually just typing a question. I wanted to know, we see the normalized coefficient here. So I want to know what this translated to in terms of like actual experience pickup times, for example, or fares. Was it like a 5 or 10 minute difference?
That's a very good question. So I don't have it here in this on this basically slides, but the difference between the extreme weather condition, the weekdays and weekends, it was around half a minute. It was around 30 seconds. So in these 30 seconds, it's in a range of basically the pickup waiting time. It's between 0 to 2 or 3 minutes. So these 30 seconds is something like 20% or 10% difference here between the waiting times. Did I answer your question? Or?
Yeah, thank you.
Mm-hmm.
We do have another question. Any interesting results for pooled versus private trips? Do people's preferences change based on the weather?
Yeah, so depending on the weather, this is not changing a lot, and also, for instance, the weekdays and weekends, but there is very interesting result that I have here. So how much time do I have?
You can go for another, go up till 10:30, and then we'll switch right at 10:30.
Okay, so here in this figure here, basically we are comparing the Uber, basically Uber and Lyft in terms of their fare, and also we are basically including also distance. So the horizontal axis shows trip distance and the vertical axis shows the trip fare. And then those solid line shows the solo rides, and then basically the dashed line shows the pool rides, pool services, Uber Pool and also Lyft line. So one of the interesting results that we have here is, let's only focus first on the solid line, UberX and Lyft. So for small distances, for short distances, then Uber is cheaper than Lyft. This shows that basically Uber and Lyft, they're trying to basically segment the market. Uber is working basically on a larger basically segment of the market, but they are providing the fare for Uber is slightly higher compared to Lyft, but they are trying to focus on the basically larger segment of the market, because if you look at those solid lines, they are basically intersecting each other between 2 or 3 miles. And then this is the segment that Uber is focusing on. Uber is trying to focus on the larger segment where people are basically only using Uber and Lyft for short rides. And then there is this paper also that it's discussing basically mostly people are using Uber or Lyft for just the first or last mile destination. Usually people are just using Uber just to go to the train station, take the train, go to another city, and then they're taking Uber or Lyft to get to work. So basically, since most people are using basically Uber for the first or last mile, basically as an option for the first or last mile destinations, Uber is focusing on the larger segment of the market. And this, we also were able to show basically the differences between the trip fare and also the trip distance between these services provided by Uber and Lyft here.
But did you have any data on whether people switch away from pooled options during bad weather? Did you collect any data on that?
Sorry, can you repeat your question?
So it's a mode choice question. So when the weather is bad, do people opt for solo instead of pooled, or is it the same?
So in our data, we didn't have this information. That's why. So our data only shows that the estimation provided by Uber and Lyft. So these data basically it's the same data when you are opening your Uber or Lyft app, and it shows that okay, the waiting time is this much, the fare is this much, and so on and so forth. We did not make the request. Actually, those are fake requests, because making the request for 700,000 rides is going to be very expensive. That's why we didn't make the request. So we have only the estimation.
Yes, it's not actual rider behavior. It's the availability. It's the availability of vehicles that's from the API that you're gathering.
Exactly.
Thank you very much. Very interesting paper. I think we should switch now to the second paper. If we could go back, Matt. The second paper is from Krishna Gurumurthy, who I think he goes by, what do you go by, Murthy?
Yeah, I just go by Murthy.
Murthy. Krishna Gurumurthy is a doctoral candidate in transportation engineering at the University of Texas at Austin. pursuing his research under Dr. Kara Kockelman. He holds 2 masters in civil engineering and statistics, and is expected to graduate with a PhD in summer of 2020. You're running out of time.
Yeah, that actually got pushed. When I sent that, I think I didn't check.
That's fine. I'm sure you'll graduate soon. His research focuses on travel demand modeling and forecasting, especially through the utilization of large-scale agent-based simulation tools. He's particularly interested in capturing the impacts of shared and autonomous vehicles on travel patterns and congestion, and measuring the resulting effects of various policies. Murthy, as he's often called, is an ENO Fellow in the 2019 class, actively participates in events organized by transportation organizations such as ITE and WTS, and has served in leadership roles in student chapters at UT. In addition to several scholarships, he's also the recipient of the Outstanding Student Award for Texas IT. And I do want to remind all the speakers, there is a little bit of give in terms of the 20-minute presentation window, 20 minutes for presentation, 10 minutes for questions. But I do want to keep everyone to 30 minutes because we don't have any excess time in the schedule, and I want to give all presenters a fair amount of time. So try to keep close to the 20-minute time limit in your presentation. So with that, I'll hand it over to Murthy.
Thank you so much. Okay, can you all see my screen now? I hope you can see my screen. So yeah, thank you so much for the introduction, Dr. Merlin. So this research is about shared autonomous vehicle systems. Like my introduction stated, that's my research focus. And similar to ride-hailing fleets, this is a more future forecasting work, looking at how people will use these kinds of fleets. And this paper that I'm presenting today is especially on how trip demand and stop aggregation for shared autonomous vehicle systems will impact dynamic ride sharing. And I'll give you an overview of why dynamic ride sharing is important and what we found from this study. So the background is that a lot of ride sourcing trips, the mode shares are increasing right now, and they're adding a lot of curbside congestion because of all the pickups and drop-offs at the curbs. Like Uber and Lyft, they have to stop in the middle of the travelway and probably cause some congestion behind. So some densities, especially like Washington, D.C., maybe downtowns of Houston and Boston, they're piloting pickup and drop-off locations just so that they can delineate where Uber and Lyft are supposed to pick up and drop off travelers. And so this was a kind of policy to manage curbside congestion. But this work explores how this can be extrapolated to a future, when the mode shares for shared autonomous vehicles is anticipated to rise. And the reason for that is a combination of low cost and convenience. People want to just be able to get to the destination, not worry about driving there. And if it's low cost, they don't have to worry about owning a vehicle. And if it's a reliable service, for example. So these fleets, SAVs, are expected to induce new travel and trip making. But because they will, just like ride sourcing vehicles right now, they have to go pick people up. So this will add some deadheading, or in terms of autonomous vehicles, empty vehicle miles traveled. And so what dynamic ride sharing does is, if we can better utilize the seats instead of serving one trip per vehicle, there are some studies that have showed that we can reduce the vehicle miles traveled, which corresponds to congestion. And so this study is trying to answer the question, can aggregation of SAV demand at stops lower congestion? So if we can bunch people up at particular locations, hopefully it's convenient also, will that aid in better trip matching and consequently better seat utilization and decrease in congestion? And also look at how this impacts walk distances and traffic and response times of these fleets. And so to answer this question, we used Polaris. Polaris is an agent-based simulator. It's pretty large scale. It has models for destination choice, mode choice, and route choice, in addition to a lot of other timing choices and activity-related models, all econometric models running behind the scene when conducting the discrete time event simulation. It runs pretty swiftly. It's written in C++. In this work, we use Bloomington, so about 600,000 trips across several modes were simulated in just about 20 minutes. And this was with congestion feedback, where vehicles are actually loaded onto the network. And the good thing is it does scale well to larger regions like Chicago. Chicago has about 27 million trips in a day, maybe 30 million now. And it runs, and this simulation can run in about 7 to 8 hours, which is far better than some other simulators like in that people use for research. And so in this simulation tool, we have included the shared service through an operator and vehicle perspective so that there can be centralized dispatch. This is not too different from what we see in other tools. This is just an overview of the different types of matching we have, and stop aggregation and the dynamic ride sharing strategy, which we can change if we want to. And I'll give you an overview of some of these things like when I proceed. So starting with the dynamic ride sharing heuristic. So the heuristic that we included in Polaris is new. It's new in that the dynamic matches occur en route, and it's not based on aggregation at the stop. Aggregation at the origin or destination like some other tools, which is good because it allows for more flexibility in terms of trip matching. In terms of minimizing response times, we used a zone-based search, which is essentially keeping track of vehicles in like nearby zones so that the response times will be within a maximum predefined threshold. And this was found to be computationally efficient for larger regions as well. But this is not the focus here, so I'll move on. So in terms of, because it's en route matching, we don't have information about these trips, full information about these trips apart from origin and destination beforehand. We don't know when these trips will come up. So to facilitate this matching, what we do is we compare ongoing trips in an SAV. So trips that are already, there are passengers in an SAV perhaps, or the SAV is moving from one origin, from one location to another. So this is the ongoing trip. We compare that with the candidate trip, a trip request that just came in the simulation time horizon. We checked for similar directionality. And here directionality was defined based on the OD Euclidean lines. Just connect those origins and destinations for the ongoing and candidate trips and compare what the angle is between them. It was just a simple heuristic just to minimize the matches, make the matches more realistic so that these travelers are traveling towards the same direction. And this helps because if the destination of the ongoing trip is nearby, it allows for lesser, it ensures that the delay is lower, as opposed to if the destination is farther away, then there's more flexibility in that delay for that same fixed angle that we check. And this is supported by the drop-offs being reordered. So this is again all in simulation time, so we don't have all the information. The OD travel times, which is essentially what the router predicts at the beginning of like a trip, we compare that time to how much time a particular traveler has already experienced in the simulation. And if this value is above the OD travel time, then we start calculating the delays, and we make sure that a particular traveler's delay is not greater than, say, 5 minutes or 5% of this OD travel time, which is kind of different from having a threshold value from the top. What we do is we stop an SAV from accepting new rides if this delay is experienced by any traveler, any occupant of the SAV. And next we move on to the PUDO stop placement. PUDO again refers to pick up and drop off locations. So in this case study of Bloomington, Illinois, the region is small, relatively at least. It's 74 square miles and hosts about 120,000 people. It's a small network as well, 4,000 links and 2,500 nodes. So all trip making in Polaris happens between predefined origins and destinations. So these are denoted by these 2,800 unique locations. So what we, because all trips travel through here, like from one of these locations to another location shown here, what we did was we used a hierarchical clustering to choose a portion of these stops. And because the reason we use hierarchical clustering is because we are able to provide a predefined stop spacing. And so clusters are separated out based on the average distance between a cluster to another cluster. And we sample one stop or one location from that so that we can have travelers walk to these stops, and it will not be farther than the predefined DS. And the figure on the right shows the predefined stop spacing of a quarter mile. And so we use another one just to check what the sensitivity is as well in this work. So several scenarios were tested because it was a small region and we wanted to understand not just pickup and drop off location, but also how trip density or trip intensity affects these features of a shared fleet. We scaled the population of Bloomington because everything is an econometric background in Polaris. We're able to just scale the trip making, scale more choices, scale the number of people who are synthesized by a predefined number. So we simulated the population of Bloomington as is, which is 100%, and increase that, multiply that 5 times, and then multiply that again 5 times. So the 25x scenario, which is 2,500%, represents about 15 million trips. So it's a really high density trips, which might not be entirely realistic, but it's a precursor to simulating trip making in Chicago. And when we do increase the population size, we expect travel times to rise and more choices may change. That would be the ideal. That would be nice to compare, but in terms of focusing on SAV fleets, we only wanted the trip demand for the SAV fleet to change and not any other characteristics. So what we did is we increased the capacity of all the links by the same factor so that the travel times, even though travel times might increase, with this increase in capacity, more choices remain fairly consistent. And this will lead to a fairer comparison of changes in system VMP, for example. The fleet sizes for each of these scenarios were also scaled up, such that in each scenario, one SAV serves about 70% trips per day. And this value is specifically for the scenario where we test dynamic ride sharing, and I'll get to that shortly. We consider SAVs to be for matching only if they're less than 10 minutes away, which is fair. 10 minutes is the threshold, so the average is expected to be much lower. Right now, I think if we call an Uber, maybe it takes 5 minutes or 3 minutes, and that's what we see here with the average of about 5 minutes, I think. The one main assumption, pretty major, I think, is that all travelers in our simulation were assumed to use DRS. And because they're assumed to use DRS, it's a lot of people right now are not okay with sharing, perhaps, but the mode shares in our simulations are still low, so this was deemed to be okay. And like I mentioned, the matching, dynamic ride sharing matching ends if the delay experience by a traveler is greater than 5 minutes or greater than 5% of the direct travel time. And then we test about 3 scenarios: no stops, a quarter-mile space stops, and a half-mile space stops. So in terms of results, all scenarios have pretty much the same mode share, 78% of trip makers using SAVs. And so that scales between 48,000 trips to 1.2 million trips. Without dynamic ride sharing, the number of trips served is slightly lower, 65 trips per day, trips per day per SAV. And each SAV travels on average 430 miles. While serving just one trip at a time, the percentage empty VMT is pretty high. This is higher than most studies. Studies predict about 20-25%. So we were surprised with the 34%, but this was consistent in terms of checking how, if there was just, it really depends on fleet size and the trade-off between how many vehicles are idling versus how many vehicles are serving trips. So if there are many vehicles idling, which means a lot of vehicles available, then the EVMT can be low. So without any changes in dynamic ride sharing, the 2 to 5% of the empty VMT was lower just because of the increase in trip density, so that we don't have the SAVs doesn't have to travel a lot farther to get a ride. So with DRS, a lot more trips were served, 5 more trips on average, and the EVMT dropped by a lot. It's just 19% now, and there was a non-linear change in SAV VMT. You would expect, by keeping consistent more chairs and everything, you would expect the same SAV VMT, but we actually found that the VMT traveled, because of dynamic ride sharing, the percentage VMT traveled by an SAV fleet was lower, but this corresponded to an increase in response times and travel times because there was added delay, and SAVs were used more than without DRS, so there were a slightly higher response time. So in terms of trip delays, the walk plus wait plus in-vehicle travel times were seen to double, but this was approximately proportional to the original trip times. So as a percentage of the OD travel time, it may not be as much as that increase. You can see the binning here, where about every bin loses half a share to the next bin on average, because of dynamic ride sharing primarily, and a little bit more because of travelers walking to stops, because this takes into account both walk, wait, and in-vehicle travel time. The percentage EVMT was not affected as much by stops, but it definitely was affected by the increase in trip densities. And this graph is better to show that. So you can see that the increase in trip densities lower that percentage EVMT, and you see a higher increase in average vehicle occupancy with the lower trip demand of the trip demand simulated, and then you see a tapering effect in terms of how much of an increase in AVO we observe with increased trip densities. So it really depends on the region's dynamic ride sharing potential, which is how many trips are overlapping and how many and how this impacts the stops benefits. If there's a region with high density and sprawl, maybe stops are useful, but maybe just high density regions may not need stops. But then there's other factors to consider as well. So total VMT across all scenarios fall by about 1 to 3%, which is good, but it means that the increase because of stops is not as much. But also we should keep in mind that the mode share was really low here. So maybe with a larger, with more shares, it might be different. But there's a lot of SAV VMT savings, about 10 to 20% possible. And this also is more with increased trip demand, which is good. With like more people willing to share and use SAVs, maybe we can considerably lower congestion. And then we saw the temporal distribution. Using stops specifically helped in the off-peak times. You can compare that with no stops, quarter-mile stops, and half-a-mile stop spacing. So maybe just stops at these times are sufficient in terms of improving the fleet usage. But the negative part of this is that we will see increases in SAV arrival at particular locations because we're using stops. And so maybe we need dedicated infrastructure to accommodate them. In conclusion, so dynamic ride sharing does help. A lot of studies have shown that with enough mode share, it helps lower congestion, but we are not yet sure about the willingness, or traveler willingness to share or to be delayed. And higher trip density can lower total VMT like we saw. And so this stops did not help as much, but maybe with higher mode shares it can. And if like other policies like high parking prices may shift shares to SAVs and transit, and this can boost savings as well. And stops marginally increased AVO and lowered VMT, but this whole study assumed that there was no disutility from walking, which might not be true, which I think is inherently not true, depending on how much they have to walk, which we will test in the future. And like we saw the negative externality part, we need that dedicated off-road infrastructure to accommodate SAVs, even though they spend like just a minute at these stops. We need that time we need that space so that they don't add delays to vehicles behind them. And choosing these stops are also important because maybe links with higher capacity or better walkability are better choices for stop placement instead of what we did here, just a random hierarchical clustering. So the future of this work is to run similar scenarios for Chicago and see how larger areas will react to stops. And that's my presentation. Thank you.
Thank you. Thank you, Murthy. I don't see any questions in the window. I typed in any questions other than mine. I typed in 2 questions. I'm going to ask one,
okay,
and then I'm going to give a minute for other people to type in their questions. So my question is, you've thought a lot about the dynamic rideshare logic, about directionality and delay. And my question is even though you've thought about it a great deal, is any of it empirically based? How do we, since we don't have SAV dynamic rideshare systems, I guess we have Uber dynamic rideshare, how do we know what people's willingness to share is? How do we know what criteria are important?
Right, that's a good question. And like I think I mentioned, so in this study, we assume that we're not concerned about willingness to share, assuming that everyone shares. But when people do not share, it does make a difference in terms of how we incorporate that willingness, incorporate their individual heterogeneity in delays. This heuristic was mainly to facilitate sharing, but it does not yet take into account the individual heterogeneity, like you mentioned. But it's something. Sorry.
I guess I just want to comment on the direction of where I think your bias is, and I don't have the empirical data either. But I think saying that a 5% or 5-minute delay is the maximum delay is actually too strict. If you consider that a lot of the population is very price sensitive, there may be significant segments of the population that would rather pay in time than in money. So to say universally across the entire population that a 5% delay is the maximum people are willing to accept, I think is too strict an assumption. Although I don't have data either. So we're both going off our intuition.
Yeah.
But I just wanted to share that thought. We have a question from Matt Dean. Do you know if Uber and others have released results from pickup drop-off locations? We know the built environment characteristics of these locations. So, you know, what do we know about suitable pickup and drop-off locations? And also, there's another question. Did you incorporate the walk time to a stop in the mode choice model?
So I guess I'll go from behind. We did not incorporate the walk time into the mode choice, and this is what I mentioned in terms of accounting for the walk disutility, because that would factor into the mode choice. We assume that it's short enough that they're willing to walk, which may not be entirely true. It might be true for some people, might be true for some locations. But that's something that we need some sort of data to actually create that or incorporate that into the mode choice model. And I think the other question was about, let me open the chat, I guess. I'm sorry, the other question was if Uber and others have received. So I don't know of any results that Uber has released. I know that only from the city side that these stops are being used. And so the cities are trying to manage them. I think that they have quantified the congestion. There's been one work by the International Transport Forum, I think, that looked into curbside congestion using micro simulation. So curbside, I mean, using these zones helps in terms of like increasing the curbside attractiveness and usability. But I'm not sure of any specific work released by Uber at least. And I mean, in the simulation, we have information about the built environment around that stop, so we could factor that in. But it really depends on what we want to factor in, right? I think the focus was that if we, in this study at least, the focus was not minimizing, but, on average, having the same walk time. With that focus, we didn't look at anything else, but we would definitely want to add something like looking into the built environment characteristics.
I think we have time for maybe one more question. If anyone wants to type a question in or raise their hand. I don't see any hands raised. If I don't see a question, I'll go ahead and ask my other question.
Okay.
Which is, can you go back to the first Polaris slide? Describing Polaris, right? So Polaris allows a simulation of destination choice, mode choice, and route choice. So does that mean that the set of trips and trip purposes is taken as a given and input into the model?
Set of trip purposes, yes. So because it's an econometric model, so the number of activities, for example, all that is fixed to begin with. So yes, that set is fixed.
Okay. Yeah. I have more questions, but I think we should go ahead so that we make sure we have time for everyone. So let's move on. To the next presentation. Actually, I'd like to hand over moderation to Dr. Islam, since he's also a moderator. The third presentation is Bob Noland. Dr. Islam, do you want to take over?
Yeah, thank you so much, Dr. Merlin. Now I would like to invite Professor Bob Noland, who is a distinguished professor at the Edward J. Bulliston School of Planning and Public Policy and serves as the director of the LMN Transportation Center and director of the PhD program in Planning and Public Policy. So I would like to request Professor Bob Noland to present your work. Thank you.
Okay, thank you. My paper is about pretty simple. It's what happens when the weather's not so good to both e-scooters and also bicycles. So it's a comparison study of these two modes. And why is that not sure? Hold on a sec. I've got to pull this up here. Okay. All right. So why does this matter? Why do we need to understand how weather might affect these new micromobility modes? That's the key question. A colleague asked me, when I told him about this work, he said, well, where's the policy here? Why does it matter? Well, I think it does for several reasons. We really see these as being a way to reduce vehicle travel, especially in cities. And if you can hear my dog barking in the background, I apologize. Both bicycles, e-bikes, and e-scooters. I'll be looking at the dockless bikes and the e-scooters. So these can be used for short trips, 5 to 15 kilometers or so, durations up to 30 minutes for the bicycles, typically shorter for the e-scooters. But what happens if it's too cold, too hot, too wet, if it snows, windy days? Are people going to be less likely to use them? And then what happens to our transportation system? Essentially what we call a snowbird effect. Will people get in their cars or take public transport? If public transport has been reduced somewhat because we now have these alternate modes, they may be more likely to then drive. Maybe some can work at home on these days if they're using it for commuting. So these are sort of questions that we need to consider, that gives some importance to trying to understand these effects. And I was curious as to whether e-scooters are less sensitive to bad weather than bikes. So we know that fewer people will use bicycles in cold or wet weather. We also know that trip lengths for those that do use bicycles will be shorter. And you know, since we have all these great bike share databases now, it's been feasible to really examine some of those associations. So other work has looked at, for bike share, has looked at temperature, precipitation, relative humidity, wind speeds, none of it giving us any surprises in what the results are, that basically colder temperatures, people will bike less, rainier, snowier weather, people will bike less. Increases in humidity will also lead to less biking, and wind speed is also deterrent. So there's been several studies over the years looking at these. So there was a study in Vermont that, not using bike share, but it was a survey study, or I think it was looking at counts, found that rain, snow, windier weather reduced commuting. Not really too surprising. Same thing in Toronto, found that when it gets below 15 degrees centigrade, and during precipitation and wind, there was less biking. It's always been curious, and I'm going back in time a little bit. If we think back 30, 40 years ago, and we looked at what the big biking cities were, they were actually the cities with really cold weather. A lot in Canada, places like Minneapolis, the Pacific Northwest, where it tended to be rainier, whereas the more temperate climates tended not to have as much biking. Now, I did an analysis with a student. We did look at Washington, D.C. using bike share data, and there we found precipitation, cold temperatures, wind, and high humidity reduced the number of trips. There was a South Korean study found fewer trips above 30 degrees centigrade, so when it gets really hot. Another more temperate climate in Australia, Brisbane, Australia, there was less variation from temperature, but again, reductions in use from wind and rain. So this is all pretty straightforward stuff, not surprising. What about Scootin? Okay, so I did an analysis of Louisville's data, and it wasn't an entire year of data, so there was not a lot of variation in some of the data. It was going from about February to May, if I remember correctly. And there, rain and snow reduced trips. Changes in average temperature and wind had no effect. Okay, and distance increased with warmer weather. Okay, so what did I do here? So the data, so Austin has lots of data into their open data portal. So it's, a lot of people are studying e-scooters in Austin right now because the data is available. So they have all their trips from April 18th, 2018 to the present are available. At the time I downloaded this, there were 7 e-scooter and or bike share companies operating. That could have very well changed in recent months. So I took 1 year of data between October 1st and September 30th. That was about 6.2 million trips. Cleaning that data and mainly removing those that had a distance equal to 0. And whether this was a computer error or someone checked it out and decided not to use it, we don't really know the source of that. But in the end, we had about 92% of that total, so over 5.7 million trips. And this down here, I don't know if you can see my mouse, but is showing just the dashboard that you get, and they've got almost 8 million trips. This was just from a few days ago when I downloaded it. Since the start, okay? Okay, so average distance and duration, looking at the 1 year sample I took. So e-scooter trips typically are about 10.8 minutes on average, 1,500 meter distance. Bike trips tend to be a longer duration, 16.7 minutes and 2.6 kilometers on average, okay? You'll notice the N value for the bike trips is 362. That's because there were 3 days when trips were not available. That may have been due to some sort of shutdown or some problem with the software. and I wasn't able to find information on why that was, but it doesn't really affect the results. So what does it look like over time? On the left, you see the pattern of total daily e-scooter trips and then dockless bike trips. And two things to note is this: in early March, we get this peak here of almost 50,000 trips in e-scooters, and another peak here in late August or so of e-scooter trips. You don't see that peak so much here in the bike trips, but a small peak. So in both cases, you get a big peak. So what's happening there? So that was basically a big festival that happens every year in Austin, the South by Southwest Festival. That other small peak was when the University of Texas session started. So Austin has the University of Texas, which brings, I don't know how many students into the city, but a lot of them. And some of the people from Texas here can probably tell me that. And then there are also football games at the university, which bring in people. So if we look at the average e-scooter trips on football days, it's about 25,000. Compared to other days, it's about 14,000. And then other Saturdays, that's when the football days are, it's about 20,000. So you're getting a peak from these events, basically. A little bit less, some variation in the bike trips also, but not as much. So that just tells us we need to control for these things when we do the analysis. The weather data was from the Austin Bergstrom Airport Station, downloaded from NOAA's website. Relatively mild climate, but with a hot summer. So our average, let's see, what would be average daily temperature, 68 degrees Fahrenheit, or almost 69. The minimum average, about 58 degrees. The maximum hottest temperature here, 102 degrees. So it gets fairly hot in the summer, but the minimum temperature was in the winter was 24 degrees Fahrenheit. So still fairly temperate, but some variation there. Not a particularly rainy season, but 4.7 inches of rain in one day was the maximum. Not particularly windy, about 20 miles per hour on average on one day. Okay, I can't see the time because I lost the clock on my screen, but that's okay. Okay, so what did we do? What did I do here? So what was the strategy? So the main hypothesis here was that weather affects bike trips more than e-scooter trips. Total trips, average trip duration, and distance were associated with the weather variables, day of the week, which varies, the football days, school session, and those SWSX days, okay? A few things in terms of how you analyze this data. So our trip counts, so if we're looking at total trip counts, it violates our normality assumption. So usually you use a negative binomial regression or something. But the other problem is our data is serially correlated. In other words, we're doing a time series. We had about 365 days or so, and we're looking at each day. And we'd expect some serial correlation because the weather on one day may affect the weather the next day. So they're going to be related to each other. So to deal with this, and I actually did the negative binomial model in the paper. I'm not going to show that, but just to kind of compare different models. But did the log of the trip counts to more estimate the normal distribution. And to account for serial correlation, we used a Praise-Winston model. And then we also, for the trip count models, I did a random forest, and that avoids some of the distributional issues and some of the multicollinearity that's among the weather variables. So it gives us a fuller picture of what's happening, or at least what's important in terms of affecting e-scooter use and the bike share use. Okay, so what are our results? And just to summarize. So SXSW and football days lead to more trips, but really had no effect on duration or distance of trips for e-scooters. When school's in session, there are more trips, duration, distance, or less. So suggesting perhaps that the students are using them for shorter trips And some anecdotal evidence of that, I've heard of students using them on campus, between buildings or between residence halls and buildings and things like that. Thursday, Friday, Saturday, and Sunday, I'll have more trips with duration and distance or greater, except on Thursday and also on holidays also. So our key variables here, the weather variables, rain, wind, and cold weather all lead to fewer trips with shorter duration and distance. So no surprise there. For bike trips, the special events had a weaker association with less statistical significance. School session had no effect on total trips. Day of week was also less significant, but Friday and Saturday had slight positive associations. And Saturday, Sunday, and holidays have longer durations and distances. And again, our rain, wind, and cold weather led to fewer trips and shorter trips. Okay, so just to pull out some of the numbers here to show the effects a little bit. On the left, you have e-scooter models. On the right, you have bicycle models. So our coefficient, our t-stats. And this was a trip count model. And the key thing here, so wind speed, well, I mean, the key thing here is almost everything's, significant. Wind seems to have a small coefficient value, but has more effect on the bicycles. Rain has more effect on the bicycles. Temperature has more effect. Warmer weather, more bikes. Warmer weather, more e-scooters, or I like to think of it the other way around. Same thing for distance. Wind has a greater effect here on bike distance. Rain has a greater effect on bike distance. Temperature here it's still statistically significant at a lower level. Not too much difference here between e-scooters and bikes on the distance of trips. Duration pretty much follows the same pattern as the distance here in this case, because those two are highly correlated. So what did our random forest model show? And just one thing about a random forest model is it gives us no directional effects, but it tells us what's most important. And so these are typically used for predictive purposes. And but I'm using it just to kind of understand what's most important here. And if we look at it here, we see that the SXSW really dominates, that really affected the total trip count, okay? So it's hard to really see much difference here in some of our weather variables, which are up here. So let's look at this. What I did is I took those out of the model and re-estimated. So here we see at the top here are our weather variables. These two here, I didn't explain these. These are like the maximum 5-second wind and maximum 2-second wind. So these are gusty winds, basically measures. Minimum temp, maximum temp, average temp. I can include all of these at the same time in this model because we don't need to worry about collinearity here. But the key result here is the orange lines are showing that these are much more important for bike trips than for e-scooter trips, which is the blue line. School sessions also more important for bike trips, and that's probably in a negative sense at least. Holidays more important. On the other hand, our football games seem to be really attracting the e-scooter trips more than bike trips. Saturdays, and then these other ones, a little less difference, but some small differences between them. And these are really more control variables. So what are some of the conclusions here? So large events affect e-scooter usage. And so the key point there is, at least from looking at weather patterns, is we need to control for that. So you still have some local knowledge of the city and when these events occur. I cannot claim, and I may have missed some big events in Austin that I'm unaware of, but it kind of looking at the pattern of usage over time, I think I picked up most of it there. The patterns of e-scooter usage, especially on weekends and during these events, kind of suggests to me that they're popular for recreation. So there's more usage on weekends and longer trips. And there's a lot of other work coming out that really shows that these, not saying they're not used for utilitarian trips, but that they are very popular for recreation also. The local demographics can matter. So student usage of e-scooters in Austin is very important, and really suggestive of some of the shorter than average trips. But the weather has an impact on both modes of travel. So it does seem to impact bike usage more than e-scooter usage. It's possible that there is reductions in e-scooter use from bad weather, mainly due to less recreational use. And that's probably true for the bikes also. So the key thing here is that e-scooters seem to be more resilient to the weather than bicycles are, which doesn't really surprise me. So the larger implications here is whether weather will deter broad usage, especially in the wintertime, but that e-scooter users may not be as affected as much as cyclists. Do new micromobility options need to provide protection from rain and cold weather? So, you know, a lot of the micromobility companies are continuing to try to offer, you know, not just rely on the e-scooters that are out there now, but try to develop new modes that might offer, you know, be suitable for a broader audience, basically, broader base of customers. So the key limitations here, and we can always think of more probably, but you know, Austin had a relatively mild climate. I didn't have any snow days in my analysis. The other that occurs to me is we don't really know about the supply side. You know, I don't think anything was supply constrained in this case, but there could be, you know, I've heard of some cities shutting down systems when especially when it's there's snow on the streets and things like that. So those things need to be controlled for. A few references that I threw in here, if you're interested. Those are other work on looking at weather effects. So happy to take questions.
Okay, thank you, Professor Noland, for your excellent presentation. There are some good questions from the participant. So first, I want to go to the question. He's confused about the difference between bicycle and e-scooter, and he's asking why is that the average distance is more in bicycle.
What, just the basic distance? Well, probably one reason is it's cheaper to use. And it's probably, that's probably the main reason. It's cheaper to use. So the pricing of the e-scooters is fairly high.
Okay. So Dr. Merlin may have some questions. Do you ask directly, or should I ask in behalf of you?
You can go ahead and ask. They're very short questions.
Okay. Okay, Dr. Merlin wants to know, is weather data available only daily, or is hourly data also available?
So yes, a good question. Before, you know, last week I actually, I have the hourly data, and I started looking at that, but it doesn't really show any difference. And it creates a lot more serial correlation issues. Basically, I could not get my Durbin-Watson statistics to an adequate value with most of the models. So I don't think it's added anything to looking at this by using hourly data in this case.
Okay. So there is a good question. Is there perhaps a difference in characteristics of users between e-scooter and bike users that would affect willingness to accept poor weather conditions?
I don't know. It's an empirical question. We need to understand who the users are. The problem with using all of this data is we don't know that. We're not doing surveys of these users, or at least I have not done them. And I think that's a key thing to look at for future research. It's easy to download this data and do the analysis. It's much more difficult to actually go out and collect some data on your own, actually, to get a good representative sample of users.
Okay. And another question is, was there any difference with respect to geographical location inside Austin?
Can whoever asked that elaborate on what you mean?
Yeah, it is Bhushan 515 to everyone. Bhushan 515, 9:17 p.m. Can you see the question?
Well, let me try to answer that. Go ahead.
Can I ask you again? I mean, you said something like on the supply side, you didn't know, right? So maybe in one geographic location, the supply was low. Maybe that will reflect in your analysis that in one geographical location, there is the effect of bikes more or something like that.
It's certainly possible. We do know from some other work that something like 93% of the scooters trips are in the central area of Austin. There are obviously fewer trips in the surrounding areas, the further you get from the center of the city. But no, obviously we don't know what the supply characteristics are and where they are located. It is something that someone could look at, but really you can only figure that out from the data that's available, from whether someone checks out a scooter or bike. We don't know if they didn't check one out, we don't know whether it was because there wasn't a bike or scooter there.
Okay. So there is another question from Manish. Can you explain your question, Manish? Because it seems a big question. Can you explain it to Professor Noland? Okay, I am reading this question.
Okay, no, I see it. I can read the chat. So he's asking, the attitudes of bicycle riders mattered based on some work in Edmonton, Canada. I couldn't agree with you more. I ride throughout the winter time myself, but less likely to do so if there's snow on the ground, having slipped a few times. So, yes, it does, but we don't have an answer to that. Don't forget, we're using over 5 million different trips aggregated together over 365 days.
Absolutely, Bob. I just wanted to say that to the point you made earlier when you started the presentation, clearly this data set doesn't lend itself to attitudinal analyses of any sort. But in this piece we did in Edmonton, Canada, we did have some data on attitudes, and what we found was that the inclination to bike actually mattered, and it mattered more for men than women. So controlling for that attitude, at least for bicycle trips, men were more likely to bicycle in snow weather with snow on the ground. And absolutely, this data is fascinating, but it doesn't allow you to dig into that deeper domain of perceptions and attitudes. I just wanted to acknowledge that piece.
Right. No, I agree. And, there are always outliers.
Yep,
people who will bike in any sort of weather, but it's really hard to make policy based on outliers.
Bob, I did want to ask a clarifying question. If you could go back to your presentation, there were two charts back to back on the effect of different variables, and I couldn't quite catch the difference between the two charts.
Okay, I'm trying to
the
get
analytical
this back.
Difference.
I turned sharing off. Hold on a sec. I've got two screens here, so it gets a little confusing. Okay, can you see that again?
No, not yet.
Here we go.
Yeah,
okay.
It's coming.
All right.
Yeah.
Do you mean this chart?
Yes, there's two charts back to back, slides 14 and 15, and I couldn't quite catch what was 14 and what was 15.
So 14 included all 365 days, including the SXSW festival. So you see here that dominates the analysis. So it's really hard to see the differences in the other variables. Okay, so I basically just took those 8 days or so out of the analysis and reanalyzed the data. And this shows me then highlights the differences in the weather variables in particular here at the top.
And these are both through random forest techniques?
Yes.
Okay, thank you very much.
Okay, thank you, Professor Noland. So I can't see any more questions. So I think that's all. So thank you.
Okay, thank you. And thank you to everyone for showing up.
Yeah. So, okay, now we can go to our next presenter, Amari Lewis. Amari Lewis is a PhD candidate at the UC Irvine in the Department of Computer Science. And he is doing his PhD under the supervision of Amelia Regan. Amari earned his bachelor's in mathematics and French minors from Winston-Salem State University, located in NC. She also earned a master's degree in computer science from UC Irvine. Her primary research is interdisciplinary in nature, focuses on developing and using emerging technologies for the improvement of paratransit transportation services. So let's welcome Amari Lewis.
Thank you. Yes, I am a woman, Amari Lewis. Thank you all for attending today's presentation. Can you see my screen? Please confirm.
Yeah. Yeah,
awesome.
we can see.
Awesome. So I'll get started. Yes, so this presentation is on our current research where we analyze the results from a survey that we sent out to California paratransit agencies on the adoption of TNC services with paratransit. To begin, I would like to provide with you the structure of the presentation. I'm going to start with a small introduction, and then I will go into the background and motivation of our work, the methodology for these projects, as well as the demographics for the participating agencies. And the bulk of the presentation, I will discuss the results from the different interviews and surveys. To conclude, I will discuss our major conclusions and the future direction of this work. Paratransit is defined as a reserved transportation service for the elderly, older adults, and disabled passengers throughout the United States and Canada. And these services are for these ADA passengers. There are some requirements for ADA paratransit, which involves that it must be within 3/4 of a mile on each side of a fixed route service. And essentially, there are some drawbacks to these services to which we address within our research. These include things such as late pickups, no-shows, and inconvenience of requesting rides. And TNCs are transportation network companies, which are app-enabled, on-demand public ride-hailing services with minimal service area constraints. ADA paratransit has been around for roughly 30 years, and per the 1990 Americans with Disabilities Act, paratransit became a mandatory service. And TNCs have more recently emerged and gained popularity, and they've mainly started out as smaller, smaller startups in San Francisco and things of that nature, and they've quickly grown. And now we have a plethora of options such as Lyft, Uber, BlaBlaCar, and things of that nature. So within this work, we are exploring the integration of TNCs and paratransit in order to improve paratransit services. And we are receiving the feedback from the agency's perspective within this study. For the passengers, we hope to enhance the experience, and for the agencies, we hope to reduce the operational costs. Essentially, since our study has began, Uber and other ride-hailing services have began to have some more accessible services offered, such as Uber Assist, Lyft Access, and non-emergency transportation services through Lyft as well. On this slide, I would like to discuss our methodology for our project. Essentially, we reached out to all of the agencies throughout California and confirm whether or not they operated paratransit. Upon receiving that information, we are maintaining and updating a database, a database of information with contacts from these agencies, as well as the information as it relates to their paratransit service. Then we are sending an actual invitation to the agencies to be able to participate in the first segment of our study, which includes an online survey. And upon receiving their acceptance to our survey, we then send a follow-up for a follow-up semi-structured interview with the agencies as well. And although all agencies did not participate in the semi-structured interviews, we received a diverse amount of responses. So upon having scheduled the semi-structured interviews, we then conduct the interviews. And following that, lastly, we transcribe the interviews and we analyze both sets of data. In total, we received 30 responses from agencies across California. And here are the demographics on this slide of what these agencies look like. So we received one response from a tribal agency, one from a private nonprofit corporation, and majority of our respondents were from city, county, or local governmental unit Department of Transportation. And lastly, we received a good bulk from independent public agencies or Authority of Transportation Services. Also on this slide, you can see the demographics as it relates to whether or not the agencies are in rural or urban areas. And majority are from urban areas. However, we did receive a good number of rural respondents as well. So we were able to compare these results. So the next section of the presentation, I will be discussing the survey results. The first 3 questions of the survey consisted of asking about the passengers. So within the first question, we wanted to know whether or not passengers actually have smartphones. And we actually found that about 50%, roughly 46% of passengers have smartphones. Additionally, majority of the passengers are over the age of 65. Actually, some agencies even reported that 100% of their passengers are over the age of 65. However, seeing that majority of the passengers are having smartphones, although they are older in age, they may also have a smartphone, which correlates. And it's very important to our study because if we're integrating TNCs, we need to be able to have the passengers with smartphones. And lastly, passengers under the age of 25, to no surprise, were very low percentages. Within the next question, we ask about how passengers are requesting their rides. And currently, majority of the passengers must request their rides by calling in advance. We found that no agency is currently using any type of mobile app to be able to request their rides. And the other responses referred to things such as simply going to a bus stop, coming to the station, or filling out paperwork in order to request their ride. The next question addressed whether or not the agency has considered the partnership between taxis, Ubers, Lyfts, or GoGo Grandparent, which acts as a vetting service for TNCs like Ubers and Lyfts. And these findings were quite interesting as well. We found that 63% of our urban agencies have considered this partnership, but only 17% of them have conducted an actual pilot study. Also, 45% of our rural agencies have not considered this partnership due to the lack of TNC services within their area. So this was a quite interesting finding from our survey as well. And this correlates with previous research, as they have found that more than half of Uber and Lyft users live in more urban neighborhoods. The next question addresses the improvements to paratransit services within the past decade, and 80% of our survey respondents answered that they have made improvements based on technologies. And here we have listed the certain types of technologies that they've incorporated into their paratransit as far as improvements, which include real-time dispatching, advanced reservation services, cameras on board, online reservation, mobile tablets within the fleet, and passenger portals. Next, with the integration of TNCs, there are some security concerns. So we wanted to ask what type of price increase an agency would be susceptible to accept in the event for this integration. And we found that the increase in paratransit costs due to this integration is a major concern for agencies for their passengers. In the more rural populations, there are limited budgets and the cost per rides are already high. And an actual agency responded by stating that our area is extremely low income and cannot sustain a price increase. And we must keep in mind that the ADA paratransit also has some requirements and restrictions as it relates to increasing the price. The fares must not exceed 2 times the full fare of a fixed route service. In the final question of the survey, we addressed 5 different sub-questions. And for the purpose of this presentation, I want to focus mainly on the second sub-question, which we ask about whether or not passengers would feel safe with the unknown drivers and unfamiliar vehicles. And generally, majority of the respondents agreed or strongly agreed to this statement. We found that 10 strongly agreed, actually, and the other 13 actually agreed to this statement. And this is also parallel to what the findings of previous research indicates, where the model confirms that concern and safety about drivers are associated with lower ride-hailing frequencies. Now I'd like to go into our interview analysis from our semi-structured interviews. As I stated before, we had a population of 30 total respondents, and from those respondents, we were able to only confirm 3 separate interviews. And these interviews were each 1 hour long, and they each had 2 different participants within the interview. The first interviews were done with a Southern California metropolitan organization. The second were with 2 Northern California transit agencies, and the third were with a Southern California transit agency. From the interviews and the transcription of the interviews, we were able to address a coding process where we analyzed different major themes through a weighted coding system from 1 to 5, 1 being the lowest and having a more negative connotation towards the theme, and 5 being the highest, having a more positive connotation towards the theme. And in the next slide, I will show the results. So here are the 14 major themes that were addressed throughout the semi-structured interviews, which includes the aging population, autonomous vehicles, customer feedback, driver shortage, education, environmental impact, funding, government legislation, growth expansion, improvements, operational costs, taxi or TNC pilots, taxi or TNC lack of wheelchair accessible vehicles, and technological advances. To hone in on some of these results, the taxi or TNC pilot theme became a major theme, and it actually had the highest count of frequency. However, the connotation towards the TNC pilot programs from the interviewers were kind of negative. And I'll go into some of those results in the next slides. Contrarily, the customer feedback was quite positive from the actual TNC pilots. And additionally, funding was a major concern and negatively received from all of the agencies in MPO. On this slide, I will address some of the excerpts from the actual semi-structured interview. As it relates to the TNC integration, one of the agencies mentioned that there's so many problems with the service provider when they actually had their pilot program. They were calling in sick, they were not doing the rides. Unfortunately, we moved away from it. And this was very unfortunate to hear from this perspective, but it happened. Additionally, another agency mentioned that Company X went out of business and left 800 rides unfulfilled at the last minute. So these are very negative experiences from the agencies. As it relates to customer feedback, though, as previously mentioned, the customers greatly receive these TNC integration programs and pilot programs. For instance, the agencies mentioned that passengers really liked the private rides and they felt more comfortable, and they actually appreciated this type of integration. As it relates to environmental impact, one of the agencies mentioned that they were able to subsidize their trips. However, this caused an increase in vehicle miles traveled and emissions and congestion. And as it relates to funding, an agency mentioned that we are allotted to receive federal transportation funds, but if we could not demonstrate or conform to the sustainability strategies implemented by the government, the funds would stop flowing. And lastly, with technological advances, one agency mentioned that technology can improve the quality of service, provided reliability and real-time improvements, assuming that the issues with cost can be addressed. So we noticed that a lot of the themes are cross-referenced and they relate to each other. In the end, we noted that many of the agencies have a desire for the integration with TNCs. However, there are many challenges that need to be addressed. There are challenges with this integration as well as the data that's collected, in addition to the actual agreement between TNCs and paratransit agencies. As far as the future work, we are working on expanding our sample and including other states as well throughout the US and Canada. We'd also like to have a focus group within California to be able to receive perspective on the actual passengers. And lastly, we're working on developing and improving the prototype app and being able to deploy that within our focus group. And this concludes my presentation, and these are just some acknowledgements. And this concludes my presentation. So thank you so much for your attention.
Thank you, Luis, for your excellent presentation. So I can see one question in the box.
Okay.
And did you receive feedback from transit agency unions or current paratransit workers?
Can you repeat the question? I'm sorry, I'm trying to go.
Yeah. Do you receive the feedback from agency unions or workers? Madden asked these questions.
Okay, so I think your question is, oh, unions, okay. So this is current paratransit workers. This was actually at the agencies. So we actually went to the agencies and spoke to different professionals with different ranges of titles. So they had different roles within paratransit, and we were able to receive their perspective.
Okay. So did you get the sense that the agencies were communicating with one another with regards to their experience with TNCs?
That's an excellent question. And yes, actually, there are some smaller studies throughout California that actually do similar surveys that like we have done. And so some agencies are communicating with other agencies. So they were aware of what other agencies have been going through and have been working on.
Okay, thank you. There is next question. Do you think that more users and drivers would get on the board if this was a direct user to driver link without a paratransit level?
That's an excellent question. And that's one of the things that I initially thought of when we started this work, to take away the paratransit label. Because essentially when you think of paratransit, you think of wheelchair accessible vehicles, you think of the vans. However, it's a range of disabilities and a range of different types of passengers. And so I'm not sure if that will improve the user's, experience, but I also thought of the same thing. So it's something that we're addressing, but we shall see in the future. But that's a good question. Thank you for that.
Okay, thank you. So is there any questions? There are time in our hands, so if you have any question, you can ask.
Dr. Islam, I'd like to ask a question. This is Lewis Merlin. So you mentioned, Dr. Lewis, you mentioned additional costs if TNCs were involved for privacy reasons. And I guess I had two questions. One is I'm not clear what the additional cost would be. And the other is my general understanding is that TNC cost per ride is lower than paratransit. And therefore it would, I mean, for example, in Boston where they've done a pilot, I think they had lower costs. So is it necessarily true that using TNCs would result in higher costs?
I was referring to the costs for the agencies. So to address your first question, with the privacy preserving security, we were thinking of using things such as blockchain, which would add some additional costs for the resources. So that is what we were referring to for the blockchain resources.
What about the second question in terms of, in general, I perceive TNCs being cheaper per ride than paratransit. Do you have any information on that?
So generally, because TNCs are shared, and I don't know the exact data, but it seems that it depends on the paratransit agency, because the rides prices can be fixed and or free. And then with TNCs, it's obviously not fixed, so it just depends. So there are times where TNCs are cheaper than paratransit. Does that answer your question?
So I think there's two sides to cost. One is what is the cost that the rider faces, and one is the internal cost to the agency. So I've seen numbers for the internal costs, you know, for typical paratransit agencies, something like $30 a ride, you know, $25, $35, $30, $40 a ride, whereas TNC rides typically are more like 15. So in other words, if you take the same set of trips and shifted them from the current paratransit service to TNCs, my understanding is that it would result in cost savings. But I wanted to know if you had any conversations about that with the agencies you talked with.
Yeah, so you mentioned Boston earlier. So Boston was able to reduce their rides from $32 per trip to about $8 to $12 per trip when they incorporated TNCs. So that reduction can be done. And within California, within our agency's surveys, we did not get perspective on exact numbers for this survey.
So I think that's all. Thank you, Lois, for your nice presentation and answer. So I think, Dr. Merlin, can we free share, or do you want to add something?
So, you know, we finished a little bit early. I think I would invite general questions from anyone to anyone. If anyone wants to ask questions about any of the presentations, if they want to unmute themselves, I think this would be a great time for discussion. If people see connections across the papers. Obviously, we had a couple of papers on weather, which is interesting. So I would just open the floor. Or, you know, if people need to stretch and go to the restroom before the next session at noon, I understand that as well. So I don't see, oh, someone wanted to, go ahead. Bhushan, unmute yourself if you can.
Oh, okay. I just wanted to ask in the first and probably second, how do we get this data from Uber? Is it available somewhere, or we have to buy it?
So I think that question goes to Dr. Shokoohyar. Well, I don't know if he's there.
Yeah, I am unmuting him. So let's see. He's here, but probably he don't hear our question.
Can anyone here answer that question?
Well, I thought that the data that was used in that study was scraped from an API.
Yeah, that's my impression as well.
So you just need to program it and scrape it. If you're looking for actual, the usage patterns, the only place that I'm aware of that has the data for free is the Chicago database, but there may be some others I'm unaware of. But generally, they don't make this data available.
Right.
Okay.
So the first study was looking at what is the cost and what is the time to pick up, which you don't actually have to book the ride. You just have to request the ride, which you can request through the Uber and Lyft both have APIs where you can request rides. So they just kind of threw all this API data requests at the APIs and scraped the data that way. That's my understanding. So it wasn't actual rides. It wasn't actual rides. It was, I guess, hypothetical ride requests.
Okay. Thank you.
I see a question for me in the chat box, and the answer is no. The question being, is there any East Coast e-scooter data available to look at different weather patterns? And I'm not aware of any that's available right now. We will have some here at Rutgers, hopefully within a couple years, because we have a system coming in the fall. So it'll be mainly students using it. So a little different context, I think, and we'll also have e-bikes to look at.
So if I could also answer that question, I believe Austin actually posts trip data. A lot of other cities don't post trip data, but they post scooter availability data from which you can infer trips. You can, based on when the scooter ID changes or disappears or appears, you can infer trips. And some research has inferred trips based on just the availability APIs.
Good morning, everyone, and good afternoon from those who are farther east, including me. So I'm Karishma Choudhury from University of Leeds, UK, and I also have Jason Hawkins from University of Toronto, who is the co-moderator of the event of this session. And so I think we have our first presenter, but we may want to maybe just wait another 1 or 2 minutes in case anyone else joins. So the first presenter we have is Shraddha Praharaj from University of Virginia. She is a 4th-year PhD student working with Dr. Donna Chen. And her research interests include data mining and machine learning in transportation engineering data sets and integrating crowdsourced data to improve transportation analysis. And her presentation today will be on estimating impacts of nuisance flooding on roadway networks, a Norfolk, Virginia case study. So Shraddha, the floor is yours.
Okay, so good morning, good afternoon, and good evening from wherever you are in the world. My name is Shraddha, and I would be talking about a data predictive approach to quantify the recurrent flooding or nuisance flooding impacts on the road users with a case study in a city in Virginia, Norfolk. Okay. So nuisance flooding or recurrent flooding is a type of disruption that has become more prevalent in coastal cities in the past few decades. Usually is a result of heavy rainfall, high tides, storm surges, and the cities or the state's drainage infrastructure not being adequate to remove all this water in time, thereby causing the flooding. With climate change and sea level rise, this problem is expected to be far more frequent, as well as not just stay in the coastal cities, but also propagate to more inland cities as well, with more riverine flooding, etc. To look at some statistics in the coastal communities, this is a screenshot from one of the reports from NOAA, where there were about 30 coastal cities just in the East Coast alone, which experienced more than at least double the number of flood days per year in 2010 to 2015 time period as compared to that in 1950s. This a little predated for now, it's already 5 years past, and a study by US EPA said that the frequency of flood events has increased by 75% just in the Northeast Atlantic coast between 2000 to 2015. And it has increased by 125%, a lot more in the Southeast Atlantic coast. A study by Jacobs et al. From FHWA has said that in 2018, there was anticipated 100 million vehicle hours of delay on all the highways in the East Coast states alone. And although this 2020, the 160 million vehicle hours of delay projection might not be true with respect to coronavirus, but that was what was projected. And with all the climate change and sea level rise, this was projected to be at 1.2 billion vehicle hours by 2060. The prior studies that we just looked at have always mentioned projected data from different hydrological and transportation related forecast models and simulations. There is a lot of research that is also done with non-simulated data or real data, but they usually pertain to high impact and low frequency events such as earthquakes or hurricanes. The problem lies that there is no real data when it comes to something like nuisance flooding, which is a lower impact, higher frequency event. It happens probably a lot more frequently, but it's not big enough to, as a hurricane, to actually cause major disruptions. The problem with not being able to analyze the observed impacts for nuisance flooding is because we don't have enough data, empirical data from agency data sources that could tell us how the traffic has changed or which roads are getting impacted. That's where our study comes into picture. I don't think I'm controlling my screen, but I'll just keep coming back in case this is being a problem. So this is where our study comes into picture, where we are trying to integrate hydrological and transportation data sets to estimate what the traffic volumes on the roadway could be on a flooded day or on a non-flooded day, and in comparison to see how flood days get affected. Okay, so on the x-axis, we have the spatial coverage, which goes from low to high. That is any data that is collected at one location in the city, being a low spatial coverage, or if the data is collected at every location of the roadway network, it would be called as a high spatial coverage. The temporal resolution, low temporal resolution, implying that the data is collected once in a day, and high temporal resolution, implying that data is collected at every minute of the day. Now, coming to some data sets that we look at, we have hydrology data, which includes a tide level data, which is collected at one point in a city every 6 minutes of the day, thereby being on the top left corner. And we have rainfall data, which is collected at a few rain gauge stations installed by the city, which is collected at every 15 minutes to half hour of the day. We then have the Department of Transportation's continuous count station data, which essentially collects the traffic counts in certain locations in the city. We also have some flooding data, which is the City of Norfolk flooding data, where the city officials go out and collect where the flooding occurred, and they put in a date stamp into their records. We have the roadway features, which are like number of lanes with lane, which are collected from the Department of Transportation as well. We have streetlight data, which is a new crowdsourced data set, which essentially gives us which essentially gives us what the number of cell phone pings that are observed in each roadway network. And these are collected by active cell phones, which record the location-based service apps. And thus it converts it into traffic counts, which could then be converted into traffic volumes. It is only as comprehensive as the number of people who are able to use these active location-based service cell phone devices. We also have Waze flood incident data, which I would be coming to a little later. So to look at the study area, we have the city of Norfolk, which is a coastal city in the state of Virginia. It has very low elevation and is very frequently affected by coastal flooding, almost about 40 to 50 days per year, and thus is used as our case study area. We also only analyze the links that are shown here in blue because we have data only pertaining to these links and not all the entire roadway network. We built a data predictive model for the traffic volume estimation. We integrate the roadway characteristics data, some traffic volume data, and some hydrology data together in a data predictive model, which would give us volume estimates on a flood day and on a non-flood day, which we could then compare to show what the impacts are faced by the road users on a flood day. To look at this model in a little bit more detail, we have some roadway characteristics such as the number of lanes, the speed limit on the roadway, and the per lane capacity. For traffic flow, we have trip counts or the cell phone pings that are collected through streetlight, the speed, the time of day, and the type of day that the flood day is. We have some hydrological data, which are the rainfall data, the flooding report data, and the tide level data, which are also put into a few different data predictive models that we try out, which then gives us the volume estimates, which are calibrated by the Department of Transportation's traffic count volumes, which are used as our ground truth as well. When we run through a few different models, we found that the random forest model, which has these roadway, traffic, and hydrological characteristics, gives us the least amount of error, as well as has some of our dynamic variables show up as the high importance variables, such as the trip count, the time of day, and the speed limit and per lane capacity on the roadway. So we use this on the city's flood data that we acquire from the City of Norfolk employees. And in the 20-month time period, there were only 10 days that got recorded in the entire city being marked as flooded. When we look at the change in travel on a flood day as compared to a non-flood day, we find that on an average, there is a 3% decrease in travel. And this is directionally consistent with the change in volume on the ground truth traffic counts from the Department of Transportation, having a 12% decrease in volume and a 6% decline in speed. When we look at how these change in travel happened with the rainfall or the tide level, we find that the rainfall actually has some sort of trend going on, which we cannot see in the tide levels. The reason why rainfall might have a trend, even with so less points, might be because rainfall is more spatially uniform throughout the city, and thus people might make travel choices very similar in different parts of the city. However, when it comes to tide level, it might be that the roads which are closer to the coast would get more affected with flooding than the others. Thereby, the impact might not be seen on an overall citywide scale. So from this first part of the study, we see that this methodology that we used is not able to distinguish the spatial heterogeneity of flood impacts, just because one, we use travel, if you heard me before, which includes traffic volumes and speed in VHT, which might have a compounding effect. It's also aggregated, this VHT is aggregated across the entire city's roadway network, which might not give us an idea about which areas are getting more impacted than the others. And thirdly, we have this agency reported flood data, or the City of Norfolk flood data, which is only as good as their employees record it, which has low temporal resolution because we only get what day there was flooding occurring, and the spatial coverage is only where the city employees could actually go and report a flooding. So to improve on our citywide impact analysis, we move on to localized flooding impact analysis so that we could look at smaller regions, how they are impacted due to a flood reported at a specific point in space. Additionally, we change our agency flood report data to include a more robust incident reporting crowdsourced data called Waze. Waze is a traffic navigation app which also has an incident reporting component to it. So we use the incident reporting, which are reported as flooded, as is, and do not perform any analysis on it. So if anyone reports a flood incident, that we take it as a true flood report and do our analysis. We change our traffic volume estimation procedure a little bit to accommodate for the space as well as the new data set that we are using. We first changed to crowdsourced flood incidents, which now have a space and a timestamp. So we need to find the rainfall at these exact locations in these exact times. So we interpolate our hydrological data, as well as when we go to the localized spatial boundary selection, we use a different procedure to find what a boundary should be instead of using an entire citywide impact. And then we perform the same data predictive model for volume estimation. And we use the flood impact estimate, which would be done only on the localized impacts. So to do the localized spatial boundary selection, we use a graph theory term called hub dependence. It is the ratio of the traffic borne by the highest traffic volume link among all the links connected to the node. So a lower hub dependence value for a node implies that it is a strong node and thus is less vulnerable to an impact. We find first the hub dependence, which is for each node, and then we find the hub dependence for each node, and then we see if the hub dependence value is greater than the previous node, then it gets included, or else it gets rejected. So the boundary stops when there is no lower hub dependence in any direction from the starting node, the one that is in a blue circle as shown in the picture. We use the same methodology that we did in the citywide analysis. However, we do that inside the hub boundary, and we find how the impacts occurred for weekdays versus weekends, as well as for different time periods. We find that weekends do not have enough significant change, and thus I have not shown it in the presentation. When we look at the travel impacts on weekdays, we find that the evening time periods, one between 3 p.m. to 6 p.m. and the other between 6 p.m. to 12 a.m., actually has higher significant changes in terms of volumes, VMT, and some for the vehicle hours traveled as well. I focus in on the 3 p.m. to 6 p.m. time period, and I look at how what the percentage volume increase was in these links on a flood period as compared to a non-flood period. The links that are marked in orange are the links that experience the highest decrease on the flood day, and the ones with blue represent the highest increases during the flood period. When I'm plotting it in a spatial manner, we see that there are some links which come up as significant. The one being here, which is marked as I-64, is one of the major interstates that goes through the city. It experiences a major decrease on the road. It experiences a lot of decrease in traffic in the 3 p.m. to 6 p.m. time. And the other thing to point out is Hampton Boulevard, marked in the top left corner, consists of a tunnel that connects two important parts of the city, experiences both increase and decrease corresponding to different times of, corresponding to different flood events that got reported. We also look at how the most impacted links are distributed by the road facility type. And we find that the principal arterials experience more increase, principal arterials experience more increase in volume than the number of links that face a decrease. However, the interstates have experienced more decrease than increase, thereby saying that there is lesser travel going on in interstates, and there is more travel in the arterials, in the principal or minor arterials. When we do this overall comparison across all the ways reported flood events, we find that on an average, there is still about 3% of VHT decrease. However, this 3% could not be compared to the previous citywide analysis, because now we have more than 100 reports that were assessed, implying that this change is actually heterogeneous in over space as well as time. We see that there are high VHT and high VMT decreases observed during the evening and the night periods. And thirdly, there are also more traffic increase seen in arterials than on the interstates, which could be due to either a shift in travel choices, due to the access controlled nature of interstates, which might give less flexibility for people to go in and out of interstates, thereby preferring arterials. To conclude on the overall study, we find that the citywide level of analysis is not comprehensive in showing the true nature of nuisance flooding events. These disparities in space and time are better explained in our localized flooding impacts. There are some trends, such as the evening periods getting more impacted than the morning periods, could be helpful for the city officials to concentrate on providing mitigation efforts to particular hotspots in these time periods. One of the limitations in our study that we use is that we use the ways reported flood events as is. That is, we perform no truthfulness or trustworthiness analysis on it to identify the correct reports from false reports, which would be done in our next study. And by the end of this study, we hope to provide some real-time decision support to reroute the traffic during flooding, so that people are not stuck in more vulnerable locations. In the end, I would like to thank all the agencies that provided me with the data and all the co-authors, and I would be happy to answer any questions.
Okay, well, thank you, Shraddha. I think we have one question in the chat window, and if you have any other questions, anyone, just post them in the chat window. So the first question is, what is the temporal aggregation of your predicted traffic volumes?
The temporal aggregation was divided based on the travel demand model. So there are 5 different time periods the peak hour periods are 3 hours and the non-peak hours are non-peak periods are 6 hours.
Okay. Does anyone else have any questions? I don't see any in the chat window. Okay, well, if no one else has a question, I have a question.
Yes.
So during my undergrad, I actually, I don't do anything in hydrology anymore, but during my my undergrad, I worked for one of the highway departments in Canada, and we actually spent more time than I expected doing hydrology. And so my question is actually, you've applied this in a city for flooding events associated with coastal events. But I'm just curious, I assume that it's equally applicable in rural areas or in areas affected by river or sort of general precipitation flooding.
Yes, I think in theory it is. One of the problems that I had was that I couldn't get enough transportation related data. So if you see I don't know what has been happening to my presentation, but if you see here, like in the background, there is a much bigger grayed out roadway network, which is essentially the entire all the city streets included. And I was only able to get data for the major minor arterials, major collectors, and the interstates and freeways, just because the cities have more data about the geometric design of the roadway. And as we go to more rural or more smaller roadways, those kind of data is missing. So like doing an analysis becomes a little more trickier in that case. But in concept, it should be possible to do it.
I don't see, oh, there's another question. Okay, so Charisma is wondering, is there any accumulation effect? So for example, is there flooding events over, say, the past 7 days? Does that make a difference compared to the first day of flooding? So I guess sort of.
So I think the way I was trying to not make that accumulation effect. So when I was comparing a flood day versus a non-flood day, first I just used whatever day was reported as a flood day is considered as a flood day. So if someone reported that August 10th is a flood day, I just could consider that that is the only flood day that occurred because I don't have a report on August 9th or August 11th. And to remove the effect from the non-flood days, what I had done was to remove the first, the 4 days prior and the 4 days after the event was reported, and then did a search in like 3 weeks before and 3 weeks after to find out what an average non-flood day would be, so that there is no impact of this storm, even if it was a storm, to not have an impact on an average non-flood day.
So she has another sort of related question. Also, is there accumulation of multiple events? So for example, a storm and a flood event sort of occurring simultaneously?
Yes, I think I do not answer that question in my analysis, but I think because we did not have enough data from or enough information about the flood events, it was not possible to find out if it was like the first day of flood and if it was like a few other storm events were accumulated together. But hopefully, I think with other people who work on this project from the hydrology side, maybe there could be a way to address that. It's a really good question.
Great. Well, if there aren't any other questions, then maybe we could move on to the next speaker.
Yeah, that's me. Perfect timing, you guys. So I was in a different session this morning, and of course, I think my co-author's name is still highlighted as the presenter today. But Ty is quite busy with her work. She works at General Motors here in Austin in their Innovation Center, and so this is one of 2 papers she wrote as a master's student while here at UT. The other was about electric buses with smart charging en route, and so that's also at my website if you'd like to see that. This one was about the land use impacts, really, of having autonomous vehicles, and so we used Rolf Mokel's silo model, which is simple integrated land use orchestrator, and he, I think, developed much of that while he was here in the US and applied it to Maryland, and has been trying to make it more user-friendly. It took a few students before Tyler was able to sort of crack the code and break through the wall and take his Maryland application to the Austin setting and play around really with travel times and vehicle occupancies to try to reflect what might be the case for the future of autonomous vehicles. And so the 2 big scenarios that we ran here are private ownership of autonomous vehicles, and then mostly a shared fleet of autonomous vehicle options and higher ride sharing en route with strangers. Okay, so that's called dynamic ride sharing. Ride hailing is where you call a shared vehicle, but to share it en route is ride sharing. And so that a lot of journalists have misnamed Uber and Lyft and Didi as ride sharing, but they're really ride hailing applications, and only if you're sharing en route with a stranger or 2 or 3, as I've done before, then that would be called the ride sharing application. So land development is a scary thing because we already have more than enough sprawl here in the United States, and so by making driving easier, of course, we are expecting more sprawl. And this is a question that some of my students before Ty have asked on their surveys, and to see if we can figure out whether people are going to be more motivated to live further from their work and their other destinations because they can sleep while the car drives them. And we see about 9% of households in the US suggesting that they would probably live farther away in that autonomous future, but we also see about 7% thinking that they would live closer to the city center because they, I guess, expect better response times from the shared autonomous vehicle fleets. And so that was kind of nice that they almost balanced each other. Pat Mokhtarian did a similar question recently in the state of Georgia in the US, and got slightly higher shares of people saying move further and move back towards the center. So there is this centralizing or attractive force of not having to own your own vehicle, right? And that might keep you closer to the center because you're paying per mile, basically, or per kilometer to get in that shared fleet vehicle. And so you're a little more conscious rather than buying this big vehicle and owning it and having it just sit there in your driveway or garage, and where the marginal costs are so small when you actually own it. So we really hope Americans and everybody else get used to the shared fleet application, but that there's also competition among different providers, and that our transit agencies become a major provider. They already have a fair amount of subsidy to help lower income and vulnerable users, people who maybe can't get a driver's license and really need help getting to important destinations. So that's what their customer base is supposed to be. But of course, a lot of us wealthier people use transit too. And in the future, though, I hope that they can contract with other groups to provide these services to make sure that everybody has access and that the vehicles are efficient and right size and that those seats are filled. So I'm just going to talk about the land use modeling impressions that we got from this particular tool. And it makes use of the public use microdata sample in the United States. So as I mentioned, Rolf Mokel had applied it in the Maryland area, and we went ahead and needed to apply it to Austin, Texas, which is a 6-county region with about 2 million people in it. And so we were using a synthetic population as well. Luckily, there is a public use microdata area or region here in Austin. And so we used that sample to create these synthetic households across the region because you can't get that kind of individual level data by location. So we had to apply it at the level of census tracts or traffic analysis zones. And there's a few thousand of them here in Austin. And so we needed to know, age and gender and job location versus home location. That's really important for a land use choice model. Of course, the location of your school or your children's school is also very important. Maybe your dentist, maybe amenities like rivers and parks, things like that, also very important, but mostly ignored in the silo model, which is working at the level of individual households. So it's microscopic in that sense, but it really focuses on the job co-location for workers. And it looks at, what land is already developed here in the Austin region, because that will be probably on nice central parcels, but more expensive to get a redevelopment permit for. And so a lot of the new development is on greenfield, undeveloped land. And we also need to understand travel times. So in addition to running the silo model, Ty went ahead and ran MatSim, which is also by Europeans working in Europe at the time that they developed that. So Kai Nagel is the one who's now at ETH Berlin, I believe, who created the MatSim model. And Rolf, who's also in Germany, I believe, wanted to make sure that these two could talk to one another. So they're both in Java. And the first thing that Silo does for us, thank goodness, is it helps with the synthesis there. It also has demographic modeling for the evolution of those households. So they're getting older, they might be getting divorced, hopefully they're getting married, maybe having a couple babies each, this kind of thing. But of course the children eventually flee the nest or leave the nest grudgingly to go off to college and have their own lives, these kinds of things. And then there's the construction, renovation, demolition. So you can have brownfield development, of course. You can also expand existing building stock, but it's really on the residential side. So Silo is still very focused on the residential side. So any of you graduate students out there who want to do land use modeling, this might be a really nice model to look at to include the commercial side of things. It's open source, which is wonderful, a wonderful gift that Rolf and Kai have both given the world by making their code open source. And so I think Rolf would love the help and the interest and in the household relocation as well as the business location. And you have new households arriving, maybe from California where land prices are so high. I grew up in California, and we do have quite a few people moving here. I think Elon Musk also has just decided to have a new fabrication plant in the Austin region. And part of that is because the folks in Fremont, California, would not let him go back to work at his Fremont factory. And that was very frustrating for him. And so a lot of businesses like Texas, because we're more lax on those kinds of like COVID and other regulations. But the final step is that travel demand model. And like I mentioned, the demographic model is pretty complex, and this was not something we wanted to have to assume. So we're glad that Rolf has done that work for us. And the real estate model is just updating the residential housing stock. So those are dwelling units for living. And of course, you can move or not move in any given year. It's a 1-year time step on the location and land development decisions. And you're selecting not just a neighborhood to move to, but also a dwelling within that zone. And so in that sense, it is quite specific for the households. The move or stay decision is just a standard kind of logit. It's got utility differences. I've got my cursor showing here. Let's see if I can make this a little bit brighter for you. So this difference in the utility of location J versus location I, where you presumably already are living, and we've got an inclusive value, or a scale parameter here to take a look at these differences, and those will feed into this move decision. So you're looking at all of the possible destinations for your household. So just that move decision, taking a look at all the possible destinations and then making that move to where decision on the the new neighborhood J, if you do pass this first threshold, this first sort of marginal decision, then you've got this next decision. So you've got a joint decision between the two of these things. We're looking at how attractive the availability of homes in that new zone. So these are people who are, I guess, moving and they're making their building stock available, or it was already unoccupied building stock is becoming available. And it's a function of the accessibility of the location. So N, I guess, is just subscripting the zone, and then some of the environmental factors also in that zone, and that might be amenities such as the lake I was talking about, or the parks. And then you get to make that dwelling unit decision. Of course, the dwelling unit has to sort of be unoccupied or almost unoccupied in that year that you're moving. And so this has to do with a time budget and a commute time. And so TB is time budget, CT is commute time. There's some other things that go in there. PD is the price of the dwelling, so it's a very big factor. This will have a strong coefficient in that exponent. And these are all multiplicative, which you can linearize very easily because utility is not a unit that we can observe. And so as long as you monotonically transform it, generally you won't end up with different preference structures, different orderings of those dwellings. And so I think that's why Rolf went with a multiplicative structure there. There is a big income versus home price trade-off. And so this is sort of some of the data that Rolf was using from Merlin suggested that these lower incomes, the share that they spend on their household for the mortgage or the rent payment, depending on whether you own or rent, it can be pretty severe at the low income levels, and less of your household income, I think, at the higher income levels typically. And so this is the utility of the price of the dwelling, that PD subscript. It has to do with these household shares. And so this is something that empirically Rolf determined. This is a pretty big category that's greater than 60,000. I think over half of US households may qualify for that. So it would be nice to see some more of these trade-offs in here for the more refined, I guess, decision-making. The worker locations, as I mentioned earlier, really important, not the school locations, although school quality can certainly impact those utilities. And these work trip lengths are really centered on these blue dots. So this is the first scenario where there's only one worker in the household and he or she works in that central blue dot. And this is just a map from the Maryland region. So this is the Atlantic Ocean. I guess this is Washington, D.C. area, where these lower probabilities of a person residing in these other zones if it's a one worker household with the worker at the center there. Of course, if that worker works here, then there's a different map for those probabilities and based on all sorts of other things that are going on there. You can see the District of Columbia, I guess, here with this almost a diamond shape. We're missing the rest of the DC location here. So it's not a state, it's a district. And it's where you would head if you were headed to the Transportation Research Board meeting. And of course, they are one of the co-sponsors of this conference. So I hope maybe we'll see you there one of these days. This coming January, of course, that's going to be a tele meeting, so because of COVID, but maybe in year 2022, we'll all be physically together. If you have two workers in the household, there's competition, and of course, locations in between those two job locations are very attractive to those households because you've got joint decision making between the two workers, presumably. And so that's just another example. I'm not sure if 3-worker households are permitted, and maybe that third worker is not such a professional that it would be that important. He or she may be a young person picking up a kind of a temporary or part-time job, and so it might just allow up to 2 workers for these decisions. And then there's the commute time and cost trade-offs. So we've got discretionary income for the household H. We've also got savings. So not too many Americans save well, I'm afraid, but as long as that's less than your travel cost, which has been amplified, I believe, because generally household income and savings are going to swamp your travel costs. And that, I guess, would suggest a travel budget utility of 0 for that particular household. But if you've got it going the other way, once you've scaled it, then you get this sigmoidal function on expenditures, or yeah, I think that's discretionary income, excuse me, and how savings by the household divided by this TC term, which has presumably been scaled. So that leads to some interesting dynamics between incomes and expenditures. And this is after tax income on the x-axis, and housing expenditures and non-fuel transportation expenditures. Energy is very cheap in the United States. Energy is quite cheap, actually, in many parts of the world, and especially on gasoline in this country. And we've really dropped gasoline prices in part because of the fracking revolution. So the U.S. has become a major energy provider and almost a net exporter of energy because of the fracking technology that was, I guess, perfected here in the U.S. And we're finding just tons of, unfortunately, fossil fuels under the ground. So the price of a barrel of oil has dropped, and that's very, very scary for a lot of people in the Middle East, where it undercuts a lot of the incomes. Of course, very tough on Venezuela and other countries. So it's just this little strip here. I have an electric vehicle now. I have a hybrid electric vehicle and a battery-only electric vehicle. So my little green bar is going to be even lower. I get 5 miles per kilowatt hour, and I pay about 10 cents per kilowatt hour. So pretty amazing on a Tesla Model 3 with the smaller battery pack. And here's some savings in this case, but down here you can see there's not a savings that these people are dipping in to maybe loans and that kind of thing, and to be able to pay for their housing and their transportation expenditures. So there's other factors, of course. There's home quality. That's very important. How old is the home? How has it been maintained? There's transit access and automobile access to jobs, and the school quality, as I mentioned earlier. Also, crime rates were used here. Austin really doesn't have much crime, but there are certain neighborhoods where it can feel scary, and there may be certain types of crime, not violent for the most part, thank goodness. But it leads to some pretty long utility expressions in this very, I guess, economically rigorous approach to studying this very complex problem of how all these different players navigate and outbid one another for homes and locations. And it's a very, very complex, and Rolf tried to really focus in on that decision making. Here's all the zones, these little green lines, these numbers here, I forget, these might be like census tracts or zip codes, but they're almost like counties, practically. These are very big. They're holding a lot of traffic analysis zones, and I'm sorry we have the numbers on there. They're distracting, they're not relevant. We're running the land use model every year, and then the travel demand model every 10 years. Ideally, you'd run that more often, probably every 5 or 3 years if you could. And I know many of my students could do that, but this was a lot to ask of a master's student, quite honestly. So it was just amazing she was able to run both of these agent-based models. And she ran it for a 27-year period because her base year was actually an odd year. It was 2013. And of course, autonomous vehicles were not available in 2013, and they're not really available right now. But she used that base population and job locations, and then just moved it forward to a nice rounded year. So if you start in 2013, you add 27, you're in 2040. So she wanted to see what things might be like in 2040, but I really think this is more like a 2050 or a 2060 sort of evolution, because we did assume that autonomous vehicles were available in that first year, and there wasn't some growth in it over time. So it was really a big shift from a business as usual, where there were no autonomous vehicles over this 27-year period, to a future where a lot of households were gifted basically a private autonomous vehicle to own, and we assumed that brought their value of travel time down by about 50%, especially for the driver. That might happen, but it's pretty generous to reduce. So that's kind of a maximum sprawl case. You can imagine if nobody's really relying on those shared autonomous vehicles that are attractive to many households, but they've really been given a lot of private AV access, and everyone, including the passengers in those cars, are feeling they're not paying attention to the travel time as much. It's only about 50% is burdensome. And then we wanted the third scenario to be different. So we said, let's call this the shared autonomous vehicle scenario. Let's not reduce their value of travel time as much because it's not their car. They're going to be in a shared fleet most of the time. And hopefully they'll be sharing with others. So we brought their vehicle occupancy up from about 1.2 persons to about 2 persons. So you still may have half the seats not filled in that 4-seater shared autonomous vehicle, but it is about 60% higher vehicle occupancy, so that does get rid of a lot of excess traffic. So they might be driving more because it's an autonomous vehicle, right? So they've seen a reduction of 25% in their value of travel time, so they've got about a 75% of their original value of travel time. And of course, these vehicles don't really belong to them, so they're paying per mile, and they're also sharing the rides to get that average vehicle occupancy up to a 2.0 level, 2 persons per vehicle. So 2 person miles per vehicle mile. Sometimes you've got 4 people in there, sometimes you don't have anybody in that shared autonomous vehicle, but on average, you have 2 persons in it. And interestingly, Silo is very focused on a peak time of day, and so you're seeing this very simplistic sort of peaking over, I guess this was a 30-hour run period or something, a number of people on the road, how many are en route, very simplistic. This is not what real traffic diagrams look like, although for the work trip, you know, a lot of people leave in the morning and come back in the afternoon, but some people leave at night and some people leave midday, and that just won't happen if you're using the current version of Silo. So we'd love to see somebody working on that if you need a topic for your thesis. And I also mentioned this, it's focused on residential, so those commercial locations are exogenously given. That's a big limitation right now. And we didn't have time to re-estimate all of the parameters that are needed in this complex model, so we imported quite a few from the Maryland applications that Rolf had done. And we're not really focused so much on the number of people living in a particular zone in a particular dwelling type, but really the percentage changes over time, because, you know, these are all models, these are all abstractions of reality, and we are borrowing some parameters for this application. So here's a lot of results, as you can imagine. As you make driving easier, you make travel easier because your value of travel time burden has fallen, you're seeing the travel times rise. Versus the business as usual. So of course, travel times are rising if we're keeping the networks pretty constant, and we're adding population, a lot of Californians, let's say, moving to Texas. And so the business as usual in the future year is going to definitely have a higher travel time. This work travel time is, I think, maybe outside the city of Austin. This is a very high work travel time. Even today, I think it might be closer to 26 or 27 minutes today. So Rolf's software is loading all of the workers at the same time, but none of the other trips. So you would not expect this to be as high as it is. And then if, of course, now it's going to be higher without AVs, just due to natural population increases and sort of shifts in location choices over time, maybe to bigger homes. We've seen that certainly in many countries over time. And then when we reduce that value of travel time and give a bunch of people autonomous vehicles, essentially, we see the travel times get worse, although people aren't noticing it. They're thinking, because they have a 50% lower value of travel time, maybe they're thinking this is like a 21-minute trip, not a 42-minute trip. And if you put them into higher occupancy shared autonomous vehicles and don't give them as much of a value of travel time reduction, you might get up to 40 minutes. So not a big change over between these 3 scenarios, the no autonomous vehicle and the autonomous vehicle scenarios. But again, this model is very focused on the work trip. And those who live inside the city of Austin, you're seeing their numbers go from maybe a 26 minutes to pretty much same thing. So they don't see much of a difference if they're inside that city, which is almost 1 million people. So almost a half of the region lives in that inner city, which is almost 1 county of the 6 counties. And even versus today, let's say, not a big change 27 years forward, according to this model. But if you live outside the city of Austin, so you live less core, then there is maybe a lot more driving going on those networks. And so that's kind of noticeable. That's a 20% increase. And there are people who are going the extra mile, let's say, with a 60-minute or longer work trip. That'd be about 30 miles or longer work trips, taking 60 minutes or more. And so those numbers do seem to jump a bit. They're not the bulk of this 2 million person population or 1 million worker population region, but that is a scary thing to see the tail of that curve. And this is that tail right here. This 60.
Dr. Kockelman, we're just over 20 minutes.
Yeah, no, in my other session, everybody was too short except for the first speaker. So I'm so sorry it's taking me longer than I expected, but I think we'll be good.
No, okay, perfect.
This is just more of the information on, like she zoomed in on these traffic analysis zones. They get very small in the center of the city. So this here is the city of Austin. These are the 6 counties. And these are just differences in counts, whether they're higher in green or lower versus the business as usual scenario. Mixed, but we do see mostly red or orange in these inner neighborhoods, but we do see some red and orange spots up here where they are losing households due to the SAVs, even though these look very peripheral to you or me. So to summarize, the travel times did rise because of the AVs, maybe just 3% if you've got the SAV with the dynamic ride sharing and route scenario, or maybe 8% if it's really a private ownership model in the future. 27 years of autonomous vehicles, so it's not horrendous. I think credit-based congestion pricing and other techniques can definitely impact this, and forcing, I think she allowed vehicles to follow more tightly in these far-flung futures, so the auto manufacturers were asked to follow at tighter headways, at least on the highways. In the extreme commutes, we did see big jumps there, but again, it's just a small segment of the Austin population, thank goodness. And we did see fewer households living in the core city, maybe 5 to 6% in this big city of Austin, which has half of the region's population. And then finally, about 24 square miles or 9% of the city's residentially developed land in a non-autonomous future would actually be outside the city boundaries in that autonomous future, but maybe not a lot more land developed in total for residential uses. So that's the end. I haven't been checking the chat box, but Jason, maybe you can let me know what questions exist.
Yeah, so we have one question from Pedro. How might the results be affected by not modeling the non-residential location endogenously? He says, by that I mean non-residential externalities affecting location patterns of households as well as the non-residential mobility.
Yeah, so my guess is that Ty used the Metropolitan Planning Organization's future land use patterns for those jobs, and those will be affected by AVs. I think they will often be farther flung than they currently are because of the AVs allowing, some of their workers to feel like, oh, I'm not going to be so worried about the long commute, and that will have an add-on effect to that sprawling component that we're not able to pick up with silo. I'm not sure about externalities per se, except for that agglomeration, economy or diseconomy in some cases. So if Pedro wanted to be more specific about that, I might be able to address it.
Okay, and we have another question. How are housing price changes handled in the relocation model?
Oh yeah, so those are all updated, and they're practically at the level of the unit. So that's one of the really nice features of using an agent-based model. It means that there's a lot of simplification on the commercial side right now, and on the travel side, quite honestly, as you saw with those 2 simple bumps for work work trips. But I do think the prices are every year allowed to kind of re-equilibrate in this stochastic, but econometrically driven fashion.
Oh, so we have just a comment, and we'll wait for it to come. Urban Sim might incorporate these features like housing price and job location choice.
Yeah. So I have used Urban Sim in the past, but there are a lot more parameters involved. So I was counseled to try Silo because it would be much easier to develop than Urban Sim. As it turns out, it took years for us to get Silo off the ground. There's no great documentation or anything. So we had to work, it was very scary for the students who tried it, and 2 failed before Ty succeeded. So in retrospect, yeah, I think I would try Urban Sim the next time on this.
Okay.
Thanks, you guys.
Okay, so the next paper is on investigating the impact of residential relocation on vehicle ownership and commute mode choice. It's a case study of housing schemes in Lahore, Pakistan, and it will be presented by Mamuna Fakhar. So she is currently working as a transport consultant in Lahore Development Authority in Pakistan, and she actually did her master's with me at Institute for Transport Studies, University of Leeds, and the paper is based on her master's work.
Oh, hello. Can you hear my voice?
Yes.
Okay, let me share my screen. Yeah. Everyone, my name is Mamuna Fakhar, and I'm working as a transport consultant and government authority in Pakistan. Today, I'd like to present my research, which I co-authored with Dr. Karishma at Institute of Transport Studies, University of Leeds. I'm glad to get a chance to present my research in this prestigious conference. This presentation will focus on investigating the impact of residential relocation on vehicle ownership and commute mode choice behavior in the Global South. The outline of this presentation includes a brief study background, aims and objectives, the methodology I adopted for this research, data collection and analysis, then the model structure and model estimation. Lastly, the conclusion and direction for future research will be explained. Residential relocation is an important event in lives of many individuals and families. It affects the vehicle ownership and commute mode choice behavior of the individuals and families. A growing number of studies around the world have been devoted to find the effects of residential relocation on vehicle ownership and behaviors of travel mode choice. But most of these studies only focus on developed countries. However, in most of these studies, these are not transferable to developing countries because of different traffic conditions, different socio-demographic characteristics, different social behaviors, and family characteristics. For example, a motorcycle is a popular transport mode in developing countries for making short and long trips, but it is uncommon in developed countries. For this research, I selected Lahore as a case study area. Lahore is a provincial capital of Punjab and second largest city of Pakistan. This mega city has a share of over 11 million population in the total population of the country. As you can see in the map, its location, if you can see here, it's adjacent to India-Pakistan border. In developing countries like Pakistan, the importance of measuring the impacts of residential relocation on travel behaviors has been neglected, especially due to the development of new housing areas. As Lahore is confronting many urban challenges due to rapid urbanization, which mainly include urban sprawl, housing shortage, and urban connectivity. Lahore is growing due to new housing developments on outskirts. Here, for a new housing development, the common and the official nomenclature, which in Pakistan it's used for the housing development, is basically a housing scheme. So in my whole presentation, wherever I talk about housing scheme, it means the new housing developments or a housing area which is developed. So in this map, as you can see, which is showing the growth of this city in every decade, where the yellow color is showing its urban expansion in 95, and then the blue one is showing its expansion in 2005, and the red color is showing its expansion in 2015. This urban expansion is mainly towards south and southeast direction. The development hindrance towards north and northeast is because of a presence of a river on a north side, and on a northeast side, the presence of India-Pakistan border. Due to this growth, the vehicle ownership level is increasing, and people are preferring private travel modes for commuting. So actually, in results, the number of motorized vehicles are increasing day by day. According to recent statistic, out of all travel modes in Lahore city, 66% are motorbikes and 25% are cars. This research will fill this gap by developing model for Lahore city to predict the impact of new housing schemes on outskirts of the city on vehicle ownership and mode choice behavior. In response to such situation and inadequacies, this study attempts to develop a framework on quantify the relative impact of residential relocation on travel behavior compared to other influencing factors, such as household size and household income. There are two main objectives of this research. Number one is to understand the relationship between residential relocation and vehicle ownership. And number two is to identify the impact of residential relocation and vehicle ownership on commute mode choice behavior. The methodology adopted for this research includes the aims and objectives, literature review process, data requirements were specified, and after that, the data collection methodology is formulated by designing a sample size and a questionnaire. Then the household surveys were conducted, and the data was analyzed in Excel. Then comes the model development, model estimation, and finally the conclusion and recommendations. So for this research, primary data is collected through household surveys in a selected housing schemes to identify their travel behaviors before and after shifting to a particular housing scheme. In this case, I have selected 3 housing schemes on 3 major roads along which Lahore is expanding. As you can see in this map here, these 3 roads are the main corridors along which Lahore is expanding, and the new housing schemes are developing along these roads. So I just, as a sample, I picked the 1 housing schemes on each road. While selecting these housing schemes, I tried to select those housing schemes which are not very old and where maximum people shifted to housing scheme during last 5 years, so that they can easily tell their travel behaviors before shifting to the particular housing scheme. From each housing scheme, 30 questionnaires were filled. A stratified sampling technique was used in this study to distribute the sample of each housing scheme equally among 3 stratas. three stratas were basically formulated by considering income-based plot size categories. The sample of 10 households was randomly taken from each stratum, where the surveyors directly interviewed one member of each household. Now, if you can see in this graph, the analysis of collected data shows that majority of the household after residential relocation on 3 or more vehicles. Moreover, this sample data indicate that 78% of households have relocated to housing schemes from different neighborhoods of Lahore metropolitan area, and 22% of households shifted from different cities. Household size decreased after residential relocation, while household income, earning members, and house plot area increased after relocation. In travel characteristics, 47% of households trip increased, and travel distance for 77% of households also increased, which shows an increase in vehicle ownership. However, the public transport usage and its accessibility decreased dramatically after relocation due to an increase in vehicle ownership. The exploration of collected data specifically for the vehicle ownership, it shows that 49% of households in housing scheme gain motorized vehicles, and only 8% lose vehicles after relocation. The distribution of vehicles owned by households show that many families own cars and motorbikes. After relocation, the percentage of households who own both cars and motorbikes are increased from 46% to 60%, and the percentage of households who only own cars or motorbikes is decreased. And moreover, bicycles, this data shows that the bicycles are least popular mode of travel for residents of housing schemes. The data is also analyzed to find the impact of residential relocation on vehicle ownership in perspective of different influencing factors. The analysis indicate that change in socio-demographic characteristics, and in the next table I showed the life events and the travel characteristic after residential relocation correlated with gaining and losing vehicles. For example, households who gain vehicles after residential relocation, 73% of households' income increased, and 36% gained members in a household. Here, there are some also other statistics for the life events and the perceived travel characteristics, which include travel distance, number of trips, public transport accessibility, and the usage. So the data analysis for the commute mode choice in this study, the number of commute trips of households made by different transport modes used to observe the change in commute mode choice behavior of households after and before residential relocation. Basically, in household surveys, the commute trips, travel time, and commute modes for different trip purposes were recorded at the household level, like work trips, educational trips, recreational trips, and religious trips, etc. The data was collected in the form of estimated trips. As you can see in this table, the data was collected in this form specifically for the estimated trips, which then I converted into a numeric number based on some assumptions. So through these assumptions, I get an average number of trips per week per household. So the analysis for the average number of trips per week per household shows that the number of trips per week per household made by cars and motorcycles, private transport, public transport, and active transport were calculated actually to analyze the commute mode choice behavior. Here, from the private transport, I mean it includes rickshaws, private vans or buses, Uber services, and car share. While the active transport, for this research, it includes just walking, not cycling, because cycling is not common in Pakistan. The analysis of this data by different transport modes illustrate that the average number of trips per household made by cars and motorbikes increased after relocation in housing schemes, while the number of trips by public transport, private transport, and active transport decreased after relocation. Similar to vehicle ownership data analysis, the change in commute mode trip made by cars, motorcycles, active transport, public transport, and private transport after relocation are also observed against some parameters, including socio-demographic characteristic, life events, and travel characteristic. Here in this table, I have shown some socio-demographic characteristics. So for this study, the modeling framework which is proposed for this study is to investigate and model the factors that affect vehicle ownership and travel mode changes due to residential relocation. Based on the modeling framework, which I have shown already in the previous slide, the model structures are developed for estimating the changes in vehicle ownership level and changes in number of trips made by different transport modes after relocation. In this study, vehicle ownership model parameters have been estimated using disaggregate discrete choice modeling method based on utility maximization principle. The MNL model structure have included all these parameters, which include socio-demographic characteristic, life events, and travel characteristic. And all these parameters are observed against the choices for change in vehicle ownership that are gaining vehicles, losing vehicles, and no change in vehicle ownership. And for a commute mode choice behavior, to analyze the change in commute mode choice, a multi-linear regression model is used in this study to identify the potential factors that basically affect the number of trips made by cars, motorbikes, active transport, private transport, and public transport after residential relocation. The MNL model has been tested to find the change in vehicle ownership with all explanatory variables, which include socio-demographic characteristics, life events, and travel characteristics. However, few parameters have not been estimated in the model because they have very less or no number of observation in the data. For this model, the confidence interval used is 75% is considered for the MNL model because the margin of error could be high, as for this study, the sample size is quite small. So the results of this MNL model shows that the alternative specific constant in the model shows that all else being equal, there is a less probability of gaining and losing vehicles after relocation. Because many households tend to keep their household vehicle ownership the same. If you see in the socio-demographic characteristic, the model result indicate that household income is positively associated with the change in vehicle ownership. And an increase in household income increased the likelihood of gaining vehicles. For rest of the coefficients are here, like the family events and the travel characteristic. If an example, I can explain that the commute distance also has a positive association with the vehicle ownership level. Householders whose commute distance increased after relocation are more likely to gain vehicles and make more trips. 5 models were estimated for commute mode choice behavior. All 5 models were estimated for all parameters shown before, but only those parameters included in these estimated result table which have a significant value. The first model here presented is a car trip model. For the car trip model, it offers a decent quality of fit and allows for the identification of variables with a significant impact on trips made by cars. So all included variables in this model show significance at 95% confidence interval, while few variables are significant at 75% confidence interval. All the coefficients in the model have expected sign except the relocation coefficient, which indicates basically that the car trips decrease after residential relocation, but the value is not significantly different from 0. The second is a motorbike trip model, which indicate also a decent quality of fit and allows the significance of explanatory variables at 90% confidence interval. The analysis of this model result shows that motorbike trips increase after residential relocation. And additionally, an increase in public transport accessibility reduced the trips made by motorbike, while low public transport accessibility increased the usage of motorbike. The third model is active transport trip model. In active transport trip model, all the explanatory variables are significant at 75% confidence interval, and the negative regression coefficient of relocation here, it attributes of this attribute is showing that active transport trips basically decreased after residential relocation. And if you see the analysis of all other explanatory variables, which also indicate that an increase in household car ownership reduced the active transport trip, as we know that the motorized vehicle ownership always fascinates people to use on vehicles for making short as well as long distance trip. The fourth one is the private transport trip model, and this model, all the variables included in this model are significant at 90% confidence interval. Here the result shows that private transport trip increase after residential relocation, but the estimated coefficient of relocation is highly insignificant. The presence of, if you see other variables, the presence of senior adults and children in a household increases the likelihood of using private transport such as Uber service and car share, as they are more safe, cheap and convenient. The number of earning members here also has a negative effect on private transport trip, as more earning members in a family tend to use their private vehicles such as cars and motorbikes, which decrease the usage of private transport. The last one is public transport trip model. All the independent variables in this model are significant at 90% confidence interval. The model results indicate that public transport trip decrease after residential relocation, as the coefficient of relocation here, it's negative. The number of motorbike is negatively associated with the public transport trips, as an increase in motorbike ownership decreases the usage of public transport, because motorbikes are more efficient in traffic congestion situation. So in conclusion, I would like to say that the findings of this study may help planners and policymakers to understand the household travel behaviors and to formulate more effective land use and transport policy making. All the existing studies in Pakistan are mainly on travel demand management strategies and travel mode choice modeling, which do not quantify the location of residence and vehicle ownership. So this research will fill this gap by developing model to predict the impacts of new developments of city on vehicle ownership, mode choice behavior, and a growing number of motorized vehicles. Thirdly, the model framework developed in this study can also guide the researchers and practitioners of other developing countries who have not quantified the impact of new developments on vehicle ownership and travel behaviors, and are facing the problems of high urbanization, rapid urban expansion, and prompt population growth. Lastly, the future research can also use different models, model forms to estimate the change in travel behavior. Here, like the other model forms include the number one is like the correlation of number of trips of each household with their own vehicles can be identified in future studies by using a probit logic model. Moreover, ordered models and negative binomial models can be used for vehicle ownership and commute mode choice behavior, respectively. A combined model of vehicle ownership and mode choice decision can also be formulated. Lastly, the sample size selected for this research study was very small, due to which a significant number of observations were not available for each factor to use in model. Capturing all the factors in the model with a significant number of observations in the data can give a comprehensive resource in future research. So that's all from my side. Thank you so much for your attention.
Thank you.
Anyone have any questions? Yeah.
Thank you, Marina. Yeah. We don't seem to have any questions in the chat box, other than one person who is very excited to ask a question, but I have the sense probably wouldn't have been of interest. Okay. Does anyone have any other questions? Okay. Well, in that case, thank you very much, Marina, and I think we can move on to the next speaker then.
Yeah, welcome.
Okay, thank you.
Thank you. Thank you.
Thanks, Mamuna. So our next presentation is on, is titled, Can a Standardized Built Environment Indicator Predict Car Dependency? Testing the Mobility Score for Flanders in Belgium. And we have Eva van Inu as the presenter. Sorry if I have pronounced your name wrongly. So Eva basically holds a master's degree in history from Ghent University and a master's degree in urbanism and spatial planning, also from Ghent University. And currently she is a PhD student at Cosmopolis Center for Urban Research at the Vrije Universiteit, Brussels. Again, I think Eva, you have to correct my pronunciation. And her research focuses on car dependency and the relationship with the built environment. So, Eva, the floor is yours.
Okay, thank you. Thank you for your introduction. Can everyone hear me? I'm happy I managed to share my screen, so thank you for the introduction. My name is Dutch, so I can imagine it's a bit different to pronounce. So it's Eva van Eno. I work at Cosmopolis Center for Urban Research in the University in Brussels. And welcome at my presentation, which is titled, Can a Standardized Built Environment Indicator Predict Car Dependency? Testing the Mobility Score for Flanders in Belgium. So first, just a thing I thought it was nice to start with. What I actually am going to talk about is a trending keyword topic from Google from 2019. So as you can see at number 13, 2019, you can see here Mobi scored. I translated during the presentation to mobility score, just for reasons of clarification. But in Dutch, the word Mobi score is used. So, but as you can see here, Mobi score was ranked 13. Over the number 17, you can see the national elections. Number 18 was the national football competition. So Mobi score was more Googled than national football competition and elections. I thought that was nice to know for you guys. It probably doesn't happen very often that we're discussing trending keywords at Google, from Google. But let me first introduce you as well to region I am going to discuss. So we're talking about Belgium. You see the red spot in Western Europe, and Flanders is actually the Dutch-speaking part of Belgium, so which is the northern part. There you have in the center of the country the Brussels capital region, which has approximately 1 million inhabitants, and then you have two larger metropolitan areas. You have Antwerp, 400,000 inhabitants, and Ghent, 250,000 inhabitants, and then there's some 10 regional cities with approximately 100,000 inhabitants, and a lot of smaller, much smaller municipalities. So, but Flanders has a strong, has historically been developed in a polycentric way and has a very strong suburbanization and a strong presence of sprawl. Also worth mentioning that car ownership, that every 2 inhabitants in Flanders, every 2 inhabitants in Flanders own a car. So the mobility score, what is it actually? Well, it's an indicator, a tool that was commissioned, the development of it was commissioned by the Flemish government, more specifically the Spatial Planning Department. It's a standardized built environment indicator, which actually refers primarily to accessibility. Although the name was then, they chose mobility score to name the tool. But the idea is that citizens in Flanders can retrieve from their to-design website the mobility score for any dwelling in Flanders. So if you have a dwelling in Flanders, if you have an address in Flanders, you can check the website and then you get a score. These scores range from 0 to 10, so a high score, close to 10 or even 10, indicates outstanding accessibility on foot or by bike, so by sustainable transport means to a range of basic amenities like schools, shops and services, and also to public transport. So the score combines amenities and public transport. And if your dwelling has a low score, that signifies obviously the opposite. So the goal of the mobility score the goal of the government was to raise public awareness, raise public awareness of the environmental impact of residential choice. So the idea was that to inform or even educate people in a decent way, and that they would be aware that if they were going to move house or if they wanted to buy a house, that they should consider the location, because the location has an impact on future travel, could lead to more travel by car or even to the acquisition of an additional car in the household. So the idea was we want to inform people about that, so that based on retrieved information, so the potential environment impact of travel from a residence, that people could reflect critically on the location of their dwelling or their new dwelling, and that could lead to behavioral change, which could have positive outcomes for the whole of society. So it's really developed as an awareness raising tool. So, and there obviously are quite good reasons to assume that households living in an area with a higher mobility score, that they travel significantly less by car or are more likely to own fewer cars compared to people who live in areas with lower scores. And previous research indeed pointed to that direction, but it also showed that spatial characteristics explain travel behavior only to a quite limited extent. So therefore, our research hypothesis was that mobility score, we think, is indeed associated with car ownership and car use, but only to a very limited extent, and very limited because the reason why and how people travel differ and are influenced strongly by socioeconomic and demographic characteristics and also individual spatiotemporal constraints. But most fundamentally, which is basically the focus of my PhD, is that we also would like to add the layer of a car-dependent society, so that the car-dependent system, the car-dependent system we're in right now has a massive effect on the organization of today's society, even whether if you have a car or not. So that the fact that we have to deal with a car-dependent system also explains why, for instance, also urban residents can show very car-dependent behavior. And one of the goals of my PhD is also to find ways to conduct research that reaches then beyond the impact of the built environment, and it includes that layer of car-dependent system. So the research question that led from that hypothesis was, so to what extent does the mobility score predict travel behavior, and can the mobility score, intended as a tool to raise awareness, actually live up to the alleged expectations? As so far, there's actually no empirical evidence to make the claim that you will travel more sustainable from a household with a higher score than from a lower score. So the data we used, we combined two data sets. The first one is the data from the Travel Behavior Survey for Flanders. It's a yearly survey. We merged data from 2015, 16, and 17 in order to obtain a larger sample. So we had a sample of 3,846 people, age 18 plus. And then we used the GIS databases where the mobility score is calculated from. And that GIS database actually shows, uses for each hectare cell in Flanders, it gives each cell a node and a place value based on presence of amenity, service, and public transport. And then it combines that with the travel diary from the Travel Behavior Survey. And then the score itself is determined by calculation of the expected environmental impact of the journeys from a specific dwelling. So taking mode and travel distance into account and the environmental cost. And so, and what we then did is take the data set from the Travel Behavioral Survey and assigned each respondent a mobility score of his or her dwelling. So as you might notice, there is that the mobility score itself is partly derived from the Travel Behavior Survey, so which could seem that we that we measured the impact of the mobility score back on travel behavior, which is obviously not our intention. We discussed the topic before I was submitting the paper, and we thought we could proceed as we think we have good reasons to proceed with the research as we did, but maybe I can come back to that later in the question and answer part. So here you have an overview, a map that visualizes the mobility scores for the whole region of Flanders. So you can easily detect the urban regions. These are the scores, these are the darkest ones, so with a score from 9 to 10. You can also, the map also nicely illustrates the suburban developments and all the small municipalities that in Flanders. And then I'll move over to the analysis and the model structure. So referring back to the research question, so to what extent does the mobility score predict travel behavior? We tested for two dependent variables. Firstly, car ownership. As we know that acquiring a car has an impact on travel patterns. And the second variable we tested was vehicle kilometers traveled. Because we did that because that obviously has an impact on environment and carbon emissions. In the paper, we also tested for frequency of car use, but I'm not going to discuss that variable in the presentation. And then as independent variables, we obviously used the mobility score. We also included socioeconomic characteristics, and then for vehicle kilometers traveled, we added car availability in the household. First, I'm going to give you some very brief descriptives. The most interesting one, I think. So the mobility score, as you can see, the lowest group and the group with the lowest score and the group with the highest score are the smallest percentage. So below 5 is 13.6% and below 9 is almost 12%. So the biggest bunch is a bit in the middle. And then you can see number of cars in the households. There are 13% who has no car in the household, and then almost half has 1 car, and then the rest have 2 cars or more. And then I'll show you a graph with mobility scores against the number of cars in the households. And this graph actually illustrates quite nicely that we can assume that mobility score matters, at least from a certain threshold, 8+, that is. So then you see an increasing percentage of households without a car, but as well a declining percentage of households with 2 cars or more. And then to test the effect of the mobility score on car ownership and to control for other variables, we ran multinomial logistic regression. So we have a categorical independent variable with 3 categories, so no car, 1 car, or 2 cars or more. We selected 1 car as reference category. And as you can see, the outcomes of the regression analysis are actually quite in line with our hypothesis, namely that mobility score is significant, but that it demonstrates a rather poor ability in explaining car ownership. All the variables proved to be significant, but I'll move over to the next slide because I think these variables are a bit more interesting or more show higher significance or higher odds ratios. So as you can see that the singles and with and without children are less likely to have no car compared to the group that has 1 car, and it also shows that monthly net income, the acquisition of a car is positively associated with income. So people with lower income are more likely to have no car compared to people with 1 car. And then the second part of the regression, we have 2 cars compared to and 1 car as reference category. Again, you can see that mobility score is significant, but also that, and I'll move over to the next one, that household composition and monthly net income also shows higher odds ratios. And then especially an adult living with 2 parents. So that means that there are potentially at least 3 people in the households with a driver's license that these are more likely to have 2 cars compared to the group that has 1 car. We also ran and you can see also the monthly net income, that the higher income groups are more likely to own more than 1 car. We also ran this regression with only mobility score as independent variable, and then the model showed a very low pseudo R-squares. So Nahukerke R-square was then 0.01, McFadden was 0.03. So that's extremely low, actually, especially compared to the pseudo R-square we obtained with all the other independent variables included. And then I move over to the next part, so mobility scores and vehicle kilometers traveled. So regarding that, vehicles kilometer travels on a yearly basis. So here you can see that the percentage at the extremes. So the lowest mobility score and the highest mobility score show the highest difference as well. So with rather low vehicle kilometers travels for the high mobility scores. And to test the effect of mobility score, we ran a linear regression. And here you can see that mobility score is again significant, but you can also see that the coefficient is quite low. I mean, not even 600 kilometers traveled less a year is quite low coefficient, especially if you compare it to, for instance, the third variable, which is company car. There you can see people who have a company car tend to drive almost 13,000 kilometers more compared to people who do not have a company car. So you can see that mobility score is significant, but that the other socioeconomic and other variables explain actually much more than the mobility score. Gender is also relevant, and as expected, ages as well. So the age group of 26-45 tends to travel mostly by car, or tends to travel mostly a year. And the older people get, the less they travel. And again, which is not surprising, monthly net income also is positively associated with more vehicle kilometers traveled. So to conclude, the outcomes show that the mobility score indeed affects car ownership and vehicle kilometers traveled, but the finding also suggests that the effect is quite weak, that car-dependent behavior is not an exclusive feature of suburban and rural residents, so that although the built environment is a necessary condition to enable sustainable transport, we can see it's by far sufficient to break the cycle of car dependency. Especially, you can see how large the impact is for instance, company cars, or even gender or monthly net income. The built environment is definitely not enough. That is also, of course, due to the fact that the mobility score is a standardized indicator, so it cannot capture personal feature or structural constraints. But it also showed that car dependency is much more complex than simply a lack of choice to travel by another mode than the car. So there are a lot of other things that we need to take into account to explain car dependency. But then again, if we consider potential travel behavior, or if we want to look to future developments, we also know that the neighborhoods with high mobility scores illustrate the type of built environment that is a precondition for moving towards a less car-dependent society. So I'm going to end here. Thank you for your attention. I'm looking forward to answer your questions.
Thanks, Eva. Does anyone have any questions?
Okay, I think we don't have any questions. So let us just wrap up the session. I think it was a really interesting set of papers, and from Europe, USA, and Asia, everywhere. And what I really liked about the session is also that all the presenters were actually female, which I think is hard to find in any transportation conference. So that was an additional plus and a pleasure.
Okay, let's officially get started. Hello, everyone, and thank you for joining us today. My name is Ali Reza Ermegan, and I'm co-hosting the session with my colleague and one of our presenters, Natalia. We hope you have so far enjoyed the first day of our virtual conference and found the presentations useful. Our session has 3 fascinating presentations, as you see. We have the theme of shared economy and micromobility. If you're not familiar with sharing economy, so this concept has been around for years right now, and The goal is to help increase the availability of resources to respond to our day-to-day needs, such as traveling from point A to point B, like using Uber, bike sharing system, Lyft, staying at an Airbnb for travel, or sharing during natural disasters. As I said, we have 3 presentations. The first presentation by Natalia is about understanding the willingness to share personal vehicles in a peer-to-peer market. She conducted a survey mostly focused on Florida to understand the willingness of people to join this sharing economy concept. The second presentation by Stefan is about sharing not just the ride, but also the place to shelter during natural disasters to facilitate evacuation and recovery. His study got specifically in California, focused on California for wildfire. And the last presentation is by Orr, which is about the idea of dockless micromobility usage patterns in Austin, Texas, and how this mode of travel contributes in the general use of micromobility, particularly in the areas that are underserved by transit and bike shares. So each presenter has 20 minutes for presentation, and we get kind of 8 minutes for Q&A. And at the end, Natalia will conclude the session with the main findings and interesting observations. So our first presenter is Natalia. She's currently a postdoctoral associate at MIT, and she will join Delft University of Technology as an assistant professor in December. So congratulate Natalia for the new position. She graduated with her PhD in civil engineering from the University of South Florida, where she studied factors that impact shared mobility adoption and usage. Her research focuses on using statistical and econometrics modeling to recognize the multidisciplinary nature of transportation behavior and explore unconventional factors that affect the behavior of users. Natalia is passionate about increasing diversity in STEM and serves on MIT Postdoctoral Association Board and Women Advisory. A fun fact about Natalia is before she moved to the US, so she was an optometrist. So let's welcome Natalia for the presentation and enjoy our first presentation. Natalia?
Yes, thank you. Thank you so much for that nice introduction, and thank you all for joining. Let me share my screen right now. All right, I think we're good to go. So, as it's stated in the program, my presentation will be about the individual's willingness to rent their personal vehicle to others. And it will be an exploratory assessment, and that's the paper I co-authored with Dr. Yu Zhang, which is a pleasure to see her online, and Dr. Fred Mannering. As you all know, as transportation professionals, is that currently we are experiencing a huge disruption. The status quo is disrupted by new technological advancements and new modes, and that creates an opportunity. And we're currently experiencing this huge disruption that will shape the future, and we are responsible for how this future will look like. So this disruption that cities are experiencing allows to redefine urban spaces and their transportation systems, and that leads to new priorities, new city designs, and all that change creates new behaviors. And one of those behaviors is shared mobility. The concept of sharing economy aims to maximize the resources and its use while decreasing the cost, and increasing accessibility of products, goods, and services. There has been a substantial change in mindset from you are what you own to you are what you can access. And that shift is happening in front of our eyes. One of that one of the parts of that shift is peer-to-peer car sharing. And this is a very simplistic diagram of peer-to-peer car sharing. We have a supply side, demand side, and the operator. Supply side in this graph means all the people who are willing to give somebody else an access to their personally owned vehicle and receive a fee. The demand side represents all the users who will use somebody else's car. And then there's the operator, usually a third-party company that rents the vehicles and helps with scheduling. Sharing has been recently argued by many to be a novel concept. And in fact, a lot of researchers have pointed out that sharing has been practiced by low-income communities for centuries. But what is new in sharing economy, and in particular in shared mobility, is that technology allowed to share one's resources with people outside their network. So we can let somebody else stay in our house, or let somebody else use our vehicle. And these are a couple of facts to introduce peer-to-peer car sharing in a little bit more detail. That although the vehicle owners do receive a monetary compensation for renting out their cars, the operations are usually managed by the third-party company, and that company keeps a percentage of that commission. And the operator, the rental agency, does not have to buy the vehicle fleet. Thus, the initial startup costs are negligible compared to a traditional car-sharing model in which the provider owns the fleet. So there's a huge opportunity to decrease the cost while giving an access. And the concept supports that sharing and the use of already owned and hugely underutilized goods, because the vehicle stays in park mode over 90% of the time, allows for decreasing the environmental impact of transportation, and it allows the rental agency to use the vehicle fleet without the need for maintenance. Based on prior research, there are a variety of motives for participating in sharing economy. The main one is always economic, which means people share the resources to get a monetary compensation. But there are also other ones, and that was the trigger for this paper. We wanted to explore what other factors, if any, are there to motivate us to share our resources. And some of them are environmental, social, lifestyle-related, or psychological. Sharing economy concept is based in common psychological theories that I'll share a few in a second. The first one is the theory of hierarchy of needs, which suggests that sharing economy participation is an outgrowth of our psychological and self-fulfillment needs. The other one, self-determination theory, says that the motivations to act can be distinguished as both driven by enjoyment and others by economic benefits. The theory of planned behavior is somewhat different, implies that a motive to engage in certain activity is dependent on beliefs about that activity and information available to the users. And the last, social exchange theory, focuses on the formation of motivations for economic relationships through exchanges in a network. So all these theories have some differences, but there's one main similarity, that we participate in shared economy because we get some self-satisfaction from doing so. So we decided to develop a very detailed stated preference survey, and we collected social demographics, characteristics, travel data, commute patterns, parking time, traffic crash history, health data, households compositions, and more. The survey was distributed from the University of South Florida with help of the bike sharing program, but we also advertised it to the students as well as through social media to gain a little bit more broader audience and a wide variety of participants. So the data collection happened in the early 2018. So this study is about 2 years old, and we ended up with 644 observations. The dependent variable in this study was we asked the respondents how likely they are to rent out their personal vehicle and receive a monetary compensation. And here's the breakdown of our results. Extremely unlikely, it's still a very substantial part of the sample, 285, unlikely, really high. And then a much smaller group was likely and extremely likely. And to increase the reliability of the data, the responses of users who claimed they did not own a vehicle were removed. So we avoided the respondents to make hypothetical choices. This is a descriptive statistics of our sample. We have a wide variety of participants. Although these are not all the variables we collected, these are just some of the most common that I used in these types of studies. We have over 10% of people with children under 6, which in our prior research has shown that the presence of children plays a huge role in our travel behavior. Household size, age, income, gender, race, and even motor vehicles per household. To arrive to the conclusions, we estimated a random parameters ordered probit model to take advantage from our ordered response. And the dependent variable, as I mentioned, was the willingness to rent out a personal vehicle and receive a monetary compensation. All parameters that are in this study are normally distributed because there was no other distribution that outperformed normal. And we estimated the models using 1,000 Halton draws. And all the presented findings are statistically significant at least p equal less than 5%. So here are our results. The higher probability to be extremely unlikely, and the reason we are talking about the results on the extremely category is because one of the disadvantages of this type of model is that we cannot necessarily say what impact that the independent variable has on the dependent variable on the intermediate categories. So the higher probability to be extremely unlikely to rent your personal vehicle to others had respondents who identified as females, were Caucasian, from one-person households. And this one is a very interesting variable. One-way travel time to a grocery store of 5 minutes, but one-way distance of being more than 1 mile. And I'll talk more about that. So let's go one by one. Females had a higher probability to be extremely unlikely. And I'd like to point out to this finding because genders act differently in the transportation reality. And females have been historically overseen in transportation planning. And they have been shown to not have equal access to opportunities. They suffer from time poverty. And in this particular business model, they have higher probability to be extremely unlikely to rent somebody else their personal vehicle, which consequently means that they have higher probability to not have that additional income from that act. And then another variable, Caucasians, although the concept of race has been disputed by a lot of psychologists as a controversial variable, a lot of researchers use it as a deductive premise. And in statistics, it could capture historical experiences that are usually experienced by a particular race. Another one is the one-person household. So people who live alone had higher probability to be extremely unlikely. And the last one, we also tested every other variable that we had in terms of commute and the grocery store distance, and this only combination came up to be statistically significant. So it likely captures some of the lifestyle choices and living locations. The next variable that I was very excited to see was the lower probability to be extremely unlikely to rent somebody else your personal vehicle had people who were previously registered for bike sharing program. So we can speculate here that people who have already been a part of shared economy are likely part on the could also had a lower probability to be extremely unlikely to rent their personal vehicle. So that creates an opportunity, and it shows, or at least we can speculate, a particular mindset. These three parameters were identified as random parameters, meaning they do not have a homogeneous behavior, and people who are at least 40 years old, their impact varied. And the next one I would like to point out, because it's household income above 200,000 which is relatively high. And considering that prior research has found that the main motivation to participate in this type of business model is to gain financial benefit, I expected that the people with high income will be unlikely to let somebody else use their car. But our findings suggest otherwise. They suggest that there is an opportunity to engage all levels of income, and even those from high income households, they will likely meet their psychological needs, which we discussed before, and still participate in peer-to-peer car sharing as the vehicle suppliers. And then the last one, the households owning one motor vehicle, that was also interesting, because if they had one motor vehicle, a portion of that group had a still higher probability to be extremely unlikely, but the other part had a lower probability. And that shows a varied dependency on their only car. Here are marginal effects that we have also estimated for the random parameters ordered probit model. It shows you when the sign changes from positive to negative, and how we justified the results that I just presented. And to bring it all together, transportation, and in particular shared mobility and sharing economy, does no longer mean only solving congestion problems or minimizing traffic crashes, but also creates a unique opportunity to fight for social justice, to create accessibility, increase public health, and gender equity. Discussion on policy and opportunities. As I just mentioned, the opportunities even for the households with very high income, that was not something that we expected to find. And then the needs for policies to acknowledge gender differences in peer-to-peer behavior. There's a unique, we're living in a unique time that now that we're forming the policies, we can just do it in the right way, to not oversee any groups of people, and instead of then going back and changing the policies should be formed to acknowledge the differences, because it's easier to just get it right rather than then going back and changing that behavior that people have adopted. And then the peer-to-peer car sharing is a promising way to decrease cost and increase vehicle utilization while meeting some of the psychological needs, not even mentioning the environment, and decreasing the overall production. And based on other researchers' work and our literature review, there's a huge need for national policies, because some of the people who said that they are not willing to rent their personal vehicle were worried about the insurance company. So there is another opportunity from the insurance company perspective to play a role in the viability of this business model. Every study has their limits and so assumptions that had to be made, so is ours, and here are a few that I would like to highlight. The temporal and spatial instability. Because it's such a brand new business model that has not matured. The behavior that was captured was only captured in this certain point of time, and it will likely change based on which direction this business model goes. We also assumed that the individual willing to rent their vehicle would be satisfied with the compensation. It is somewhat consistent with the business models that some allow for flexible pricing, meaning the owner names the price and then the company can adjust it, or it's the other way. And then, of course, all stated preference surveys ask to make a hypothetical choice, while the real behaviors may differ in some cases. And that's going to be the end of my presentation. Thank you so much.
Sweet and short. Thank you, Natalia. If you have any questions for Natalia, please feel free to post on our chat box, and we are going to ask Natalia to answer your questions. We have 5 minutes for Q&A. Okay, Natalia, you can see the question. So Stefan asked, how do you see the peer-to-peer car sharing change with the current pandemic and 1 or 2 years down the line?
Thank you, Stephen. This is a great question that everyone is wondering which direction we're going to go. I find this to be a huge opportunity, actually. And let me tell you why. Because a lot of people are working from home and they do not use their vehicles. If somehow we can encourage those users to let somebody else use their vehicle, because public transit is experiencing lower frequencies. A lot of people who really need that car to get to work because that's what their job requires do not have access to it for mostly economic benefit. So I think there is a tremendous opportunity in this business model, particularly when transportation is experiencing a disruption in the disruption. And to answer the second part, in 1 or 2 years down the line, I think like it's going to be mainly impacted by the policy. If the users and the owners of the vehicles had a little bit more confidence in terms of the insurance policy, because they don't know who the user of their vehicle is going to be, I believe that could increase the success of the business model. And I think we will only know that in a few years, depending on if it's going to completely not work out or if it's going to experience more interest.
Thank you. Any other questions? Yeah, till you think about if you have any question or not, I would like to...
Oh, sorry. I saw just a question come in. One about the random parameter. So the random parameter model, it captures the unobserved heterogeneity. It's a very standard modeling process to capture all the omitted and unobserved variable. And although we don't know what they are, we know that there is a variation, especially that is very important in studying human behavior, because we are by default incapable of collecting every single variable that impacts our behavior. And did I miss any questions? Do you have any foresight into the operator role of public agencies versus private companies? That's a good question. Thank you, Stephen. Do you mean public agencies as subsidizing that business model?
Yeah, I guess in the idea of either subsidizing public-private partnerships or as in a complete shift into public agencies providing the entire operating service on their own, especially given changes because of COVID. I'm curious what you think about that.
I do believe that our system is extremely overloaded because the public transit is not making money and they need subsidies already. In an ideal world, I would suggest the subsidies for the owners of the cars to encourage them to share their vehicle, and maybe through that process they would gain more confidence. It's about making that shift. Like COVID creates the opportunity because we change our behavior, and now the question is, are we going to go back to our old behavior or continue? And I feel like that's something that we already have the fleet. The cars are sitting in our parking spots or garages, and a lot of people struggle to get to work. So I would see a huge opportunity for the public agencies to somehow incentivize that business model.
Any other questions? Okay, I have a question, Natalia. So you conducted a survey, and for sure you had some hypotheses when designing your questionnaire and survey. I'm wondering, based on your analysis of the data, was there anything that surprised you in the findings, or things that was against your hypothesis or did not work the way that you thought?
Yes, we also, as I mentioned in our data, we also collected a lot of health variables, and the paper is a part of a larger study. And in many of the other shared mobility behaviors, such as frequency of use of ride sourcing services like Uber and Lyft, and frequency of use bike sharing, or even substituting a bike sharing trip for a car trip, we found that self-assessed health and or high BMI played a role, which we did not find in this paper. And that was surprising, because I expected there will be some connection to health, which it didn't work. And another surprising finding was that high income and the bike sharing registration. High income, I was pleased to see that we're not only driven by economic benefits, but we're also driven by our psychological benefits, as well as the sharing mindset. If we can build up on that and maybe cultivate that sharing mindset, if somebody is already a bike sharing member, maybe they'll be more likely to use other modes of shared mobility. I feel like there is a huge opportunity and a huge value that could be brought on a larger scale.
Okay, we have another question.
Yes, I see. Could you please try to relate this to a country such as India, where vehicle ownership and income are lower? That's a good question. I believe if the vehicle utilization in India follows the same pattern as it follows in, for example, US, meaning the vehicles are parked for 95% of time and they still are underutilized, I believe there is an opportunity. I think it all goes back to the utilization, which I am not sure what the utilization rate of the vehicle is. It like one vehicle per person? Is it a one vehicle per family? Because I feel like that could change a lot of things and the viability of this business model.
Good. I think we need to wrap up the Q&A session. Thank you so much, Natalia, for a great presentation and introducing the concept of P2P for the car rental and from the supply and demand side. I know you're tired right now, little, but I let you introduce our second presenters and his study, and we will have the second presentation after.
Yes, thank you so much for engaging and asking questions. It was a very insightful conversation, and because sharing is already available and underutilized resources such as vehicles has been shown to have a great potential, as it is in my paper and all the other papers. Similar concept can be also applied to other scenarios, and that's what our next presentation is going to be about. Stephen is a doctoral candidate from Berkeley. We'll talk about the role of trust and compassion in the willingness to share resources in cases of evacuation. So in his paper, he estimated a binary logic model to gain further insights into human behavior, response, disaster, and resiliency. And this is a short bio of Stephen to introduce him in a little bit more detail. As mentioned, Stephen is a doctoral candidate at Berkeley in the Department of Civil and Environmental Engineering. His research focuses on the multidisciplinary intersection of evacuations, decision-making, shared mobility, sustainability, and sociology and public policy. He's affiliate with the Institute of Transportation Studies and the Transportation Sustainability Research Center. He serves on multiple committees at TRB, and he was a National Science Foundation Fellow, ENO Fellow, and Eisenhower Fellow. So very big accomplishments. And a fun fact, in the summer of 2015, he cycled over 3,000 miles across the United States from Baltimore to San Diego to support young adults affected by cancer. And without further interruptions, Stephen, take over.
Thank you so much. Let me share my screen. Sorry about that. It's always difficult with two screens, but I appreciate everyone for joining in on this session. I am going to be presenting on the role of trust and compassion and willingness to share mobility and sheltering resources and evacuations. This is a case study of wildfires, so just want to mention that outright, and this is work along with Joan Walker and Susan Shaheen, also at UC Berkeley. All right. So just a brief introduction. I realize that most of the presentations in this conference are actually not disaster related. I might be the only one, so just want to give a brief background on that. And it's really focused. I really focus my research on large-scale evacuations, which is one of the primary methods to safeguard human life in natural and also man-made disasters. We've seen this with millions ordered to evacuate from Hurricanes Irma, Florence, and Dorian, as well as 1.1 million people ordered to evacuate from California wildfires. And of course, there's a number of other disasters that also lead people to have to evacuate, such as a potential for a dam failure from Orville a couple years ago with 180,000 people, as well as a chemical plant explosion in Texas with about 50,000 people. Of course, these large-scale evacuations are only going to increase in size and frequency with ongoing climate change, as well as increasing development in high-risk areas. So in my research, I've really come across three critical evacuation challenges that can really be summed up in the idea of safety, but I want to call out three specific ones that I see as the most critical. First is persistent non-compliance evacuation to mandatory evacuation orders, as well as poor transportation response leading to heavy congestion, slow evacuation clearance times, as well as high evacuee risk. And so a lot of the opportunities for transportation management agencies to provide improved responses are not actually being done currently, and that's largely because of a lack of planning. And finally, there's really been minimal attention in ensuring that all populations, especially those most vulnerable, have transportation and sheltering. And so if you remember anything from this presentation on the critical challenges in evacuations, you can think about it in compliance, congestion, and social equity. So how do we tackle these different challenges? Well, one opportunity and one strategy is looking at the sharing economy. So I focus on the feasibility of the sharing economy and emerging mobility and evacuations. And this has been enabled through new technological connections such as expanded internet and smartphone adoption, as well as the increase of sharing economy platforms such as Airbnb, Uber, and Lyft. And the idea behind the strategy is that resources from private companies or citizens could supplement public resources. So they do a business-to-peer or a peer-to-peer mechanism, such as carpooling that Natalia just described, or car sharing that Natalia just described. And you can also think about the idea of sharing rides and shelter within the community and neighborhoods, but also with strangers. So there's kind of two different levels with that as well. So this emerging idea of the sharing economy is that you could use the sharing economy to increase the resource availability, given that there is substantial capacity and some demand for these resources in evacuations. And past research in the last couple of years has found both of those to be true, especially demand for individuals who do not have vehicles who would actually welcome having these types of resources available to them. Also, research has found that sharing economy companies have acted in over 30 US disasters, so these companies are already acting. So it's only, we need to think about policies and mechanisms to increase the resources through these companies. And the main question becomes, how do public agencies increase sharing behavior in disasters? So the research development behind what I'm presenting today, first we came up with a hypothesis, is that trust and compassion could trigger willingness to share transportation and sheltering resources during evacuation. We formed this hypothesis largely because there is mixed evidence that trust increases following disasters, and there's strong evidence that compassion increases following and during disasters as well. So our goal of the research was really to understand the influence of these different factors, including trust and compassion, on willingness to share transportation and sheltering. And we used post-disaster surveys from two different California wildfires, the 2017 December Southern California wildfires and the 2018 Carr wildfire. As a note on limitations, the sample does skew wealthier, whiter, and more educated than the actual geography. However, in our case, it is not as much of a concern, largely because a lot of the areas that were impacted by these wildfires were also wealthier, whiter, and more educated. In terms of scenario development, we developed a willingness to share idea, which was transportation before the evacuation as well as transportation during the evacuation. We also came up with 2 scenarios for shelters, shelter for free and shelter for a cost. And so this is just one of the sample questions. If you had known of individuals in need of a ride, how likely would you have transported any individuals before you and your household evacuated? And we did this on a Likert scale from extremely likely to extremely unlikely. Our modeling methodology, we actually decided to use a binary logit, mostly for simplicity since we were conducting 8 binary logits. But another key aspect is that we wanted to isolate the extremely likely people to share away from all the other answers. Because we were a bit skeptical that people who said that they were moderately likely to share would actually share in a disaster. So we wanted to get the more realized behavior, and so we decided to go about it this way. Of course, we retained significant and behaviorally important variables related to trust and compassion, demographics, evacuation circumstances, as well as something we call urgency indicators. In our surveys, we did ask individuals the level of, for example, fire, visual fire level at the time of their evacuation, and we consider an higher urgency to be higher visual fire level, for example. As a note, we did retain some insignificant variables to reduce bias, which we note is less efficient, but we did still include them. Better to reduce bias than have a more efficient model. And then we also simulated a high trust compassion and a low trust compassion community to see changes in sharing rate. So going into the results for our work, we have trust indicators. First on descriptive statistics, the change in trust following wildfires. You can see that people substantially, their trust of other people, specifically in their community, increased substantially following the wildfires, increasing substantially as well as increased moderately. And of course, there is some that stayed the same. For other trust indicators, from mean level of trust of other people from very low to very high, we can see a nice wide range. Of course, we trust family and friends the most. That is not surprising. But the trust doesn't actually go that low, for example, for strangers. Most people still, to some degree, are trusting strangers, which could pose a possibility for sharing in disasters. And so we use these different trust indicators in our model in order to do that. We also have compassion indicators, and this is based on the Santa Clara Brief Compassion Scale, and this is 5 different compassion levels from general all the way down to tender compassion, and we specifically asked these questions to individuals on what they thought. And so these are the mean compassion levels for not true at all to very true. Again, we can see relatively similar levels of compassion across. Tender compassion was, though, a little low for the Southern California wildfires. And then for our specific dependent variable, we asked willingness to share, and we're reporting only extremely likely to share here. And so this is a little bit actually different than Natalia's work in that it seemed actually people were very willing to share their resources in a future disaster, particularly transportation, likely because this was a temporary mechanism to share resources compared to that of sheltering. So it is interesting to note the differences between our 2 papers and that people are just much more willing to share these types of resources in a disaster context. Now, there is obviously still a question as to the extent to which people are actually going to share the resources, since this is a stated preference and not a revealed preference. But just the willingness is already a good indication and could pose a great possibility in these disaster situations. So into the model, so I'm not going to share the exact table because it's a very large table and I don't want to have eyes glazing in terms of numbers. So I'm just going to present some of the more higher level results. And again, these are the different scenarios, and we divided it between the 2 wildfires since the geography for the 2 wildfires was substantially different from each other. The Southern California wildfires were mostly a highly urbanized area, while the Carr wildfire in Redding, California, kind of transitioned in from rural to suburban and a little bit into urban. So we can see in terms of willingness to share, what increased sharing willingness was high trust of different types of people, such as friends or strangers, as well as increases in community trust. We also see that high non-selfish compassion, increased willingness to share for the car wildfire, as well as being a volunteer in a past disaster. On the negative side, people just weren't willing to share transportation for a cost, and we saw that in the last slide. We also see that higher income households were not willing to share for the car wildfire. For sharing housing for free, we can see for the Southern California wildfires, for, again, trust of neighbors and substantial increase in community, increased willingness to share housing for free, as well as high helping compassion, which goes to show that people just aren't really willing to share their housing for a cost. They may think that this is not a good idea for a disaster, and so that really shows that compassionate behavior. On the negative side, though, people who had children in the household, such as families, as well as smaller households, and long-term residents were less likely to share housing. On the car wildfire side, again, compassion was important. And in this case, the 1 to 2 person households flipped, which is, we're not exactly sure why. So we had to dig a little deeper into that to really understand the difference between the two here. And then for not sharing, the constant was really the only one here. For sharing transportation before, we actually saw a kind of an explosion of variables to describe what was going on. For the Southern California wildfires, again, trust and compassion were our two main indicators for willingness to share. On the non-sharing side, long-term residents were, again, not willing to share, perhaps because they had their own plans already available and they didn't necessarily want to share before the evacuation began. On the car wildfire side, we see compassion. If you didn't have any trips before evacuating, you were more likely, just purely more time. And then these urgency variables. If there was a very high smoke level or very low visibility, they were actually more likely to share transportation before evacuating. Our hypothesis to this result is that people actually realize that the only way that their neighbor or someone else is going to survive a fire is if they actually provide that transportation resources directly to them. And so that's why we think that these urgency variables are moving the needle in terms of sharing. On the not share side, though, we see that, again, families are less likely to share. We're seeing a mandatory evacuation order as well, which could be something, we're not exactly sure on this one, but it could be the language in that order telling people to leave. And then people who shelter at with their family are less likely to share before as well. When individuals are en route to their destination, again, trust is important. Being a volunteer in a past disaster, and having high presence of police along the way, we think that the police could actually be a mechanism to tell people to go check on your neighbors, for example, here. For the car wildfire, again, trust, compassion, and having spare seatbelts in this case, and multiple spare seatbelts, not just one, not just two, but 3+, was really the indicator here. Not willing to share, though, young adults, as well as, again, families, and then very high presence of first responders along the route. And our hypothesis here is that they think that the first responders, such as in EMT or fire, are going to help the people who may still be in their homes and may not be willing to share. All right. So then for the just generalized takeaways. So first, the summary of the modern characteristics. These were just some of the descriptive statistics that came out of the models. They included our R-squared and adjusted R-squared values. Note that actually a lot of these values are quite in line with a lot of work in disasters. There's still a lot of variability in how people make choices. So actually these are quite in line with a lot of work in the evacuation disaster space. And then we also did a quote-unquote simulation for a high trust compassion versus a low trust compassion community. And we can see here that when we change all these dummy variables into everyone is high trust versus everyone is low trust from a 0 to a 1, we can see that these trust and compassion variables are really driving people's willingness to share. And we can see a really large increase. But this also shows that the current level of trust and compassion communities is actually not that high compared to what it could be. So there, again, we can be expanding. But I do also want to note that even if it's a low trust and compassion type of situation or community, people are still willing to share their resources, which is, again, a benefit here in our work. All right, and then on to, this is also for the car wildfire. I did want to make sure that I did both the wildfires, but again, we see very similar results between the two. All right, so key takeaways. So first, trust and compassion matter. The increased willingness to share regardless of resource or wildfire context. One thing that came out of the research process is that we just had a hunch that this could be the case, and that was our hypothesis. We didn't realize the extent to which trust and compassion matter in willingness to share. And so I think that's in and of itself a very interesting takeaway. We do want to note that the demographic variables were really scattered. Volunteers and past disasters and members of community organizations were somewhat more likely to share, but this wasn't always significant. Families and longtime residents were usually less likely to share, but again, not always significant. And then also varied and isolated influence of income, age, and gender, and no effect of education, employment status, and ride-hailing experience, which is a little bit of disappointment, especially considering if we want to create kind of an ecosystem of sharing that Natalia mentioned, having this ride-hailing experience, for example, did not actually change people's willingness to share in the disaster situation. It may, though, work for under normal conditions, which could be something interesting to as a future research idea. A couple other key takeaways. These circumstances were somewhat significant for the transportation scenarios. Some influence of receiving a mandatory evacuation order, as well as usually spare capacity increased willingness to share, but it wasn't always significant. And our thinking is that spare capacity is just a prerequisite for sharing. It doesn't actually get people to do it. And again, these evacuation urgency variables generally increase willingness to share, such as higher smoke levels or police presence or first responder presence. And then urgency variables, which are related more to the car wildfire. And finally, I want to go into some of the different recommendations, because I think it's really important to have practice-ready results directly out of our modeling results. So it's very clear. Increasing community trust and compassion as a part of disaster preparedness will help to increase willingness to share resources. This can be done through civic events or neighborhood networks, preparedness events as well. And part of this could also be to develop closer partnerships with community-based organizations and their volunteer networks. Linking these different networks, for example, to neighborhoods and communities with a high proportion of access and functional needs populations, also kind of known as vulnerable populations. Ensuring community members can easily volunteer, as well as maintaining these volunteer networks to keep volunteerism high for the next disaster, will also be critical in increasing this willingness to share. It's already a mechanism in which we can be moving resources around. Oops, sorry about that. And then a couple other recommendations. We want to be increasing public resources, such as public transit, through either NGOs and CBOs or through, again, public agencies. And we can also be thinking about carpooling as another mechanism specifically for areas that have previously evacuated from wildfires, who may be less likely to evacuate particularly during COVID-19. And then also we want to be increasing community trust and compassion during and after the disaster, not just before. And so this would be continuing information of community needs, but also in that period of time when people are evacuating, we may be able to leverage police and fire personnel to communicate the need to share and also to check on neighbors. So it's just another communication mechanism in order to get that shift, that nudging behavior to move over. So with that, I do have a couple of acknowledgments. The National Science Foundation, as well as the Federal Highway Administration, and the University of California Institute of Transportation Studies. And a big thanks to the agencies and community organizations who helped distribute the survey across California. There is a working paper available. It is open access. You can go check on it. The paper is currently in review, but we have a working paper available. So if you really want to dive into the very specific different statistics as well as the models and the numbers, I highly recommend you look at that and go through there. Citations I provided in this presentation, and that's it for me. And I'm happy to take your questions. And thank you so much.
Thank you, Stephen. Thank you. That was really great. I found two very interesting things in your presentation when I compared it with mine. That's trust doesn't change much for strangers. I feel like that was a great observation. And the willingness to share changes in the face of the disaster, which also, that was very interesting. We're waiting for the questions to come in, but as they're coming in, I have a question for you. So based on your research, how do you believe that the sharing economy can impact on your work? What was the most vulnerable population or the most opportunity?
Yeah, that's a great question. I think there are certain groups of people who would be more able and more willing to use, be the users of shared resources. So, you know, providers of shared resources, but there's a whole other question about the users. And the carless populations is an easy one. For example, those with however, and like older adults who may have access to technology, but I want to caveat that, of course, with technology. But a number of different groups, such as those who may have physical disabilities, may not be able to use these resources because the vehicle or the shelter is not accessible, for example. There's also questions on homebound individuals, on, for example, just finding where they are. That is a question that agencies have struggled for years, is where are vulnerable populations? And there is ongoing debate on whether there should be some type of registry, who owns that registry, is the government going to be able to provide those resources? So there are definitely certain groups of vulnerable populations who could really benefit from this. But for those who you might not be able to find or might not be able to use the resources, additional steps might have to be taken, such as training people, drivers, on how to assist someone who's physically unable to get to a vehicle and on getting there, or in the shelter, for example. So there's definitely different equity implications for different groups. But I think there's both an opportunity, but significant challenges and barriers that need to be overcome. And I think pre-planning and communication are going to be critical in that.
Thank you. We have 3-4 more minutes, so let me loop back to COVID-19. And that's probably going to be the last question for you in this segment until we move to another presenter. So how do you see sharing economy a response strategy, a viable option for COVID-19 and building resilient cities?
Yeah, so I think in the term, I think in the near term, there is going to be, you know, I guess generally, and then I'll go into more the evacuation standpoint. Generally, I do see a potential shift towards public agencies taking a broader role in on-demand transportation, right-sizing of vehicles, thinking about how to change their operations to be more efficient. And I think some of that is going to be through shared micro transit, for example, shared bike sharing, scooter sharing, as well as perhaps creating their own car sharing or carpooling systems. So I think there is definitely going to be benefit, but there are obviously there are a number of limitations, such as sanitation, that we have to overcome. There's still that trust component on a more broader scale on getting people to actually use these resources and provide that. In the disaster space, again, it's the sanitation and trying to figure out if you can trust someone else with these resources. But I do think there is a lot of benefits in terms of social distancing, because we're not necessarily using a lot of these buses, for example, to transport people. And there has been a huge shift, particularly in California in the wildfire season, of moving to non-congregate shelters. Most of congregate shelters we think of as like a public shelter, as like a gymnasium and a school where cots are pretty close to each other. But there's been a huge shift in non-congregate shelters, such as hotels, as well as motels. And so Airbnb and other private homes of citizens can also be along this more non-congregate shelter that could decrease the issues related to that, related to COVID and spreading of it. So I think there's a lot of benefit out there, but I think pre-planning is so important in this situation, and trying to build those networks from the ground up can sometimes be difficult. So it might have to be working with already established community associations and community-based organizations.
Thank you, Stephen, for your presentation and taking the questions. I will refer to Ali Reza, who will introduce our next speaker.
Thank you.
All right. This brings us to our last presentation by Or Catsby. For those who just joined us, Or's presentation is about the usage patterns of dockless micromobility in Austin, Texas. And in his study, he tries to understand the contribution of this mode of travel in micromobility usage. Or is a doctoral planning and public policy candidate at Rutgers University. His research focuses on micromobility travel behavior and micromobility sharing services, examining and evaluating new technologies' potential to reach more people and promote equity and sustainability. He's enthusiastic about maps, and in the last 6 years, he was teaching GIS to undergraduate and graduate students. Native of Israel, he studied his bachelor's degree in environmental studies and geography at Hebrew University and finished his master's degree in urban planning at Technion. In his free time, he likes to hike, bike, climb, and scuba dive with his wife and his 3-year-old son. Okay, Or, time yours, and we wait for your presentation.
All right, thank you, Alaraza. Let me share my screen. Great. So just let me correct you. In this study, I study both dockless and docked micromobility and try to compare them. This study is part of my dissertation, and it continues a previous study that just got published that examined the e-scooters in Austin. And here, as I said, I compare the e-scooters with the docked bike sharing that exists long before in the city of Austin, and the shared e-bikes. So, sorry. Right. So micromobility is a relatively new term that includes bicycles, e-bikes, scooters or e-scooters, and some other stuff like segways, overboards, basically anything that's smaller and slower than a car and used for transportation. And shared micromobility was more familiar as bike sharing until recently. And the thing that is the most common that we are familiar with is the model of a docking station, which was first introduced in 1995 in France to prevent the theft and to maintain the functionality of the system. So in this model, users need to take the bike from a docking station and return it to a docking station, which limits the coverage and the flexibility of the system. The dockless bike sharing release us from these limitations. They were first started actually in 2000 in Germany, but we are more familiar with the dockless bikes from China, the OFO bikes, which introduced in 2015, and they are based on GPS and smartphone technology, and they are very easy to operate. And in 2017, also e-bikes and e-scooters entered the dockless sharing market. And this time, these vehicles equipped by electric engine, which make it easier to operate, and they can cover farther distance to reach more population, make the ride easier. So in the United States, these dockless e-scooters and dockless e-bikes were introduced at the middle of 2017, and by the end of 2018, as you can see in the graph here, shared e-scooters were the most used mode. So they more than doubled the total usage of micromobility, which is very, very impressive in 1 year. So the 3 vehicles that we have, and all the 3 vehicles are available in Austin. The bicycles, the traditional bicycles that require full effort to operate. They require people to know how to ride a bicycle. Their speed is slow to medium, 10 to 16 kilometers per hour. And they're ideal for a range of half to 3.5 kilometers. Sorry. The e-bikes equipped by electric engine, and they also require people to know how to ride a bike, but it requires much less effort. You still need to pedal in order to operate these bicycles, but it's easier. And because of the engine, you can cover a larger area, larger distance. And finally, the e-scooters, they can be faster than the bikes, but they are slower than the e-bikes, and they do not require any effort at all. They don't require the knowledge of riding a bicycle. So people can just ride them with whatever they wear. So dresses, business suits, they're more suitable for this stuff. Their main disadvantage is they're lightweight, which make them much more vulnerable than the bicycles and the e-bikes for accidents. And that's, I don't discuss this in the study, but that's, you can hear more about it in many other papers. So my case study is the city of Austin. And the main reason is because I have the micromobility trip logs publicly available with locations. And that's kind of rare in other cities because companies usually don't want to share it, but they're required by the law in Austin. So Austin introduced cherry scooters in April 2018 and was one of the first cities in the US to do so. And during this time, so during the time of my analysis, there were 5 e-scooter operators, and currently there are about 3. And there are also e-bikes. There used to be 2, and now there is 1 operator, and there is the city public bike share. During 2019, there were about 5 million e-scooter trips, which make it one of the leading e-scooter cities in the United States. And for those of you who are not familiar with Austin, is a very vibrant city with about 1 million people. Some will say the most urban city in Texas. It's also the state capital and the home of the University of Texas, Austin. So my research questions here are, how usage patterns of dockless micromobility sharing different from those of bike sharing? Does dockless micromobility sharing increase micromobility usage in Austin? And does dockless micromobility sharing increase micromobility usage in areas underserved by transit and docked bike sharing? So dockless micromobility sharing literature is pretty new, is still emerging, and it adds to a rich micromobility body of knowledge that's been built in the last few decades, which examined the usage of bicycles, e-bikes, and bike sharing. And trip purpose is a key element in travel behavior research. Docked bike sharing trip purpose vary by city, gender, membership type, age, ethnicity, socioeconomic status, and many other factors. Nevertheless, commuting is the most common bike sharing trip purpose around the world, and other utilitarian purposes are also common. The influence of bike sharing on car usage is uncertain. On one hand, bike sharing does replace some car trips, but on the other hand, it replaces more walking trips or transit trips. And there is also the car trips that are being done in order to operate the system, to redistribute, and to maintain the bike sharing fleets. I mean, these are also exist in the case of e-scooters and the dockless. All right, so temporal patterns is one thing that I check in my study, and this is the temporal patterns of the bike sharing from the literature. And usually what we see is 2 peak pattern in the weekday and 1 peak pattern in the weekend. That's for regular users, for subscribers. And casual users usually have only one peak on the weekend or the weekday. And we can learn from this that the system is being used for commuting because there is a peak of usage in the morning commute time to go to work and on the evening commute time to go back home. Previous studies show that these temporal patterns for dockless e-bikes and e-scooters resemble more casual users. So you can see here in green, there is only one peak in Washington, D.C., as found by McKenzie, or also in some other cities, only one peak, and that means that these vehicles being used mostly for usages that are not commute. So it can be either recreation, tourism, or other utilitarian purposes. On the other end, studies that used surveys found that commuting and other utilitarian purposes are commonly even. There is some kind of contradiction between the data, the usage data, and the surveys. So for my study, I used aggregated spatial approach. So the main data sources that I got are the dockless and the docked trip logs from the city of Austin, which all include also spatial information, which is accurate to the third decimal place, which is about 100 meters. So first I analyzed the trip logs themselves, regardless of the location, and then I did some more advanced analyze of the locations and the things that are around it. And I'll talk about it later, but what I did was taking the locations, put them in the city of Austin, and that's how it looks when we zoom in. As you can see the shortage of the decimal places, so it looks like spare 100 meters. I built a grid around it, and then I aggregated the total number of trips in each of these cells. So in this map, for example, this is the total trips during the entire examined period in the entire city. And for the bike sharing, I created service areas around the docking stations using 400-meter walking distance buffers based on the street network. So this is something that is very common in bike sharing studies. And for these polygons, I added data from census statistics and from the built environment, and create a list of variables that are later used. So first, the examination of the trip logs. So these are the total trips per day for e-scooters in orange, e-bikes in blue, and bicycles in green. And you can see that e-scooters dominate. There are much more e-scooters available and people use it much more. But the interesting thing in the right side, so the dark gray region is the examined period. It's when the e-scooter and the e-bike usage has been stabilized. And I cut it just before the South by Southwest Festival, which created a huge peak of trips. And you can see in the right graph, there is a black line, and this is the usage in the year before. And just to show that the total number of micromobility trips didn't decline, but actually increased, even if you only look on the docked bicycles. When examining the trip histograms, so generally things look pretty similar between the different modes. So the dockless e-scooters, the docked e-bikes, and the docked bicycles, sorry, dockless e-bikes and the docked bicycles from the previous years are all being used more on the weekends than on the weekdays, which is another thing that tells us that is more for recreation and purposes that are different from commuting. And only docked bicycles in the examined period has about the same number of trips during the weekday and the weekends. We are looking at the peak patterns. The dockless e-bikes have the most. It looks much more than 2 peak pattern than the other modes, but all resemble some kind of morning peak and then an afternoon peak to some extent. And on the weekends, there is only 1 peak. So when I look at the trip statistics, I can see that e-scooter and bicycle trips have similar duration, length, and speed patterns, although there is an electric engine that can make them drive faster. E-bike trips, however, much longer, farther, and faster than the other modes. And interestingly, previous year's bike sharing trips were longer and slower than the trips on the examined period. So everybody increased their speed. People who used to ride a bike share slower now drive the e-scooter faster, and people who ride a bike sharing still do it, but faster. When I look at the special patterns, I can see, so the first thing I can see that most of the usage is around the downtown of Austin and the University of Austin, University of Texas in Austin. This is the 2 red zones. Another examination is the place where trips start and end in the morning and in the evening, and you can see that is like a mirror for e-bikes, e-scooters, and bicycles. So trips are being taken from the outskirts to the center in the morning, and from the center to the outskirts in the evening. So it does show some kind of commuting pattern, but you can see that the scooters have the least a bold pattern like this. And another thing that I checked is the correlation between bike sharing and dockless sharing usage, the special correlation. And in the upper maps, I just put them together in the same area. The area is covered by bike sharing, and the area that e-bikes and e-scooters are being used, and they're pretty much correspond, pretty much used in the same areas, a little bit expanded in the area of the University of Texas, but not to a dramatic extent. On the lower 2 maps, however, I did the same just with the transit coverage. So it's mostly buses in Austin. And there is absolutely no correlation between where the bus covered the city and where the bike share, the dockless bike sharing is being used. So it's neither extend, neither or correspond with bus usage. So for my final analysis, I wanted to examine the effect of external influences on bike sharing and e-bike sharing and e-scooter usage. So I used all these variables that you can see here in the table. I won't go over them because we don't have a lot of time. And the method that I used here is random forest. So this is a machine learning technique that based on the decision tree model. The decision tree analysis split the sample based on the value of the selected explanatory variable into 2 groups with similar response value. And the process repeats until no more splits are possible. And the random forest is basically just an array of decision trees. When I use different sets of explanatory variables in every time to check how they contributed to the accuracy of the model. And the results of the random forest is it's the importance diagram, right? I get an importance mean squared estimate for the importance of each variable. And this is just 3 examples out of 40 models that I ran. I took just total arrivals for the entire period over the entire city. And quickly, what we can learn from this is that the most important variables in the model are the spatial variables. So the row, what you can see here is it's a tau here, tau 1K, 5K, and 2K. This is different local spatial components in different caps based on the IDW. And also the distance from the city center, that's the global component. And beyond that, we can see, for example, that median income is very important for e-scooters. And if you want to read more about this, that's actually what's the first paper that just got published is about. But the results are different in each model. So I'll just sum them, just took the main findings here. So residential and industrial land uses have their largest contribution for citywide dockless trips. Educational land use has the biggest influence on bike sharing. Income has highest effect on bike sharing and lower on e-bike usage. And population density has high contribution to usage. Employment density only affect dockless sharing. And morning trips have totally distinct patterns than all the other models that show that these trips might be a commute trips because they have really different results. So for the conclusion of my study here, the new micromobility sharing services in Austin dramatically increased shared micromobility usage in the city from around 100,000 trips between August 16, 2017 to February 28, 2019, to almost 2.5 million trips in the same period on the following year. Micromobility users who are willing to pedal faster using non-powered bike sharing for short trips and e-bike sharing for longer trips. Users who prefer lower effort use e-scooters for short trips. Dockless micromobility usage hotspots highly correspond with Austin's bike sharing service area. Aggregation of the results suggests that commuting is the primary trip purpose for weekday shared e-bike users. And at the same time, commuting is also common to some extent among the shared e-scooters and the bike sharing users, but not the main usage. Weekday morning e-scooters and bike sharing trips seem to represent commute trips as well. And the low correlation with recreational land use and the short trip pattern suggests that most of the micromobility trips in Austin are not recreational, but short utilitarian trips. So for errands or something like this. And this seems to be the after work and free time short trips, mainly in central Austin, to arrive into point of interest or to be engaged in an activity. Bike sharing usage is more dependent on social demographics than dockless micromobility. And that means that dockless micromobility sharing reach more diverse population indeed. And this is a very exciting finding. And that's it. So let me know if you have any questions.
Thank you, Or. If you have any questions, please post on the chat room.
How do I?
We have a couple minutes for questions before Natalia and I conclude the session.
All right, I can see something here. Is there anything I'm missing in the chat? No, right?
Okay, while we're waiting for possible questions, I just have a clarifying question. Or so you are presenting the results of the random forest model and the importance factor that presented in one of the figures for the 3 modes of travel. I just want to clarify that those are the variables that effect in the prediction process, but not necessarily can be interpreted as the coefficients of any variables or contribution like that, the parameters value or elasticity values in that way.
Right. So I kind of rushed through this explanation of random forest because of the time. But yeah, so these are the variables that increase the accuracy of the model. So they can be interpreted as the variables that are more important for the usage, but I cannot know whether it's positive or negative contribution, or whether it's big or small, like in regression models. And there is a problem with regression models with special factors, like special negative binomial, for example, that doesn't run very well for such large samples. So in this sample, I had 17,490 cells. So that's why I came with some big data solutions for this thing.
That makes sense. Yeah.
But totally further studies should try to elaborate this part. Yeah.
To see the direct or indirect impact of them. So Leo has a question. If the use of e-scooters depend on population density, does it not help to complement transit in a less dense area? You can see the question in chat box too.
Right. So if the use of right. That's a great question. I did not see any usage in areas that underserved by transit. I took only weekday transit areas, but I did not actually use the transit data, so the transit ridership or the frequency of the buses. But they have the potential to do so, right? But it's also really dependent where the companies deploy the e-scooters. And my study and other studies in Austin actually found that the usage is mainly in the city center. And this is area that is highly served by transit, highly served by bike sharing. So we didn't see anything like that, like a neighborhood that is underserved by transit or anything like this with high usage of e-scooters.
Okay, thank you. Since we have only 3 minutes till the next session starts, which would be in the same room, I would like to ask Natalia to make a short conclusion. And thank you so much again for your participation and to our presenters for their great presentations. Natalia?
Thank you. So thank you all for participating in this session. And I would like to conclude with a couple important findings. From my paper, I would like to highlight that there's an opportunity for high-income households, especially the psychological opportunity to participate in shared mobility. From the second presentation, the trust and compassion, the trust doesn't change so much for strangers. And the other one, there's a huge willingness to share in the disaster, as Stephen's research has shown, which is a huge opportunity for our society. And the last paper analyzed the spatial patterns in usage of micromobility. And I also noticed that the income has the highest effect on bike sharing and less on e-bike. So these are that does not reflect the full scope of the papers. However, these are some of the findings that I found interesting. And with that, I would like to conclude this section and invite you to the next one. Thank you for presenters, my co-host, and thank you for joining us today.
Hello and welcome again to the second Bridging Transportation Researchers Conference. I'm Shervin Atoyan and I'll be moderating this session of the conference. Thank you for your participation today. So here we are, the last session of the Track 3, Land Use Planning 2. And we're going to have 3 researchers from different parts of the world who will share their works with us. As you know, during each presentation, you can type your question in the chat box, and we're going to discuss them after each presentation is over. We look forward to your questions. Okay, let's get started. Our first speaker is Ronak Basu, who is a PhD student in the Department of Urban Studies and Planning at the Massachusetts Institute of Technology. He holds dual master's degrees in transportation and city planning from MIT. His research interests include land use, transport interactions, relationships between mobility and life outcomes, and urban long-term decision-making under uncertainty. He is particularly interested in the impact of emerging and new forms of urban mobility on travel behavior and metropolitan growth. He has previously consulted for the World Bank on public transit accessibility and integration with on-demand mobility in Latin American cities. He is now going to present his work on generating virtual cities for land use transport interaction models. Ronak, you're unmuted and you should be able to share your screen with us. Please go ahead.
Yes, thank you for the introduction, Sherwin. So let me go ahead with my screen. Can everyone see my screen?
Yes, we can see it.
Oh, there we go. Thanks everyone for sticking around for the final session in today's track. So my talk is titled "A Framework to Generate Virtual Cities as Sandboxes for LUTI or Land Use Transportation Interaction Models." This is a paper which we've worked on at MIT and SMART in Singapore. I've co-authored this paper with Roberto, who was a PhD student of Joe's. I am a PhD student of Joe as well. So Roberto is now an assistant professor in Mexico. The agenda for today's talk would be just going over the background of LUTI models and understanding the history of the evolution and the need for modeling land use and transport interactions. Then I'll try to make the case for why virtual cities are necessary for LUTI models as we move forward in our modeling efforts. Then I'll present the framework that we propose to generate virtual cities, show you a proof of concept application, and then discuss some avenues for future research. So LUTI or land use transportation interaction models have been around in some form or another for a long time now, since Hansen's work in the early 1960s, I think it was 1959. So he first proposed accessibility measures which connected mobility or transportation and land use. And building off of that concept in the 1960s, we started to see the Lowry model or the Metropolis model and ITLO, which tried to mainly focus on OD forecasting, and those were aggregate models. In the 1970s, we started to see a lot of work in the economic theory realm. So we started to look at regional economic models, which looked at different economic sectors and tried to model their interactions. So we came up with models like TRANUS, MEPLAN, and PCAS. And concurrently, there was also a lot of work done on trying to model the decision-making in housing markets in a more disaggregate way. So we came up with the bid rent frameworks, which led to models like MUSA and Delta. In the 1990s, we had cellular automata models, mainly driven by an increase in computing power, such as Sleuth. So that was done by Keith Clark. And in the 2000s, that kind of was the golden era of LUTI models, where we saw several of the models being proposed all around the world. So Urban Sim was proposed by Paul Waddell at Berkeley. iLute was proposed by Eric Miller at Toronto, and Illumus was proposed in Europe. So all of these are agent-based microsimulation models, and which obviously require a lot of disaggregate data. But more importantly, the computing resources are now available to be doing agent-based models in a tractable simulation. And all of that is to say that, yes, we've made a lot of progress, but then again, the future is more uncertain than ever, especially now that we've witnessed what a pandemic can do to society. So Luty models have been criticized in the past for being unable to predict ICT impacts. Basically, we have not been able to understand the trends properly of unseen phenomena, for example, shared mobility or telecommuting, which might increase as we move into the post-COVID recovery plan. And there has been a paper by Eric Miller arguing that mere mobility and land use representations are not enough. We should be going for a system of systems approach, which has become necessary. So when we look at large scale changes in today's world, it's not just limited to the urban scale or urban phenomena, but now we're looking at climate change, we're looking at natural disasters, we're looking at pandemics. So perhaps we need to expand our horizons and move from Luty models to integrated urban models, where some of these overarching phenomena can also be included. One of those models, or at least we've attempted to build one of those models, it's still a work in progress, is SimMobility, which is an abbreviation of Simulation of Future Urban Mobility. That's an agent-based microsimulation platform developed by MIT and SMART, and I'll be going back to that later in my presentation. So now that we have a good sense of the history of Luty models and why we need certain changes in that realm, so let's talk about why do we need virtual cities? So what's wrong with the status quo? We have seen various applications of Luty models, but unfortunately, most of those activities have occurred in the global north. To be more specific, in the Americas and Europe. So because we have these different research groups in different places in the world developing Luty models, which are obviously extremely computationally and financially expensive to set up, there are limited opportunities to evaluate replicability, transferability, and generalizability of Luty models. For example, if MIT is working on SimMobility for Singapore, obviously we cannot share the Singapore data because that's extremely disaggregate the data that we need to calibrate the model. So there are data privacy concerns, and similar concerns would occur over sharing, let's say, Toronto data for ILU. Also, Luty models have been critiqued for their limited use by planning agencies. So as academics, we can obviously implement very sophisticated algorithms and work with big data, quote unquote, and we can calibrate these Luty models, but planning agencies obviously do not have the time or the technical expertise to be continuing that effort. So because of the difference between planning and implementation, Luty models have not been utilized in practice as much as in academia. The virtual cities offer an opportunity to expedite collaborative research. And how does that occur? So we've experienced virtual labs, we've heard of virtual realities, and now with the COVID-19 pandemic, so we're all going to experience online teaching in some form or another. So that is a virtual classroom. So motivated by that, you can think of the virtual city as like a prototypical study area that kind of alleviates data privacy concerns because we can directly release the data open source. It doesn't cater to a specific city or a study area, so there should not be any concerns over an open source release. So in terms of understanding what a virtual city is, quite simply put, it is the function of transportation infrastructure and spatial distributions of people and places. So you take a hypothetical city's transportation infrastructure and then you populate it with people and places, assuming distributions that resemble actual cities. So the framework that we use for generating a virtual city is represented on the slide. So first of all, you have data inputs, like I said, you have the transportation network, and building off of that, you can create a land use zoning plan. After you have prepared your inputs, then obviously we need to look at more disaggregate spatial geometries, such as parcels and postcodes, because we are trying to generate this virtual city for agent-based microsimulation. After we have the disaggregate spatial geometries in place, which could also be census blocks for people who are more familiar with the US spatial geometries, then we need to populate this virtual city with people and establishments from an actual city. So we look at the distributions of the populations in an actual city, and then we randomly sample from that. And finally, we allocate that population, ensuring that the distributions make sense looking at historical patterns. So we allocate households to housing units. We go beyond just residential location. We don't just say that this household resides in this postcode or in this census block. We allocate an exact housing unit because this is an agent-based microsimulation. And we can go further with job location as well. So instead of allocating individuals to jobs, we can, job postcodes, we can allocate exact jobs to individuals. So let's try to understand these steps in a little bit more detail. So the first step of the framework was looking at data input. So first of all, you have your transport network. We need a transport network that's detailed enough for microscopic transport simulation. So this has to be exogenously provided by a transport planning agency, or you can generate a transport network on your own. So there have been some papers written in the 2010s looking at network grammars to generate transport networks. We have a paper on this where you should be able to find the references. So as you can see on the figures on the right, so the first sub-figure over here, my mouse is hovering over that. I hope you can see that. These are TAZs, or traffic analysis zones. Then we have the MRT or the subway network. Then we have the bus network with the bus routes and the stops. And then we have the road network with nodes and segments. So pretty standard representation for a microscopic transport simulation. But all of this is assumed to be provided externally. So it's either by a transport planning agency or it's generated using some grammars or network science approaches. Given that particular transport network, now we can start to construct the land use zoning plan. So that would be defined by the user or the modeler or the urban planner based on the transport network. And obviously we need to come up with a plan that shows plausible spatial patterns, for example, higher residential density near transit. So we look at several different land use categories. So we kind of assume that the city is going to follow a transit-dependent orientation. So you have a CBD over here where you have commercial land use. You have some mixed residential and commercial, and then the yellow represents residential. You have some educational parcels. So you would have universities over here. The schools can be situated in the residential parcels because schools are generally situated close to homes and school districts and so on. And over here you have, on the southwest edge of the city, you have industrial, and you have an airport here as well. So now that we have the transport network and land use parcels, let's try to go further and generate disaggregate spatial geometry. So generally in agent-based microsimulations, you know where people live and work and do activities. So those are in buildings. So from those buildings, they enter the transport network at certain nodes or at certain points in either the public transport network or the road network. However, we don't know yet where people live and work because we don't have agents built up yet. So we have to work this out in reverse. So we know the entry points. We know the nodes of the road network. We know the bus stops. We know the MRT stations. So we assume that those are the entry points where people enter the transport network. Using those entry points as seed generators, we create parcels using the Voronoi cell approach, and the centroid of each parcel is a postcode. So over here you can see that we've separated out each land use parcel. We've taken the entry points, and now we have much smaller parcels over here, and the centroid of each parcel is a postcode. So that takes care of the disaggregate spatial geometry creation. Now we want to sample populations from a real city. So we can select any real city. That depends on the modeler or the user. We can randomly sample the population of households, buildings, housing units, and jobs based on a pre-specified sampling rate. So that would depend on the overall area and the density that the modeler wants to create. So, for example, if you want to create the virtual city that represents the downtown of a particular metro region, let's say the Boston metro region, then your sampling rate would be much higher because you want more density to be packed into that smaller area. But if you want that to be a prototype of Metro Boston, which is not as densely populated, then your sampling rate would be much lower. It's worth noting that when you sample these different populations, we do not maintain relationships between these samples. So a household can be sampled without their housing unit, and the LUTI model is used to perform that assignment because we want to calibrate the population based on the economic reasoning that the LUTI model is calibrated with. So we use a density matching approach for allocating the population to different spatial geometries. We know the theory that population density follows transport networks. So based on that, we compute the transport network density for postcodes in the virtual city and rank them. We compute population and job densities for postcodes or equivalent spatial geometries in the actual city, and we rank them similarly. And then we match postcode groups from the two cities, that is the virtual city and the actual city, based on the ranks. And then we allocate a randomly picked sample from the group match. So after this initial matching is performed, then we need to go ahead and assign the populations to specific units. So this was only matching to the spatial geometry. But as I said, for agent-based microsimulation, you need to go further. You have to assign households to housing units, not just a postcode. You have to assign workers to jobs. You have to assign students to schools. And there are a bunch of different variables that define these preferences or choices, and those are available in different models or within the LUTI simulation. So finally, we come up with the virtual city, which kind of looks something like this, but obviously has a lot of data structures underlying this. So you have different postcodes, you have the transport network, as you can see, the MRT lines, you have the road network, and all of these have different land use categories, and all of these postcodes have buildings. These buildings have households in them. These buildings can also have jobs, and individuals are attached to those jobs or assigned to those jobs. So let's try to understand how this can be used within a LUTI model. So the LUTI model I'll be using to demonstrate this proof of concept is SimAbility, which is our in-house activity-dependent agent-based microsimulator. We have 3 components: long-term, medium-term, and short-term components. So I'll focus mainly on the long-term and medium-term in this presentation. So the long-term on your left looks at long-term urban choices, as the name suggests. So you have the synthetic population, which is generated, and then using a daily bid auction model, we compute housing and mobility choices for the synthetic population. Based on housing and mobility choices, we generate employment and education choices for individuals, because housing and mobility are household level variables. And then if you have a closed system, then you can achieve system equilibrium given enough iterations. But if you have new developments, let's say like new buildings are coming up and are being sold as well, then we'll have to iterate a larger number of times until we reach equilibrium. So long-term passes the synthetic population, which is attached to or assigned to particular units and jobs. So all of that is done. And we pass the synthetic population over to medium-term, which looks at medium-term travel or travel behavior choices. So you have the pre-day, which is at the beginning of the day, we generate daily activity schedules with modes and times for each person. So we know where they're going to work, when they're going to leave, what sort of mode are they going to take, and why are they going to do that activity. It's not just work. Apologies about that. Then we pass those daily activity schedules to the within day, where we simulate the supply. So we have an iteration over here known as within day learning. So we pass the trip chains and we pass back the travel trajectories, and we keep iterating until we reach equilibrium for the route choice decisions. And we can iterate the entire day, which is called a day-to-day learning component. You can see that over here, until we reach equilibrium of the medium-term choices made within that day. So once we reach equilibrium, we can calculate utility-based accessibilities or activity-based accessibilities. and pass those back to the long-term models for like housing, mobility, employment, education, which use activity-based accessibilities as explanatory variables. And there's an iteration here as well. So the whole thing requires a lot of iterations and is quite complex, but can generate very useful information. And it's quite difficult to calibrate this on a real city. We've done that for Singapore and Boston and a few other cities as well, but it's quite challenging in terms of time, effort, and monetary costs, which is why we want to look at a virtual city which can help us go through this entire iterative process much faster. So let's look at what a full loop simulation looks like for the virtual city. So we find that the long-term simulation stabilizes within 6 months at most. It stabilizes much earlier than that, but we simulate every day in the long-term model, and it takes at most 6 months. For the medium term, we look at linked travel times. That's kind of used as a local optimization metric. And for a global optimization metric, we look at TAS-to-TAS travel times, similar to like OD schemes that are provided by transport agencies, transport planning agencies. So in terms of an update rule, we assume an update parameter alpha denoting the weight of the most recent iteration. We don't want to immediately replace the value from the iteration, from the most recent iteration value, because that can cause instability and which will lead to longer convergence. So as you can see over here, this is just a proof of concept. So is there value to doing the within-day learning approach? So if that is the research question, then we can examine this quite fast with the virtual city. So we look at no within-day learning iterations on the left, and then we enable the within-day learning and test that on the right. We look at different alpha values. So alpha equals 0.2, that's a lower value, which means that we don't update the parameter as fast, or we don't place as much importance on the most recent value. So we kind of opt for a smoother convergence, whereas if you have higher alpha values, like I mentioned earlier, you'll have more bumps along the road and you may not converge as fast. And we see that, like for example, with alpha equals 0.2, for the without within-day learning case, we're converging around 11 or 12 iterations. That goes up to 13 or 14 iterations with the within-day learning. So it all depends on whether those additional iterations are worth it in terms of the time and computational resources that are required. If you look at the simulation runtime, for example, we can run a year of the long-term routine in just 2 minutes for the virtual city. For the pre-day, that takes 11 minutes. For supply, that takes 5 minutes. So if I were to do a day-to-day learning routine, so that would be 11 plus 5 times the number of within-day learning loops times the number of day-to-day learning loops. And all of this is on a regular desktop, which any of you would be able to run. 16 gig RAM, 8 threads, pretty standard. For Singapore, which is much larger and obviously has many more agents, it takes 30 minutes to run 1 year of long-term, and medium-term is the bottleneck right now. So we see that it takes like 14 minutes for a day's worth of simulation. So that's 14 hours for 24 hours of simulation. And this is on a server. So this has, this is on an HPC, actually, high performance computing cluster with 256 gigs of RAM and 60 threads. So there's no way we can run Singapore simulations on a desktop or a laptop. It's going to take ages, which is why the virtual city is so much valuable to have, because you can test all these different strategies for calibration or for even prediction and understand whether those are worth pursuing or not. So we've done a case study looking at the difference between AMOD, which is automated mobility on demand, competing against mass transit. That was published in Transportation Research Record a couple of years ago. We found that mass transit is irreplaceable, and that has been cited a few times, and that just goes to show how the virtual city is quite useful. So in terms of future research efforts, where do we move from here? So obviously, as people have been saying, and in recognition of what we see around us, LUTI models are not going to be enough anymore. We need to move to a systems approach, looking at integrated urban models. And as those become more complex and more data hungry, we need virtual cities. We cannot depend on real cities and fragmented research communities spread across the globe. virtual cities enable us to collaborate. So we could do two kinds of experiments. So we can create virtual cities for multiple real cities. So we can run a particular LUTI model, let's say sim mobility on each virtual city. Let's say we create a virtual city for Boston and Singapore, and we compare the transferability of a certain scenario that is run using sim mobility on Boston and Singapore. We can also explore differences in the different LUTI implementations. For example, with the virtual city that I just presented, when that comes online, open source, Eric Miller should be able to test it using iLute. We should be able to test it using sim mobility. Waddell should be able to test it using UrbanSim, and we can examine the generalizability of overall trends. So if we are to simulate a similar scenario, can the trends that we observe in the future be termed as generalizable? So there's a lot of work to be done in this sphere, and we hope that this paper kind of spurs things along and opens up this effort of moving from LUTIs to IUNs. I would like to acknowledge the National Science Foundation of Singapore for funding the study through our SMART program, and would like to open up the floor for questions and comments.
Great, thank you so much, Ronak. We have a question here for you from Dr. Robert Schneider. Are there parts of the transport network for pedestrian or bicyclists?
Yes, so we can, when you look at segments, so you can specify segment properties that take care of pedestrians and bicyclists. So you can have like sidewalk width, you can have bike lanes if you want, so those would be under segment properties.
Great. Another question is from Pedro Donoso Sierra. Is there a difference between this and digital twin cities?
Yeah, so in digital twins, so that's a new term that has come up, I think, around like 2017 or 18. So we haven't really worked with digital twins per se, but in digital twins, I would imagine that people go beyond land use and transport interactions. So those are more representative of the integrated urban modeling. So we are trying to converge the integrated urban modeling realm with our experience in LUTI modeling efforts.
Thanks. And the last question is from Jason Hawkins. You can also see the question in your chat box. For clarification, is the objective to provide anonymized data for a specific city from which multiple research teams can develop models, or is the objective to apply the data imputation anonymization techniques presently used by statistical agencies?
I would say it's more of the former. So both of those are objectives or were motivations when we started doing this work. But the primary motivation is enabling the creation of such virtual cities, which can be shared among multiple research labs or groups across the world.
Okay, thank you so much, Ronak.
Thank you.
Thank you for your great presentation. Please go ahead and let go of the screen so that our next speaker can share their slides. Okay. So our next speaker is Dr. Robert Schneider, who is an associate professor in the University of Wisconsin-Milwaukee, Department of Urban Planning. He has 20 years of experience in the sustainable transportation field. Dr. Schneider has led more than 25 peer-reviewed journal papers contributing to international research on pedestrian and bicycle safety, demand analysis, and travel behavior, and is going to present his work on fatal pedestrian crash hotspot locations. Robert, you're unmuted and you should be able to share your slides with us.
Yes, thanks so much, Shervin. And can everybody see that on my slide on the screen?
Yes, we can.
Great, thank you so much. So I'm going to move from one side of the land use transport field to a whole other side of it, which is the relationship between transportation and land use and traffic safety, and present on United States fatal pedestrian crash hotspot locations and characteristics. Did this research along with my co-authors, Rebecca Sanders from Arizona State, Frank Prue from Tool Design Group, and Hamid Amoy from our Urban Studies program at UW-Milwaukee. Why pedestrian safety? For those of you who are in the US, you may know this already. For those of you elsewhere, it's really important to recognize that we have a real troubling trend going on right now in terms of our pedestrian fatalities. Since 2009, we have increased annual pedestrian fatalities in the United States by more than 50%. And now we're at levels of pedestrian fatalities per year that are similar to what they were 30 years ago. And so these increases represent people who've died. And every single one of the numbers that you see here is somebody who's died in a transport crash as a pedestrian. And so that's incredibly important to recognize. If we would have kept at the same level as 2009, there'd be 10,000 fewer people who died in the last decade. There's some reasons why this may have occurred. Theories include larger vehicles entering the transport fleet, wider and higher speed roadways, distracted drivers, potential increases in exposure during darkness. But we don't know exactly what the reasons are. And our primary research question does not address this issue, but is really important for informing how we can look at it from a systemic perspective. Looking internationally, the United States is somewhat of an outlier. We had a greater increase than any other country during this last decade or so. There are many countries that have actually seen decreases in pedestrian fatalities over the last decade. So what can we do? We particularly looked at hot spots of pedestrian crashes. Some countries call these black spots, where there are high concentrations of fatalities in our network across the United States. And once we know where those hot spots are, what are their characteristics in terms of exposure, road design, land use, and demographic characteristics of surrounding neighborhoods. Sometimes the transportation profession thinks about pedestrian fatalities as random events because they don't actually happen that often in any particular community. However, once you start looking at the data from a broad perspective over a long period of time, you can start to see patterns, and that has implications for systemic safety measures. If we see patterns, there are things that we can say, if we see this pattern in the future, we're likely to have future fatalities. So there's an imperative for us to do something about it and reduce the risk. Our study looked at data from the Fatality Analysis Reporting System, which is available from the federal government here in the US, and it represents fatalities that have occurred in the transportation system over the last 30 days. They are involving a motor vehicle. Since 2001, the FARS system has geocoded 97% of the pedestrian fatalities, so we used the geocoded data. We excluded pedestrian fatalities on freeways for our analysis, so we're just looking at surface roadways. And we also counted crashes that had multiple fatalities just once. There were about 1.4% of all the fatalities that actually involved 2 or more pedestrians. And we divided our analysis into 2 8-year periods. The first one corresponding roughly 2 years of decline in pedestrian fatalities, 2001 to 2008. And the second one with this increase in pedestrian fatalities from 2009 to 2016. Having 2 8-year periods is a way to also check to see if there are any similarities in the hotspots that come up in each different time section that we were looking at. So you have a sense of how we found hotspots. We used geographic information systems. The definition of a hotspot that we used for this study was a roadway corridor that had 6 or more pedestrian fatalities within 1,000 meters over the 8-year period. And you can see graphically how we did that. We searched for clusters of where 6 or more fatality points were located. Some of them, as we went through by hand, there were several hundred of these to go through throughout the country. Some of them didn't line up along a particular corridor, and so those weren't included, but ones that did line up on a particular corridor made our list. Overall, we found 34 corridors for the 2001 to 2008 period, and 31 for the 2009 to 2016 period. This is interesting that only 5 of them were consistent in both periods. So, while we saw many similar characteristics among these fatal hotspots, the hotspots tended to move around. And so it's important to think about, well, what are the characteristics of these types of hotspots if we want to think of where the future ones may occur. With our 60 corridors that were unique, we looked using Google Street View and Google Earth at their characteristics. We also gathered traffic volume data and gathered some data from the American Community Survey on neighborhood socioeconomics. We divided them into 3 different major types using cluster analysis. The first type, 39 of the corridors, were regional thoroughfares. These regional highways tended to be high speed, 35 mile an hour, 45 mile an hour roadways, multi-lanes, so in this case, a 6-lane highway, high traffic volumes, many of them higher than 25,000 vehicles per day, some as high as this one, 60,000 per day, long block lengths, many driveway cuts, relatively few opportunities for pedestrians to cross this type of roadway with signalized protection. And the land uses surrounding it tended to be single-story commercial and big box stores. So there were many parking lots surrounding these with the driveway curb cuts. The areas around this were low-density residential for the most part. You can see another example of a picture here from Maryland. These are both regional highway type hotspot corridors. Second type was the urban primary arterial roadway, and these had a lot of similar characteristics with the regional highways. They weren't quite as high speed in many cases. They still, almost all of them were multi-lane, high traffic volumes, but they did have a few more signalized crossings and some on-street and off-street parking mixed. They tended to be major thoroughfares cutting through urban neighborhoods rather than regional highways connecting more broader or wider urban regions. Interestingly as well, from an equity perspective, communities of color were common around these corridors and tend to be the victims in these types of crashes. Here's another example of that type of corridor from Florida. The third type of category was New York City's corridors, and they are slightly different than the others. This one is Canal Street as an example. It's a very highly used traffic way as well as very high pedestrian volumes. You have very high activity levels, all using a relatively small space. This is still a multi-lane thoroughfare. There are many signalized crossings though, and the surrounding area is dense and mixed use. One other example from New York City, First Avenue, showing here a cross-section from before 2010. This corridor actually changed afterwards. So it's one of our examples that had 7 fatalities during the 2001 to 2008 period, but only had 1 fatality in 2009 to 2016. And if you take a look at the corridor from Street View in post-2010, it actually looks different. New York City made some changes to take this from a 5-lane one-way street down to a 3-lane one-way street with a dedicated bus lane as well as a dedicated bike lane. This is just one case study example, but in this time period afterwards, there was only 1 fatality. It went from 7 fatalities down to 1. So the road design may have had some association with that reduction in fatalities. Future research, we would look in more depth at all of these and see how they changed over time. But looking broadly across all of our hotspot corridors, where were they located in general? The Sun Belt had the most hotspot corridors. 60% of them were in those cities in the southern part of the United States. Many of them were along national or state highway systems, numbered routes, 57% of those hotspot corridors. And these are types of corridors that often prioritize automobile speed and throughput for that function of the highway network. And then our New York City corridors, 14 of them, 10 of them in Manhattan, just very high activity locations, but having very high vehicle volumes going through pedestrian-oriented areas. When we think of the characteristics of these types of locations, it's really important to understand the underlying reasons why we may see fatalities occur in the first place. And vehicle impact speed in terms of the travel speed is one of the most important factors, as well as vehicle mass and front end height. This is how we get high levels of force involved in a crash. Then there's also, of course, pedestrian vulnerability in terms of, for example, the age of a pedestrian or overall exposure levels. More pedestrians, more motor vehicles, leading to a greater chance of a collision occurring. So physics is really important to consider in these corridors, and we see it when we look at some of their other characteristics. Multi-lane roadways. So 97% of these roadways had 3 or more lanes to cross, 70% had 5 or more lanes to cross. This increases the overall time pedestrians must take to cross the roadway, and they're exposed to more vehicles if there's more lanes. High speed limits. So there's greater force exerted if a vehicle strikes at a higher speed. So 77% of these were 30 plus miles an hour. High traffic volumes, that's a greater exposure, 62% having 25,000 or more vehicles per day. And then relatively few crossing opportunities, meaning that these are places where vehicles would be slowing down for the signalized intersection if there is that type of crossing, but if there isn't, you have high speeds in between those types of locations. And many of them had few crossing opportunities. Looking at the land use characteristics and the socioeconomics, there were a couple of key findings. Every single one of the corridors had adjacent commercial land uses. So these are restaurants, retail stores, in some cases bars or liquor stores, but retail was a common characteristic. 75% of these, even many of the regional thoroughfare highways were bus routes. So you had a certain level of pedestrian activity going to access the bus on these corridors. As I mentioned before, there are equity issues, and lower income neighborhoods were very common to be surrounding the hotspot corridors. Now, 75% of them had below 75% of the average median income for the region. And then 53% of these were in majority Hispanic or majority Black communities. And that portion of the US population is only 39%, so they're being overrepresented in these types of hotspots. What does this point to? Well, I think it really suggests the need for a systemic safety approach. If we see these characteristics in common across the 60 hotspot corridors that we looked at, can we actually take actions to reduce the risk of pedestrian fatalities in similar corridors elsewhere, like the one pictured below? It has many of the same characteristics that we saw in terms of regional highways. As in a really important aside and a very interesting case study, US Highway 19 in Pasco County, Florida, had the greatest concentration of pedestrian fatalities in the entire country. It had 7 of the 60 hotspot corridors within its 20 miles throughout the county, and the county is located on the western coast of Florida. By comparison, we had 161 fatalities on commercial airlines in the US over a 16-year period. Just in this corridor alone, there were 137 fatalities to pedestrians over a 16-year period. So these numbers are almost unimaginable, and these in general don't make the news very often. So we need to recognize this as a serious safety issue, particularly in corridors like this. And you've seen a picture of this already in the presentation, but I'll show you again. Basically, this is similar to having an at-grade freeway that allows crossings, and people do cross it at very high risk. So there are a number of considerations with our analysis, and then I'm going to get to a couple of ideas for future improvements and policy implications. But it's important to recognize, we looked at a lot of characteristics of these corridors. My co-author Hamada went through the Google Street View images and identified all the land uses alongside each side of the corridor for 1,000 meters. And that was very valuable, but there's still additional information we couldn't get, like travel speeds. What are the roadway lighting characteristics? Are there particular pedestrian or driver behaviors that are involved? Our pedestrian volume data, we just used a proxy, which is the percentage of commuters from the nearby neighborhoods who walked to work. But that doesn't capture all types of walking that might occur. So that would be important to look at in the future. Our variables, we used Street View and Google Earth images that were available to us, but they're from the 2010s. We didn't have images going all the way back to the earlier study period, the 2001 to 2008. So there may have been slightly different characteristics to some of the corridors during that time. As we look to the future, trying to gather additional data to capture things like lighting conditions, and I'll say a little bit more on that in a second, alcohol involvement, what are the crash types that are involved within these corridors, so we may be able to identify specific countermeasures to reduce crashes. And then think about these broad types of corridors. Are there different types of strategies we can use to address the safety problem in a regional thoroughfare versus in a thoroughfare within a city? So those may have different solutions. Important to note that 15% of pedestrian fatalities are freeway crashes, and of course we didn't look at those. There may be hot spots along particular freeways or the interstate system throughout the United States. And then there's a variety of different ways hotspots can be identified. We chose one particular way to do it, but there's a variety of ways that can be explored. My guess is that you'd probably see many of the same trends, but it's worth taking a look at those as well. I want to say a special thing about darkness. We look at the data for pedestrian fatalities across the country, and in recent years, 3/4 of all pedestrian fatalities have occurred at night. And so it'd be really interesting to take a look at our hotspot corridors and see if any of them have very high concentrations of nighttime crashes, and is there anything going on in particular during those times, such as alcohol use or lighting conditions that may be a factor leading to those pedestrian fatalities. As we move forward, what ultimately can we do? It's not acceptable to have fatalities occurring in types of places that we know exist and where we have, in many cases, prioritized automobile throughput and speed over the safety of people who might be crossing. So what can we do in some of these corridors? Well, there are pedestrian hybrid beacons that can be used as signals to help stop traffic for pedestrians when they want to cross. These are specifically tailored to multi-lane roadways where pedestrian crossings aren't that frequent, but they can get the cars to stop at that particular time. Through signage, we can also potentially lower speed limits and reduce the overall force of the impact, and also give people a greater chance to stop prior to potentially striking a pedestrian. Of course, these changes to signals and signs may not be enough to change the behavior within a corridor. There may be a need for broader design changes, such as redesigning a roadway with multiple lanes down to having fewer lanes. In this case, the lane reduction goes from 4 lanes to 3 lanes. In doing this, you provide space for a refuge in the middle. Islands could be added where that left turn lane is. There's fewer lanes for the pedestrians to cross in this case. And when you do a redesign like this, studies have shown that the traffic speeds tend to decrease. Also, can we look at adding curb extensions and narrowing the crossings that way, which also have a traffic calming effect to certain roadways? These types of design changes can help change the character of traffic, but also we need to think about the overall reductions in automobile use and change of the composition of travel within these corridors? Can we reduce the exposure of pedestrians and pedestrians in particular to traffic fatalities by shifting more trips away from automobile and to other types of modes? We know from several studies that communities that have more walking and biking are safer, yes, for pedestrians, but also for motor vehicle drivers and bicyclists. So we may have even bigger gains than just pedestrian fatalities and safety that way. However, it's really important to consider that some types of corridors may be easier to create this mode shift in than others. For example, the New York City thoroughfares or some of the other urban thoroughfares that were hotspots, they tended to be constructed at a time when transit systems were being developed and they were very walkable mixed-use neighborhoods. So reducing the number of lanes and diminishing the throughput for automobiles may actually be fairly easy to do because people can shift to other types of modes. However, a regional thoroughfare where that roadway is the only highway corridor and there aren't very many parallel routes or transit options or other good walkable options for local trips, it's much harder to make that mode shift. And so we may need to be thinking of much longer land use strategies to make those corridors work better for pedestrian safety. In the shorter term, we may have to think of ways where we could have overpasses or underpasses or pedestrian hybrid beacons that really change the composition of the traffic and the interactions between pedestrians and motor vehicles. So with that, I want to thank you for listening and welcome any questions you have. I want to thank also my co-authors for the great work on the paper and helping all along the way.
Great, thank you so much for your presentation. Seems like there's a question in the chat box from Laxman Bisht. How has your study taken care of hotspot migration issues?
Yeah, so that is something that I mentioned briefly, but it's a really important concept. If you look at hotspots over time, they tend to change the types of locations that are being identified. So we saw 34 hotspots between 2001 and 2008, and we saw another 31 between 2009 and 2016, and only 5 of them from 2001 to 2008 were still ranked in the hotspots for 2009 to 2016. So we absolutely recognize that issue, and that's one reason that we use 2 different study periods to see how much they did in fact change. However, the really important point that we want to get across from our analysis is that the characteristics of these hotspot corridors were very similar in the early period and in the later period. They weren't necessarily the same locations geographically in those 2 periods, but they're very similar in terms of the number of lanes they had and the higher speeds and the, of course, commercial land uses around them. So if we look to the next 8-year period, we're likely going to see these hotspots migrate again, and maybe only a few of them will still be at the top level for the United States, but those other locations that are at the top level will probably have these same characteristics. So traffic safety engineers, planners all across the country need to be thinking, do I have a roadway corridor like this in my community, and what can I do about it now to prevent it from having more pedestrian fatalities in the future?
Great, thank you. Do we have any other questions? I myself have a question here. If you had an administrative authority, what was the first thing that you would change to make things better?
The first thing, I think it would be to slow speed limits in these corridors. And to do that also, I wouldn't just put up a sign that slows the speed limit. I would want to reduce the number of lanes. or narrow the widths of the roadway. I think that those types of changes have been shown through other studies to have very positive safety effects. Now, I could probably do that in about half the corridors of our study. This is just if I had full administrative authority, without really impacting people's core travel or the regional commerce that needs to happen in many of these corridors. But the other half of the corridors that are these regional thoroughfares, my idea of slowing the speeds and narrowing them down and making it really harder to have automobile throughput would be a very tough thing to do politically and just in terms of keeping the traffic going, where it's really dependent on those particular roadways. So I would do it for the places where it was easiest to do.
Mm-hmm. Great. I think there are no questions in the chat box, but I have another question for you.
Sure.
I wonder if you have shared or planning to share this study and its results with transit agencies, or did you get any support from them for conducting this study?
That's a great question. No, we did this on our own. We took the data and analyzed it ourselves. We thought that this issue was so important that it was worth spending a little bit of extra time on. We did most of the analysis last summer, and we're publishing it in the Journal of Transport and Land Use. It was just accepted for publication, so we will have a published version so that anybody who's interested will be able to access it. It will be open access on the Journal of Transport Land Use site in probably a couple of months when they're able to finish publication. And we definitely want to share it with a variety of transportation agencies. I think some of the most important, of course, are our United States Department of Transportation, the National Highway Traffic Safety Administration, but many of our state departments of transportation. In the US, much of this transportation funding and project authority goes through our state DOTs. And so many of these thoroughfares, as I was mentioning during the presentation, are state highways and are national highways. And so those agencies keeping these systemic safety needs in mind can actually have the authority to make some of the changes that we're recommending.
Amazing. We have another question. Is it possible that these hotspots are just by chance? I mean, there could be a place where there were some near misses and it became not a hotspot.
Yes, absolutely. I think over time, there are patterns that develop and that we saw time and time again through the 60 corridors. So yeah, any particular corridor, it might have just been by chance that it had 5 fatalities and not 6 during the 8-year period that we're looking at. And so a few of them probably missed out because of that, and some others just by chance there was an extra fatality within this 1,000 meters, and so it made the threshold of 6. I would still be very willing to bet that the ones that barely missed out and had 5 fatalities instead of 6 probably have a lot of the same characteristics that we saw in our 60 corridors that we identified for this study. I certainly suggest that we continue research in this area, though, to find out if what I think is true is actually true. So using other types of methods to identify corridors is a great way to see if these overall systemic results are consistent. And that'll be valuable to cross-validate this types of research.
Great, thank you. And this may seem a little off topic, but I'm just curious why I couldn't see any footbridges in any of the images in your slides. I haven't been to the US and I wonder whether they're common there.
Yeah, they aren't all that common. There was one of our 60 case study corridors, or the hotspot corridors that we identified, that had overpasses added probably, it was in the second study period, so 2009 to 16. And it saw, of course, a reduction in fatalities. But none of the other 59 had that type of change occur in it. A few of them had fences put up along the median to discourage pedestrians from crossing at mid-block locations. But it isn't as common of a practice, I think, in the US to have overpasses on these types of major highways. We certainly have overpasses for pedestrians where the interstate system or limited access freeways go through urban areas. You'll see that when you drive through major cities. But when some of these major highways go through neighborhoods, that typically isn't a common treatment. One of the reasons that it isn't a common treatment is that it's very expensive, and in many places that they have added them, they found that pedestrians will still cross at grade anyway because it takes a lot of extra time and effort to go up the stairs or up the ramps, over, and then come back down the other side. So you still will have people trying to cross the street at grade.
Yes.
So, and I'm guessing that's a problem in other countries that have these as well, even though they may actually prevent some of the fatalities, which is a positive.
Yes, they're really common in Iran, but we have pedestrians not using them still.
Yeah.
Thank you so much for your great presentation. Now, if you let go of the screen, we're going to turn it over to our final speaker. The last paper is going to be presented by Dr. Eki Kratzberger, who is a senior researcher at the Delft University of Technology, currently at the Faculty for Civil Engineering and Geoscience, and his main focus is on freight transport. He was up to the end of 2016 also a part-time senior planner at the Municipality of The Hague Mobility Department of the Office for Urban Development in the field of passenger transport and urban development. And now he's going to share his paper on climate-friendly mobility. Eki, you're unmuted.
Hi, I'm Eki Kreuzberger, and this presentation is about the planning of climate-friendly mobility in the four large cities of the Netherlands, Amsterdam, Rotterdam, The Hague, and Utrecht. We focus on the long term, like 2050. The presentation is based on a draft paper written by Keith Unsworth and myself, me being the main author, and with support of Rob Konings. The central research questions are, do the four cities have relevant carbon reduction aims? And do the four cities in the field of urban mobility know whether they are sufficiently on track to achieve the reduction aims? And thirdly, is this knowledge anchored at the right place of the municipality? We believe that these questions are not only interesting as evaluation, but also to learn by other cities. Our presentation consists of 4 blocks. In the first one, the introduction, I'll give a brief outline of the climate challenge and of the scope of the presentation and the central research questions I've just mentioned. The second block is about the reduction aims. Also, in relation to higher level aims, and I'll focus on the Netherlands in this presentation. Then I'll talk about the position of reduction aims towards other aims and to which extent they compete or support each other. And in the third block I'll talk about the measures to achieve the carbon reduction aims. Starting with an overview of implemented and planned types of measures, and then moving on to an assessment. The assessment takes place consists of 2 parts. One is the planning steps which have been taken and the involved planning departments. And the second is about the measure packages themselves and their carbon effects. Finally, we draw some conclusions in the last block. Our subject is part of a big social transition process, which will only be successful if all sectors, levels, and types of work, and with the types of work I mean from strategic planning to daily operations, contribute in bottom-up and top-down actions. And our presentation only covers a small part of the spectrum, that is strategic planning of cities in the field of mobility. The scope of the presentation is narrow, but highly relevant, we are convinced, because mobility and cities both have a substantial share in the carbon emissions, and also because cities are a relevant crossroad of multi-sector, multi-level, top-down and bottom-up decisions and actions. The strategic planning establishes the frameworks for effective and efficient climate mitigation by communicating and defining the aims, by defining measures, and using knowledge to clarify the impacts of measures. The Hague has the carbon reduction aim, or the climate aim, to become climate neutral by 2030. Amsterdam wants to become climate neutral more or less by 2050. And it also has an intermediate aim, namely a 55% reduction by 2030. Utrecht was the most ambitious city, wanting to become climate neutral by 2030, but has in the meantime relaxed this aim to as soon as possible. Rotterdam explicitly aims for a reduction of 49% by 2030, and implicitly, that is to say, by the Dutch climate law, of 95% by 2050. We can compare these reductions aims with national aims, and we have three references. One is a study of PBL, Netherlands Environmental Assessment Agency. The second is the government agreement, and the third one is the Dutch climate law. The PBL study concludes that to limit the global warming by 1.5 degrees Celsius, the carbon emission has to be reduced by 55% until 2030, and by more than 100% by 2050. More than is to say that carbon removal is allowed, like processing carbon or storing it underground, or maybe planting trees. The government agreement only has one aim, that is a reduction of 49% by 2030. The climate law has the same intermediate aim and adds a final one, namely 95% by 2050. Before the climate law was decided, there was a discussion in Parliament whether to be more ambitious or less ambitious. And the lower ambition actually got the majority of the parliamentarians, and this is the result. And this is less than what the PBL study suggests, namely these reduction rates. In this slide, only one city, maybe two cities, have carbon aims which will contribute sufficiently to the maximal upwarming of 1.5 degrees, namely The Hague and maybe Utrecht. This leads us to the national carbon approach, to the carbon budget approach, which is a framework to justify decisions concerning different ambition levels. And I can easily explain what it's about. It expresses the maximal carbon and the expected carbon in a certain time and area by a surface, and the expected one is determined by the goals, like what is starting from the current emissions to the intermediate goals to the final goals. Now, in our area, two organizations have carried out such an analysis, the City of The Hague and PBL. But they come, even though they have a similar approach, to different results. And one is that The Hague says that 1.5 degrees maximal upwarming will require becoming climate neutral before 2030. And PBL says that climate neutrality should be achieved by 2050 and preferably before that. So, what is different at first sight is very explainable at second sight. And the differences are due to the allowance of carbon removal, which The Hague does not consider. And PBL is convinced that without carbon removal, the aims will not be achievable. Secondly, the way of geographical distribution of the global carbon budget. The Hague has a distribution method which is more favorable for the southern hemisphere and more challenging for the northern one than PBL does. And of course, thirdly, the reduction aim, the shape of the reduction curve also plays a role. The carbon budget approach is also underlines the relevance of intermediate reduction goals. I will not explain these three figures, but what they have in common is, except that they have in common the same budget, the carbon budget, and the consequence is that dependent on the intermediate aims, you are allowed to achieve climate neutrality in an earlier or a later year. Like if you are more ambitious in the first phase, then you can extend the period to become climate neutral. The last sheet in this block shows the carbon reduction policies of the 4 cities and how they have changed in the run of time. Take The Hague. It once had the aim to become climate neutral in 2050. Then they switched to 2040, and later they have defined 2030 as the year to become climate neutral. Some sense of urgency has played a role in this shift. The opposite is Utrecht. It had the starting point of becoming climate neutral in 2030, and then has relaxed it to as soon as possible. And the background to that is a notion of having feasible aims. We have Amsterdam, which has actually the most continuous or stable reduction policy. The main thing that has changed is that the time period for aims has been extended, but otherwise the curves in different times are more or less the same. And we have Rotterdam, which is the least stable, has the least stable policies. Once having been ambitious, then a new city government entered the stage, and climate had less priority, and that led to this reduction curve. And then another city government came, and the government had more, and climate had more priority, which led to this at least intermediate climate reduction aim. In total, the ambition in the first phases of the cities is less than in the second phase, with the biggest difference in Utrecht, having 1 percent point reduction in the first phase and 7 percent points in the second phase. And one could say that in the run of time, the differences between the phases have become a little bit smaller, and in one case even have been abolished. The climate mitigation the success of that depends on the position on the urban agenda and what the other municipal aims are, like economical ones, cultural, urban, spatial investment opportunities, or social and financial circumstances, or the aims concerning other types of sustainability, like air quality or livability. And these can either compete or undermine the carbon reduction aims. And I will illustrate this on the example of spatial development aims. Currently, the cities are mainly aiming for absorbing the growth in their own territory or their own city. At least this is the perception of the cities themselves. And this idea of the compact city provides shorter distances, lower road shares. It keeps the compact city accessible, and together you could say it supports the carbon reduction policies. However, in the public discussion, also alternative spatial aims have been launched, namely to build in the green heart, the so-called green heart. That is this area here in between a city chain to which the 4 big cities belong. And very clearly, if you start building more in this area than remaining inside the chain, the distances will increase, and also the road share will remain larger. The building in the green heart is socially motivated by housing experts who think that without building in the green, the housing prices will rise faster. And is partly also opportunity motivated by mayors of villages and small cities who think that they who see opportunities to have more growth in their own area. The people advocating the alternative spatial aims typically do not take in account the increase of external costs. And our conclusion is to avoid this pitfall of competing aims to undermine effective carbon reduction. It will be important to condition the urban infill and densification, in this case, providing inclusive developments. And also, it would be needed to clarify the trade-off between housing and mobility effects, external mobility effects. The types of transport measures in the cities which have been implemented the last 10 years are shown on this sheet. It's a summary, you could say. But I want to highlight one of them, transforming bus to tram lines, tram to metro lines, high floor to low floor tram lines, heavy to light rail systems, increasing service frequencies and the average speeds of ground level public transport lines, restructuring many train stations, and upgrading many bus, tram, and metro stops. Important spatial measures of the 4 cities are the densification of central districts, including the increase of the functional mix by adding homes, the reconstruction of former port and industrial areas, the addition of residential areas at some city edges, and the development of some residential satellites around regional train stations. This is a TOD idea on the regional level. There have also been some negative developments for climate and carbon reduction, namely the extension of motorway infrastructure, even where this was debatable. The office development along motorways on a quite substantial scale, and also some budgetary developments. The measures in the strategic plans, they address more or less the same type of measures, but there are also new types. And there's one which I would like to highlight. That is the bidirectional charging system in Utrecht. It connects solar panels and the roofs on buildings with the batteries of nearby parked cars with the electricity grid. This serves the electricity demand of houses and of offices, of mobility and of the rest of the city. Smart algorithms smoothen demand at supply peaks and valleys, and they relieve the electricity grid from needing to transport too much electricity. The development started with the pilot Lombok's-net. In 2019, the city decided a citywide outroll of the system. In some areas and projects, which are well accessed by public transport, also low parking standards, like down to 0.3 parking lots per household, and shared car concepts are introduced. Let me move on to our assessments. The first part, which strategic planning steps have been carried out and at which municipal departments? Currently, carbon reduction of mobility is the subject of 2 types of plans. One are the sustainable mobility plans, SOMs, and the other are the sustainable energy and climate action plans, the SECAPs. The SOMs typically have a horizon of 10 to 15 years, and for climate, this is not long enough. Certainly not if you take the planning paradigm seriously, moving from problem analysis to goal formulation, to design of alternative solutions, to analyzing and comparing the future impacts of the solutions, to taking decisions. The CCAPs are well in this regard. They are transition-oriented. They have a distant horizon of several decades. But they don't cover the complexity of transport, and they typically do not consider mobility demand. And they are elaborated by energy and sustainable departments, while the transport infrastructure and services are developed and co-decided by the mobility departments. So even if their work was good and did not have the shortcomings, it's the wrong place because the sustainable and energy departments don't take the decisions. The conclusion from these observations are strategic mobility plans should incorporate the results of carbon reduction studies and SECAPs, ideally cover the entire period up to the year of climate neutrality. There are some remarks about that conclusion, but in favor of time, I will not go into that. They should be updated periodically because the time is quite envisaged is very long, and because of the future uncertainties, and because the policies might change priorities concerning the types of measures which they prefer. This leads us to what we call the planning ladder to let cities successfully contribute to carbon reduction on the long term. It consists of 5 planning steps, from simple to advanced ones. Simple is measure type of step 1, define measure packages, roughly knowing which ones reduce carbon emissions of mobility. More advanced is define measure packages and explore the change of mobility and carbon reduction that they will provide. Again, more advanced is define measure packages which, proven by explorations, more or less assure that the carbon reduction aims will be achieved. Of course, under acceptable conditions like space saving or affordability. Even more advanced is to embed the measure packages of 3 in mobility or other strategic plans wherever the infrastructure and service investments are decided. And the 5th step would be to update those strategic plans, to update such strategic plans periodically. Sorry, I'm just going to pick a glass of water. Okay, there I am.
It's okay. Take your time.
If we assess our 4 cities along this planning ladder, you could say Roadway step 2, The Hague is step 2 and 3, depending on which study or policy document we are referring to. Amsterdam step 4, and is heading towards step 5. And with this result, you can say that these 4 cities partly still have a lot of work ahead of them, because important steps to successfully reduce the carbon in the strategic planning are missing. The second part of our assessment that is only can only take place for the cities which have carried out step 3, that is defining measure packages that assure achieving the aim, the carbon reduction aim, and these are Amsterdam and The Hague. Methodically, I would like to underline, we have accessed these studies and plans more pragmatically, reflecting on the scope and the plausibility and the reasoning of the quantifications, and without carrying out own calculations. This is a result of this study for Amsterdam carried out by CE Delft and incorporated in their structural vision. In the left column, you see the types of measures, and in the second and third column, you see the carbon reduction effects. And I would, again, because of time, only want to highlight one of these measures. That's the transition to electric transport. The input assumption was that 90% of the traffic in built-up area is electric by 2040, and 50% of the through-going traffic. And this then would lead to a reduction of 24%. The reduction development is also shown in this graph. You see different parts of the measure package leading to different reductions. The final aim is is shown by this gray line, that is a 75 reduction of carbon to be achieved by 2040. And this is the intermediate line to be achieved by 2025. But as you can easily see, none of the curves moves through the 2025 line in 2025, If that was the case, we would have needed such a line. This is interesting from the viewpoint of the carbon budget approach, because such difference can play a role whether you exceed your carbon budget or not. I'll now move to The Hague. This is a picture referring to a study for the region of The Hague. The city of The Hague and the region of The Hague have carried out a backcasting study which was elaborated by CE Delft in 2 sequential years. And the region has summarized actually what it's all about, the conclusion. Here you see the business as usual line, and then what the international measures result in, and then what the local measures ought to do. And you can say about 60% of the required reduction takes place by measures decided on the international or national level, and 20 to 25% is defined by new policies, and another quarter of the total required reduction is sort of a reduction for which the measures still need to be invented. That was the main conclusion of these studies. In a new backcasting study from 2018, we have this type of measures. And most important is that the first 5 ones overlap with the 6th one, the environmental zone for all the city. And the amount of overlap is not known. So again, we are dealing with a type of uncertainty whether this package will lead to the results. One thing is sure, if you introduce an environmental zone for all the city while not having provided alternatives before, then you reduce the accessibility of the city. We conclude concerning the aims that the study documents clearly indicate that in order to limit the global warming to 1.5 points Celsius, climate neutrality would be required before 2050. One could more or less say far before 2050, unless carbon removal is taken into consideration. To avoid that compact city aims are undermined by less climate-friendly spatial aims or other competing aims, the first need to be defined actively in socially inclusive terms. Concerning the strategic planning, an important conclusion is mayors' covenants, municipal climate aims, and European planning paradigms or guidelines apparently do not automatically lead to the strategic planning work appropriate to reduce carbon emissions of mobility on time. I'll move on to this third conclusion. It is not clear whether a high reduction ambition, like climate neutrality in 2030, encourages or discourages municipal officers and politicians to take sufficient action, like the steps 3 to 5 of the planning letter. And concerning the measure packages, none of the 4 cities has convincingly presented measure packages that will reduce carbon emissions from mobility in climate neutral amounts at all, and let's stand on time. And these are some of the conclusions during our assessment, which underline this main conclusion. There are some perspectives, like the policies of electrification in Utrecht, which are technical and also social, behavioral of kind. They have perspectives, and there are many other examples as well. We can also say robotized road traffic has not really been taken into consideration in the 4 plans yet. From other cities, we have positive and negative signals. The negative one is that in some countries with a lower welfare, the substitution rate of cars is likely to be slower than even than in the Netherlands, making the carbon reduction challenge even larger. This is an observation in the European project 2050 Climate City. A positive signal comes from Warsaw, namely that by making transport and mobility more smart, further carbon reduction of 30% might take place. However, this assumption requires verifications. So this is a brief, my last slide actually, the brief overview of our knowledge contributions and also maybe the starting point for other research. We have strengthened the empirical fundament of climate mitigation research by adding 4 more cases. And the strengthening took place actually in all fields, the goals, the measures, and the strategic municipal planning. We also have contributed to clarifying what regional municipal carbon reduction aims are. This is not initially our work, but structuring all the contradictive conclusions or conclusions which seem to be contradictory at first sight, and say which is plausible and which is not. That is how we hope that the things become more clear. And we have presented a framework how to assess the planning steps and the location of decision making, by which we hope that this clarifies more where the gaps are in successful planning work and research work. So thank you for your attention, and maybe you have some questions. And sorry for my dry throat.
It's okay. Thank you so much for your presentation. It seems like there are no questions in the chat box. Am I missing anything? I don't think so. So I'm gonna have you let go of the screen now. All right. This was our final paper, and we had 3 amazing works on land use planning presented in this session. So here we close down track 3 of the second BTR conference. I want to take this opportunity to thank everyone for participating today, and we have been recording these sessions and we will soon share them with everyone. We would appreciate any suggestions for future conferences, so please share your thoughts with us on our website. Looking forward to talking to you soon. See you all around.